Look up at the night sky. What do you see? A scattering of distant, twinkling lights, a beautiful but seemingly random tapestry. But what if I told you that this apparent chaos is an illusion? What if every single one of those stars, every planet spinning in the void, and every vast, swirling galaxy is actually part of a grand, intricate design, a master plan written into the very foundation of reality itself? This is the cosmic blueprint, a profound architecture governing everything from the spin of an electron to the explosive birth of a supernova. It is the ultimate story, and we are not just passive observers, we are woven into its very fabric. As the legendary Carl Sagan once said, "The cosmos is within us, we are made of star stuff." That isn't just a beautiful piece of poetry, it is a scientific fact. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the nuclear hearts of long-dead stars. You, me, everyone you have ever known, are literally the universe becoming conscious of itself. We are living fragments of that grand design, and that gives us a unique and powerful role. We are the universe's way of reading its own instructions. This video is an invitation to join an epic voyage, a journey to decode that cosmic blueprint. We will travel across the vast expanse of time and space, from the very first unimaginable moment of creation in the Big Bang to the ultimate, mysterious fate that awaits the entire cosmos. We will dive into the deepest mysteries that modern science is grappling with right now. What is the true nature of dark matter and dark energy, the invisible forces that shape the cosmos? How could a universe spring from nothing? And what does it mean that the fundamental laws of physics appear to be perfectly fine-tuned for life? We will connect the dots between the bizarre, probabilistic world of quantum particles and the immense structure of galactic superclusters, seeing how the smallest scales are intimately linked to the largest. This isn't just a collection of facts. It is a transformative exploration designed to fundamentally reshape your perspective on reality, on your place within it, and on what it means to be alive in a universe that is both knowable and deeply mysterious. So get ready. We are about to pull back the curtain on existence and peer into the underlying order of everything. This journey will challenge what you think you know and fill you with a sense of awe that only the cosmos can provide. We will see how understanding this blueprint doesn't diminish the wonder, but amplifies it, revealing a reality more strange, more beautiful, and more interconnected than we ever could have imagined. This is more than a history of the universe. It is an investigation into the very rules that allow it to be, and our quest to understand them is one of the most profound adventures any human can undertake. Let's begin. Think of the most magnificent, complex structure ever conceived: a soaring cathedral, a sprawling city, or a circuit board with billions of microscopic pathways. Now expand that vision to encompass the entire observable universe. This is the essence of the cosmic blueprint. It's the idea that underlying the seeming chaos of exploding stars and swirling galaxies is a profound, coherent order, a master architectural plan where every component, from the tiniest subatomic particle to the largest supercluster, has a defined role and position governed by a consistent set of rules. This blueprint isn't drawn on paper. It's written into the fabric of reality itself through the unchangeable laws of physics, the precise numerical values of fundamental constants, and the very initial conditions set at the birth of the cosmos. It's the reason why a hydrogen atom in a distant nebula behaves exactly like one in a laboratory on Earth, and why the force of gravity that holds you to the ground also orchestrates the majestic dance of entire galaxies. For centuries, the greatest minds in history have looked at the heavens and sensed this hidden design, this grand architecture waiting to be decoded. Ancient philosophers gazed up and saw the hand of gods. Today, scientists probe the data from particle colliders and space telescopes. They are all, in their own way, asking the same fundamental question: what is the source code of the universe? One of the most powerful affirmations of this quest came from Albert Einstein, who marveled, "The most incomprehensible thing about the universe is that it is comprehensible." He was expressing a sense of wonder that we, with our limited human minds, can actually perceive and understand the deep mathematical principles that govern the cosmos. His own revolutionary work on relativity was a monumental leap in reading this blueprint. It showed us that the rigid, static stage of space and time envisioned by Newton was actually a dynamic, flexible fabric spacetime that could warp and curve, and that this curvature is what we experience as gravity. This wasn't just a new theory, it was a new page in the cosmic instruction manual, revealing that the blueprint itself is not a fixed, timeless etching but a living, evolving framework. This dynamic nature is crucial to grasp. The cosmic blueprint is not like a static map of a finished city. It is more like the genetic code of a living organism, a set of instructions that unfolds over billions of years, guiding a process of constant change and evolution. The same fundamental laws that dictated how the first quarks combined to form protons are still at work today, governing the nuclear fusion in stars that creates heavier elements and ultimately the building blocks for planets and life. The expansion of the universe itself, the gradual stretching of the spatial fabric between galaxies, is a direct consequence of the initial conditions and the properties of dark energy written into that original design. So, the blueprint influences everything from the infinitesimally small quantum realm, where particles flicker in and out of existence, to the impossibly large-scale structure of the cosmic web. This naturally leads us to a pivotal question. If such a blueprint exists, what clues has the universe left lying around for us to find? How do we, mere inhabitants of a tiny planet, even begin to read the instructions for the entire cosmos? The answers are hidden in the light of the farthest stars, etched into the faint afterglow of the Big Bang, and encoded in the very particles that make up our world. It is a detective story on a cosmic scale, and humanity has been gathering evidence for millennia. To understand how we began this great deciphering, we must rewind the clock and journey back to the earliest civilizations, who first looked to the sky not just for stories but for order. Long before telescopes or written equations, humanity's first astronomers were already at work. Picture a clear, dark night thousands of years ago. A lone figure stands atop a ziggurat in ancient Mesopotamia, their eyes fixed on the shimmering band of the Milky Way. There were no city lights to dim the spectacle, no satellites to confuse the patterns. For them, the night sky was not a random scattering of points of light. It was a vast celestial clock, a divine calendar, and a map of the gods' domain. These early watchers, from the Babylonians to the Egyptians and the Mayans, were the pioneers of decoding the cosmic blueprint. They meticulously tracked the repetitive journeys of the sun, the moon, and the planets, and in doing so, they made a profound and fundamental assumption about reality, that the universe operates on principles of order, not chaos. They believed that the heavens and the earth were connected, that events in the sky directly influenced the rhythms of life on the ground. The flooding of the Nile, the changing of the seasons, the fate of kings and empires. The Babylonians, in particular, were masterful computational astronomers. Operating in what is now Iraq over 3,000 years ago, they didn't just watch the stars, they recorded their movements with obsessive precision on clay tablets. They identified the paths of the planets and could predict lunar eclipses with remarkable accuracy, by recognizing a repeating cycle they called the Saros cycle. Their cosmology was deeply intertwined with their religion. They saw celestial events as messages from the gods, a form of divine writing in the sky. Yet, beneath the mythology was a rigorous, mathematical pursuit of pattern. They created the foundations of the zodiac, dividing the sky into 12 sections, and their work was so advanced that it would later form the bedrock of Greek astronomy. Similarly, in ancient Egypt, the sky was the realm of the goddess Nut, whose star-studded body arched over the earth. The heliacal rising of the star Sirius, which they called Sothis, coincided perfectly with the annual flooding of the Nile, the lifeblood of their civilization. This connection between a celestial event and a terrestrial one was not seen as a coincidence. It was evidence of a cosmic harmony, a designed relationship between the heavens and the earth. This foundational idea that the universe is an ordered system found its most powerful and enduring name in ancient Greece. They gave us the word cosmos. For the Greeks, cosmos did not simply mean the universe as a collection of stuff. It meant order, harmony, and beautiful arrangement, the direct opposite of chaos. This was a monumental philosophical leap. It suggested that the universe was not a realm of unpredictable, capricious deities, but a structured whole that could, in principle, be understood by the human mind. The philosopher Plato took this concept to its logical and beautiful extreme. He envisioned a universe created by a divine craftsman, a demiurge, who fashioned the world from a blueprint of perfect mathematical forms. For Plato, the ultimate reality was not the imperfect world we see and touch, but an eternal realm of ideal geometry. He famously proposed that the elements of earth, air, fire, and water were represented by perfect solids: the cube, the octahedron, the tetrahedron, and the icosahedron. He even suggested that the entirety of the cosmos was structured according to the harmonious ratios of music, the music of the spheres, an inaudible symphony produced by the orbital motions of the planets. As Plato himself wrote, "Astronomy compels the soul to look upwards and leads us from this world to another." He was urging a shift from mere observation to a deeper contemplation of the rational principles governing the whole. While these ancient models were steeped in mythology and philosophy, we must not mistake them for pure fantasy. They were humanity's first scientific theories, grounded in careful, long-term observation. The Mayans of Central America, for instance, developed a calendar system of astonishing complexity. Their long count calendar could track time over spans of millions of years, and their ability to predict Venus's cycles as both the morning and evening star was a feat of observational astronomy that rivaled anything in the Old World. They built pyramids and temples like the one at Chichen Itza, which was precisely aligned so that during the equinoxes, the setting sun would cast a shadow resembling a serpent slithering down the staircase. This was architecture in direct conversation with the cosmos, a physical manifestation of their belief in a structured, cyclical universe. These weren't just rituals, they were practical applications of a decoded celestial order, used to determine the optimal times for planting crops, conducting ceremonies, and ruling empires. So, while we now explain a solar eclipse as the moon's shadow falling upon the earth, rather than a dragon devouring the sun, the core intellectual impulse remains identical. These ancient stargazers looked at the same overwhelming vastness that we do and refused to see chaos. They insisted on finding rhythm, pattern, and meaning. Their tools were different, and their explanations were woven with the threads of their own cultures and beliefs, but they were undeniably reading from the same cosmic blueprint we study today. They established the crucial premise that the universe is lawful, and that its laws can be discerned through patient observation and reason. This bedrock belief in cosmic order, born on those starlit nights millennia ago, would eventually provide the essential philosophical foundation for the revolution to come, a revolution that would replace the geocentric crystal spheres with a sun-centered system and begin to describe the cosmos not with the language of gods, but with the universal language of mathematics. The intellectual landscape of Europe in the 16th and 17th centuries was electrified by a new kind of thinking, a radical departure from the ancient dogma that had placed our planet at the immovable center of all creation. This was a period of fearless questioning, where a handful of brilliant minds dared to look at the heavens with fresh eyes and mathematical tools, forever altering our place in the cosmic blueprint. The revolution began not with a shout but with a quiet, posthumous publication. In 1543, as he lay on his deathbed, Nicolaus Copernicus finally released his life's work, On the Revolutions of the Heavenly Spheres. In it, he presented a heliocentric model, a universe with the sun, not the Earth, at its center. This was more than just swapping celestial positions. It was a fundamental philosophical earthquake. It removed humanity from a privileged, central throne in the cosmos and placed us on a planet in motion, a mere participant in a grander celestial dance. The implications were staggering, challenging not only astronomical charts but the very authority of religious and philosophical institutions that had built their worldview on an Earth-centric universe. While Copernicus set the stage, it was Johannes Kepler who discovered the precise choreography of that dance. A man deeply immersed in the Pythagorean idea of a mathematical universe, Kepler was convinced that God had created the world according to a geometric plan. He inherited a wealth of meticulous observational data from the Danish astronomer Tycho Brahe, and for years he wrestled with the orbit of Mars, trying to fit its path into the perfect circles that ancient philosophy demanded. The data refused to cooperate. In a stroke of intellectual courage, Kepler abandoned 2,000 years of circular dogma and considered a new shape, the ellipse. This led to his 3 laws of planetary motion, a set of rules that peeled back a layer of the cosmic blueprint with stunning clarity. His first law stated that planets move in elliptical orbits with the sun at one focus. The second law revealed that a planet speeds up as it gets closer to the sun and slows down as it moves away, sweeping out equal areas in equal times. And his third law established a precise mathematical relationship between a planet's orbital period and its average distance from the sun, proving that the harmony of the solar system could be expressed in a simple equation. The music of the spheres was no longer a metaphysical concept. It was a quantifiable, predictable reality. At the very same time, in Italy, Galileo Galilei was turning a new invention, the telescope toward the heavens and seeing things no human had ever witnessed before. He saw mountains and craters on the moon, proving it was a complex world, not a perfect, smooth sphere. He discovered 4 moons orbiting Jupiter, a miniature solar system that definitively proved that not everything revolved around the Earth. He observed the phases of Venus, which perfectly matched the predictions of the Copernican model and utterly dismantled the Ptolemaic system. Galileo was a master of demonstration, translating abstract mathematical theories into visible, undeniable evidence. His advocacy for the heliocentric system, most famously in his dialogue concerning the 2 chief world systems, brought him into direct and dangerous conflict with the Catholic Church. His subsequent trial and house arrest stand as a powerful testament to the immense social and cultural upheaval caused by this new understanding of the cosmos. The blueprint was being rewritten in real time, and it was a profoundly disruptive process. Then came the synthesis, the mind that would weave these disparate threads into a single, universal fabric. Isaac Newton, building directly upon the work of Kepler and Galileo, presented a framework so powerful and complete that it would dominate physics for over 2 centuries. In his monumental Philosophiae Naturalis Principia Mathematica, published in 1687, Newton laid out his law of universal gravitation and his 3 laws of motion. The same force that caused an apple to fall from a tree in England, he proposed, also held the moon in orbit around the Earth and the Earth in orbit around the Sun. This was the ultimate unification, erasing the ancient Aristotelian distinction between the imperfect, changeable terrestrial realm and the perfect, immutable heavens. The entire cosmos, from a rolling pebble to a spinning galaxy, was now subject to the same set of physical laws. Newton famously acknowledged his debt to those who came before him, writing in a letter, "If I have seen further, it is by standing on the shoulders of giants." This humble statement captures the cumulative, collaborative essence of scientific discovery, each generation building upon the insights of the last to read the cosmic blueprint more clearly. The practical power of this new understanding was immediate and profound. Comets, long feared as omens of disaster and divine displeasure, were demystified. Newton's friend Edmund Halley used the new laws of gravity to calculate the orbit of a prominent comet, predicting its return in 76 years. When it reappeared right on schedule, it was no longer a terrifying portent but a celestial clockwork, a predictable testament to a lawful universe. This predictive power reached its zenith with the discovery of a new planet. In the 19th century, irregularities in the orbit of Uranus suggested the gravitational tug of an unseen world. Using only Newton's laws, mathematicians Urbain Le Verrier and John Couch Adams independently calculated the precise position of this hidden body. When astronomers pointed their telescopes to that exact spot in the sky, they found the planet Neptune. This was perhaps the ultimate triumph of the scientific revolution's worldview. The cosmos was so predictable that you could discover a new world with nothing more than a pen, paper, and the unwavering faith that the universe obeys mathematical rules. This era cemented a principle that is now the bedrock of all modern science. The universe operates according to a rational order that is accessible to human reason. We are not passive subjects of a capricious cosmos. We are active investigators, equipped with the tools of observation and mathematics to decode its deepest secrets. Now, imagine for a moment that you could chase a beam of light across the universe. What would you see? This is the very daydream that captivated a young patent clerk named Albert Einstein, a thought experiment that would ultimately shatter humanity's most basic assumptions about reality. While Newton gave us a universe of absolute space and absolute time, a rigid, unchanging stage upon which the cosmic drama played out, Einstein's mind saw something far more fluid and strange. His special theory of relativity, published in 1905, introduced 2 revolutionary principles that rewrote the cosmic blueprint in a whole new language. First, the laws of physics are the same for all observers moving at a constant speed. And second, the speed of light in a vacuum is always constant, no matter how fast you are moving towards or away from its source. These 2 simple-sounding ideas have breathtaking consequences. They tell us that space and time are not separate, independent entities. Instead, they are woven together into a single, 4-dimensional fabric called spacetime. And within this fabric, measurements of space and time are not absolute. They are relative to your state of motion. This means that if you were to travel through the cosmos at a significant fraction of the speed of light, time would literally slow down for you compared to someone who remained stationary. A clock on your spaceship would tick more slowly than a clock on Earth. Distances in the direction you were traveling would contract, becoming shorter from your perspective. The very concepts of now, then, here, and there lose their universal meaning. Einstein himself captured the profound weirdness of this when he reflected. The distinction between past, present, and future is only a stubbornly persistent illusion. There is no single, universal, present moment that everyone shares. Your now and my now can be different depending on how we are moving relative to each other. This relativistic view of time isn't just a mathematical abstraction. It has been experimentally verified countless times. Particle accelerators keep short-lived particles like muons alive much longer because they are traveling so fast that their internal clocks slow down. Even the precise atomic clocks on GPS satellites have to be constantly adjusted for these tiny relativistic time shifts. If they weren't, the entire global positioning system would drift out of accuracy by several miles each day. Our daily navigation depends on the fact that Einstein was right, but Einstein wasn't finished. For 10 more years, he grappled with a problem Newton's laws couldn't solve: how to fit gravity into this new relativistic picture. His monumental breakthrough, the general theory of relativity published in 1915, was even more radical. He proposed that gravity is not a mysterious force pulling objects together across empty space, as Newton had described. Instead, gravity is the result of the geometry of spacetime itself. Think of spacetime as a vast, taut, flexible rubber sheet. Now, place a heavy object like a bowling ball in the center of that sheet. The ball creates a deep depression, a curve in the fabric. If you then roll a smaller object like a marble near the bowling ball, the marble will follow the curved path around the indentation. It isn't being pulled by a force, it is simply following the straightest possible path, a geodesic through the warped landscape. In our universe, that bowling ball is a massive object like the Sun, and the marble is a planet like Earth. We aren't being pulled by the Sun. We are following a curved path in the spacetime dimple that the Sun creates. The true power of a scientific theory lies in its ability to make testable predictions, and general relativity made several spectacular ones. The most famous early test came during a total solar eclipse in 1919. Einstein predicted that the path of starlight passing very close to the Sun would be bent by the Sun's warping of spacetime. Sir Arthur Eddington led an expedition to photograph the stars around the eclipsed Sun, and the measurements confirmed Einstein's prediction exactly. Starlight was deflected by precisely the amount general relativity calculated, not by the smaller amount Newtonian physics would have suggested. This was front-page news around the world, catapulting Einstein to international fame and providing stunning confirmation that the fabric of the cosmos itself could be warped. Another key prediction was gravitational time dilation. Time runs slower in a stronger gravitational field. This has been confirmed by incredibly precise experiments, like comparing clocks at the top and bottom of a tall building. The clock at the bottom, experiencing slightly stronger gravity, ticks imperceptibly slower. With general relativity, Einstein gave us a cosmic blueprint that was dynamic, malleable, and geometric. Mass and energy tell spacetime how to curve, and the curvature of spacetime tells mass and energy how to move. This elegant dance explains phenomena that were completely mysterious before, such as the precise orbit of Mercury, which exhibits a tiny wobble that Newton's gravity couldn't account for. It opened the door to predicting the existence of incredible cosmic objects like black holes, where spacetime is curved so severely that not even light can escape, and gravitational waves, ripples in the fabric of spacetime itself caused by cataclysmic events like colliding black holes, which were directly detected a century after Einstein predicted them. Most profoundly, when applied to the universe as a whole, Einstein's equations naturally described a cosmos that could not be static. It had to be either expanding or contracting. This single mathematical insight planted the seed for the next great revolution in cosmology, forcing scientists to confront the ultimate question of origins. If the universe is dynamic and evolving, then it must have had a beginning. This redefinition of gravity, from a simple force to the curvature of the cosmic stage itself, leads us directly to the grandest beginning of all. So, if Einstein's equations described a universe in motion, where did that motion begin? Let's journey back not just millions, but over 13.8 billion years, to a moment before planets, before stars, before even atoms existed. The universe was compressed into an almost unimaginable state, a singularity of infinite density and temperature, a point of pure potential where the very concepts of space and time as we know them break down. Then, in an event that defies all human intuition, this singularity began to expand, not an explosion into a pre-existing space, but the rapid, fiery unfolding of space itself. This is the Big Bang, the foundational event that set the cosmic blueprint into motion, the moment we began reading the very first pages of the story of everything. The theory of the Big Bang didn't spring from a single mind but emerged as the only logical conclusion from a cascade of observational evidence. The first major clue came from an American astronomer working at the Mount Wilson Observatory in the 1920s. Edwin Hubble was studying faint, fuzzy patches of light then known as nebulae. He made a stunning discovery. These were not clouds of gas within our own Milky Way, but entire galaxies, island universes far beyond our own. Even more shocking was what he found when he analyzed their light. With very few exceptions, the light from these distant galaxies was shifted toward the red end of the spectrum. This redshift indicated that these galaxies were all rushing away from us, and the farther away a galaxy was, the faster it was receding. The entire cosmos was stretching like dots on an inflating balloon. The universe was not static, it was dynamically expanding. If you could run the film of the universe backwards, all that expanding space would contract, all the galaxies would rush together, implying a definite starting point in the finite past. This idea of a definite beginning had been proposed a few years earlier by a brilliant and prescient Belgian priest and physicist, Georges Lemaitre. He called his concept the primeval atom or the cosmic egg. Lemaitre envisioned a universe that began as a single, extremely dense and hot quantum of all existence, which then underwent a tremendous radioactive decay, initiating the expansion. That Hubble would later observe. For a time, many scientists, including Einstein himself, were skeptical, finding the notion of a beginning too theological or abrupt. But Lemaitre was a scientist first, and his hypothesis was grounded in the mathematics of general relativity. He saw what the equations were pointing toward, a cosmos with a birth date. The next and perhaps most definitive piece of evidence arrived by accident decades later. In 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were troubleshooting a persistent, faint hiss of microwave noise that was plaguing their sensitive horn antenna. It was present no matter where they pointed it, day or night, and they tried everything to eliminate it, even famously cleaning out pigeon droppings from the antenna, thinking that might be the source. The noise remained. Meanwhile, just a short distance away at Princeton University, a team led by Robert Dick was actively building a detector to find a predicted relic from the early universe, a faint, cool glow of radiation that would have been left over from the universe's hot, dense beginning. When the two groups connected, the realization was electrifying. Penzias and Wilson had not found an instrument defect. They had stumbled upon the afterglow of the Big Bang itself. This cosmic microwave background radiation, or CMB, is the oldest light we can see, a snapshot of the universe when it was just 380,000 years old, a time when it had cooled enough for protons and electrons to combine into neutral atoms, allowing light to travel freely through space for the first time. This discovery was the smoking gun that cemented the Big Bang theory as the standard model of cosmology. But what happened in those first few moments? The timeline of the early universe is a story of rapid transformation and decoupling. In the very first fraction of a second, a period known as cosmic inflation, the universe underwent an exponential growth spurt, expanding faster than the speed of light, smoothing it out and planting the seeds of all future structure. As it continued to expand and cool, the fundamental forces of nature, gravity, the strong nuclear force, the weak force, and electromagnetism separated out from their primordial unity. Within the first 3 minutes, during an era called Big Bang nucleosynthesis, the universe was still a searing hot soup of protons and neutrons. These particles began to fuse, forming the nuclei of the lightest elements, hydrogen, helium, and a tiny trace of lithium. The relative abundances of these elements, which we can still measure in the oldest regions of space, match the predictions of Big Bang nucleosynthesis with stunning precision. This is a direct chemical fossil from the universe's infancy. The evidence for this grand beginning is now overwhelming and comes from multiple, independent lines of inquiry. First, there is the primordial abundance of light elements. The universe is about 75% hydrogen and 25% helium by mass, with that tiny bit of lithium, and this is exactly what the calculations of Big Bang nucleosynthesis predict. Second, there is the stunning uniformity of the cosmic microwave background. When we map it across the entire sky, we find it is almost perfectly smooth, with temperature variations of only about 1 part in 100,000. This incredible uniformity is exactly what we would expect from a universe that underwent a period of rapid inflation. Finally, the very existence of the large-scale structure of the universe, the great cosmic web of galaxies and clusters, fits the model perfectly. The tiny quantum fluctuations imprinted in the CMB provided the gravitational seeds. Over billions of years, gravity amplified those slight overdensities, pulling in more and more matter, eventually forming the stars, galaxies, and the vast filamentary structures we observe today. This entire narrative, supported by such a robust body of evidence, inevitably leads us to some of the most profound and humbling questions we can ask. What, if anything, existed before the Big Bang, since time itself, according to our best physics, began with that event? The concept of before may have no meaning. Perhaps our universe is just one bubble in a vast, eternal multiverse, constantly budding off from a larger cosmic fabric. And is our universe unique? The fact that its physical laws and constants appear so exquisitely tuned to allow for the existence of galaxies, stars, planets, and life itself suggests that either we are the beneficiaries of an astonishingly lucky cosmic lottery, or that our universe is just one of many, each with its own distinct set of rules. The Big Bang theory gives us the framework to ask these questions, providing the critical starting point from which we can investigate the very parameters of reality. This foundational event, this first page of the cosmic blueprint, sets the stage for our next great inquiry. Why is this blueprint written with such precise, seemingly intentional numbers? Now, let's consider the universe itself as a kind of cosmic vault, a vast structure of immense complexity and potential. But this vault is locked, and to open it, to allow for galaxies, stars, planets, and ultimately, life requires a very specific, precise combination. This is the concept of cosmic fine-tuning, the startling discovery that the fundamental physical constants of our universe appear to be set to incredibly exact values, as if someone carefully dialed them in. These constants are not derived from any deeper theory. They are the bedrock numbers that plug into the equations of physics. They include the speed of light, c, which dictates the ultimate speed limit of causality, Planck's constant, h, which governs the bizarre quantum realm, and the gravitational constant, g, which sets the strength of gravity's pull. What is so breathtaking to physicists is that these numbers seem arbitrary. The universe could have, in principle, had different values. Yet, if any of them were altered by even a minuscule amount, a few percent in some cases, a fraction of a percent in others, the consequences would be catastrophic. The cosmic vault would remain forever locked, rendering a universe that is either sterile, unstable, or utterly incapable of supporting any form of complex structure, let alone conscious life. The physicist Paul Davies has eloquently captured the profound nature of this puzzle, stating, "The impression of design is overwhelming." He is referring to the Anthropic Principle, a logical but deeply intriguing idea that any universe we can possibly observe must, by necessity, have the properties that allow for the existence of observers. In other words, we find ourselves in a universe that is compatible with us because we are here to see it. But this doesn't solve the mystery, it simply reframes it. Why does a universe that allows for observers exist at all? The fine-tuning is so precise that it demands an explanation. Let's look at a few concrete examples to grasp the sheer improbability. Consider the strength of the strong nuclear force, the glue that holds atomic nuclei together. If this force were just a few percent weaker, the simple proton-proton bond would be impossible. Hydrogen would be the only element in existence. There would be no carbon, no oxygen, no chemistry, and no planets. The universe would be a boring, eternal sea of hydrogen gas. Conversely, if the strong force were slightly stronger, two protons could bind together directly, causing hydrogen to fuse into helium so rapidly in the early universe that stars would burn out in a cosmic flash, leaving no time for life to evolve. The window for a universe with a rich periodic table of elements is astonishingly narrow. The fine-tuning extends to the very fabric of spacetime and its expansion. Think back to the dark energy we discussed earlier, the mysterious force driving the accelerated expansion of the cosmos. The observed density of dark energy is incredibly small, a decimal point followed by about 120 zeros and then a 1. If this value were even slightly larger by that same tiny factor, the repulsive force would have been so powerful in the early universe that it would have blown everything apart before galaxies could ever form. There would be no stars, no planets, just a thin, ever-diluting cloud of isolated particles. On the other hand, if dark energy was zero or slightly negative, the universe would have collapsed back in on itself in a big crunch after only a few million years, again snuffing out any possibility for life. The initial conditions of the Big Bang itself were also fine-tuned. The rate of expansion in those first moments had to be exquisitely balanced. If it had been a little faster, matter would have flown apart too rapidly to coalesce into galaxies. A little slower, and gravity would have pulled everything back into a premature collapse. It seems we live in a universe that hit the cosmological jackpot on multiple, independent fronts. So, how does science respond to this overwhelming impression of design? There are several compelling, though speculative, lines of thought. One of the most prominent is the Multiverse Hypothesis. This idea suggests that our universe is just one bubble in a vast, perhaps infinite, cosmic foam of universes, each with its own random set of physical constants and laws. In this vast landscape, most universes are stillborn, too unstable or too empty to host anything interesting. But by sheer chance, in a tiny, tiny fraction of them, the numbers line up just right. We, of course, find ourselves in one of those rare, life-friendly universes. There is no designer, just a colossal cosmic lottery, and we hold the winning ticket. Another response is to question the very nature of these constants. Perhaps they are not truly free parameters, but are the inevitable outcome of a deeper, unified theory of physics that we have not yet discovered. In this view, the constants must have the values they do. There is no other possibility. The apparent fine-tuning is then just a consequence of a deeper, necessary logic built into reality, waiting to be uncovered by a future Einstein. Naturally, this discussion leads some to consider the possibility of a cosmic designer, an intelligence that set the dials to their life-permitting values. This is a philosophical and theological interpretation that has been debated for centuries. From a scientific perspective, however, this explanation is problematic because it simply pushes the question back a step: who designed the designer? Science seeks explanations within the framework of natural laws and testable hypotheses. The multiverse and the appeal to deeper physical laws remain within that investigative domain, even if they are currently difficult or impossible to test directly. The true answer might lie in a direction we haven't even conceived of yet. So, the next time you look up at the night sky, consider this profound puzzle. Why do these fundamental numbers have the specific values they do? Is our existence a fantastically unlikely accident in a boundless multiverse, the inevitable outcome of a hidden logic, or something else entirely? This incredible precision, this fine-tuning of the cosmos, doesn't just define the universe we live in. It defines the very possibility of us being here to ask the question. And as we ponder the delicate balance of these cosmic constants, we are naturally led to investigate the invisible actors that use this finely tuned stage, the mysterious dark matter and dark energy that sculpt the cosmos on its grandest scales. But for all the breathtaking beauty of the galaxies and nebulae we can see, we are only witnessing a tiny fraction of the cosmic reality. If you could put the entire universe on a scale, everything we have ever observed through every telescope, every star, every planet, every swirling cloud of cosmic dust would account for a mere 5% of the total weight. The remaining 95% is composed of two profound and invisible mysteries: dark matter and dark energy. These are the true architects of the cosmos, the hidden forces written into the blueprint that dictate its structure and its ultimate destiny. Yet they remain completely unseen and undetected by our eyes and our most advanced instruments. The universe we know and love is just the visible tip of a cosmic iceberg, with a vast, submerged bulk consisting of these enigmatic components. The story of dark matter begins not in the vast emptiness between galaxies, but within them. In the 1930s, a brilliant and tenacious Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive gathering of thousands of galaxies. By measuring the velocities of galaxies orbiting the cluster's center, he made a shocking discovery: they were moving far too quickly. The combined gravitational pull of all the visible stars and gas in the cluster was utterly insufficient to hold these speeding galaxies together. The cluster should have flown apart eons ago. Zwicky concluded that there must be some form of unseen matter, which he called dunkel materie, or dark matter, providing the extra gravitational glue. For decades, his idea was largely ignored, considered a fringe curiosity. But the evidence became undeniable thanks to the pioneering work of astronomer Vera Rubin in the 1970s. Rubin was meticulously mapping the rotation curves of spiral galaxies, that is, how fast stars and gas orbit the galactic center at different distances. According to Newton's laws, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly, just as Pluto orbits the Sun more slowly than Earth. But Rubin found something completely different. The stars on the outskirts of galaxies were orbiting just as fast as those near the center. It was as if the entire galaxy was embedded within a giant, massive, invisible halo of something that was providing extra gravity, preventing these high-speed stars from being flung off into intergalactic space. Vera Rubin's data provided the most compelling evidence, yet that dark matter was not a fluke. It was a fundamental component of every galaxy, including our own Milky Way. As she later reflected, the world of science is enriched by the discovery of a mystery, not by its solution, and dark matter was a mystery of the highest order. While dark matter acts as the cosmic scaffolding, pulling matter together to build the large-scale structures of the universe, dark energy is its bizarre counterpoint, a repulsive force that is doing the exact opposite, pushing the cosmos apart at an ever-increasing rate. This stunning discovery was made in the late 1990s by two independent teams of astronomers who were studying distant supernovae, the colossal explosions of dying stars. They used these supernovae as standard candles to measure cosmic distances, expecting to find that the expansion of the universe was slowing down over time due to the collective gravitational pull of all the matter within it. To their astonishment, they found the reverse. The most distant supernovae were fainter than expected, meaning they were farther away than they should have been if the expansion were decelerating. The inescapable conclusion was that the expansion of the universe is not slowing down, it is accelerating. Something was overpowering gravity on the largest scales, a mysterious pressure embedded in the fabric of space itself. This something was dubbed dark energy. It is now considered the dominant component of the universe, making up about 68% of its total energy budget. As astronomer Saul Perlmutter, a leader of one of the teams, later said, "It feels like being a child who has been exploring a house and suddenly discovers a door that leads to a wing of the house they never knew existed." We had just found a door to a completely new and unexpected part of the cosmic blueprint. The quest to identify the true nature of these invisible giants is one of the most thrilling frontiers in modern physics. For dark matter, the leading hypothesis is that it consists of as yet undiscovered particles that do not interact with light or ordinary matter very often, but whose collective gravity is immense. Scientists are hunting for these hypothetical particles, known as WIMP or weakly interacting massive particles, through three main methods. The first is direct detection, where incredibly sensitive detectors are placed deep underground in old mines or tunnels, shielded from cosmic rays, waiting for the rare occasion a dark matter particle might bump into an atomic nucleus and create a tiny, measurable signal. The second is indirect detection, using powerful telescopes to scan the skies for the gamma rays or other radiation that could be produced if dark matter particles were to collide and annihilate each other in dense regions like the centers of galaxies. The third method is to create them, using colossal particle colliders like the Large Hadron Collider at CERN, smashing ordinary particles together at nearly the speed of light in the hope of producing dark matter particles in the resulting energy burst. Alongside these particle searches, astronomers also map the distribution of dark matter through its gravitational effects, using a phenomenon called gravitational lensing. The immense gravity of a dark matter halo can bend and distort the light from galaxies behind it, acting like a cosmic magnifying glass. By studying these distortions, we can literally trace the outline of the invisible dark matter scaffolding that holds the visible universe in place. Dark energy, however, presents an even deeper puzzle. Is it a constant energy density of the vacuum of space itself, a concept Einstein once called the cosmological constant? Or is it a dynamic field that changes over time, dubbed quintessence? To answer this, astronomers are undertaking massive sky surveys, mapping billions of galaxies to measure the expansion history of the universe with extreme precision, trying to determine if the strength of dark energy has remained constant or has evolved over cosmic time. The nature of dark energy is inextricably linked to the ultimate fate of everything, determining whether the cosmos will end in a frozen emptiness, a dramatic tear, or something else entirely. The existence of dark matter and dark energy is a humbling reminder that our current understanding of physics is incomplete. The standard model of particle physics, which brilliantly explains the world of quarks and electrons, has no place for a dark matter particle. And our theory of gravity, Einstein's general relativity, while exquisitely accurate, struggles to reconcile with the apparent existence of a repulsive dark energy. Some physicists even speculate that on the largest scales, our understanding of gravity itself may need to be modified. These invisible forces are not just minor curiosities. They are fundamental flaws in our map of reality, glaring signposts pointing toward a deeper, more complete theory that lies just beyond our current grasp. They challenge the very core of the cosmic blueprint we thought we were decoding, forcing us to admit that the most dominant players in the cosmic story are still complete unknowns. This exploration of the universe's hidden architecture, governed by dark matter's pull and dark energy's push, leads us directly to the magnificent web-like structure that these forces have sculpted across the cosmos. So, if dark matter provides the invisible scaffolding and dark energy dictates the pace of expansion, what is the grand structure that they have built together? The answer is one of the most breathtaking discoveries in modern cosmology, the cosmic web. Forget the old idea of galaxies scattered randomly through space like lonely islands. Instead, picture the universe on its largest scale as a colossal, three-dimensional spiderweb, a vast architecture of breathtaking complexity and beauty. This web is composed of brilliant, dense knots where thousands of galaxies swarm together in massive clusters. These clusters are connected by long, delicate filaments and great sheet-like walls made of galaxies and dark matter, tracing out the web's strands. And between these structures lie the cosmic voids, immense, nearly empty deserts of space that can stretch for hundreds of millions of light years, containing almost no galaxies at all. This is not a static sculpture. It is a dynamic, evolving network, and our own Milky Way galaxy is embedded within one of its filaments, a single thread in this universe-spanning tapestry. Mapping this colossal structure has been one of the great scientific endeavors of our time, and it has been made possible by ambitious surveys that have methodically charted the positions of millions of galaxies. The most famous of these is the Sloan Digital Sky Survey, which for years used a dedicated telescope to take detailed images and spectra of the night sky. By precisely measuring the distances to vast numbers of galaxies, astronomers could then plot them in 3 dimensions. When they did, the result was staggering. The galaxies were not randomly distributed. They formed a clear, foam-like pattern, a cosmic sponge where the galaxies make up the walls and filaments, and the voids are the empty bubbles within. This vast pattern is the direct descendant of the tiny, quantum fluctuations that were imprinted on the universe during the first split second of inflation. Those microscopic ripples in the density of the primordial universe were the seeds from which the entire cosmic web would eventually grow, as cosmologist J. Richard Gott so eloquently described it. Our universe has a sponge-like topology, a specific kind of geometry where one connected region, the dense web of galaxies, wins its way through another connected region, the vast emptiness of the void. It is a single, continuous structure filling all of space. The story of how this web formed is a story of gravity's patient, relentless work over billions of years. This process is known as hierarchical structure formation. It begins with the slight overdensities, the regions that were just a tiny bit denser than average, that were frozen into the cosmos after inflation. As the universe expanded and cooled, the relentless pull of gravity, dominated by dark matter, began to act. Those slightly denser patches had a little extra gravity, so they pulled in more dark matter and gas from their surroundings. This made them even denser, which increased their gravitational pull, drawing in even more matter. Over cosmic time, small clumps of dark matter, known as halos, formed first. Then ordinary matter, in the form of hydrogen and helium gas, was pulled into these dark matter halos. Inside these halos, the gas could cool, condense, and eventually fragment to form the first stars and galaxies. But it didn't stop there. Through a relentless cosmic dance of attraction and collision, these small proto-galaxies then began to merge, building up larger and larger galaxies. Groups of galaxies then fell together to form clusters, and clusters themselves gathered into even larger structures called superclusters, all of it tracing out the grand pattern of the filaments and nodes of the web. Let's take a closer look at the key features of this cosmic architecture. At the densest intersections of the web's filaments, you find galaxy clusters. These are the metropolises of the universe, containing hundreds or even thousands of galaxies, all bound together by gravity, swimming in a searing hot cloud of gas that glows in X-rays. Our own Milky Way is part of a smaller group of galaxies called the Local Group, which is itself on the outskirts of a much larger cluster known as the Virgo cluster. Zooming out further, clusters themselves group together into superclusters, which are not gravitationally bound structures but rather vast, flowing rivers of galaxies moving along the filaments of the web under the influence of even larger-scale gravitational forces. One of the most dramatic early discoveries of this large-scale structure was the Great Wall, sometimes called the Sloan Great Wall, a colossal filament of galaxies over 1.3 billion light-years long, one of the largest known structures in the entire observable universe. It's a stunning reminder of the sheer scale of the patterns we are discussing. A beautiful and humbling example of our place within this web is the Laniakea supercluster. For a long time, astronomers thought our local supercluster was centered on the Virgo cluster, but more recent mapping of galaxy motions has revealed a larger truth. Laniakea, which means immeasurable heaven in Hawaiian, is our true cosmic home address. It's a vast collection of over 100,000 galaxies, including our own Milky Way, all flowing together under the gravitational influence of a central point known as the Great Attractor. This supercluster spans about 520 million light-years, and within its flowing filaments, our galaxy is just one of many, moving on a slow, billion-year journey along a cosmic highway. Understanding Laniakea gives us a profound sense of our location in the universe. We are not in a special central place, but reside in the suburban outskirts of an immense continent of galaxies. This magnificent cosmic web, a direct result of the initial conditions of the Big Bang and the relentless pull of gravity, tells us a deep story about the universe's past. By studying its pattern, the thickness of its filaments, the sizes of its voids, the distribution of its clusters, cosmologists can work backwards, testing their models of dark matter and dark energy against the observed structure. It acts as a fossil record, preserving the imprint of the universe's earliest moments, but it also hints at the future. As dark energy continues to accelerate the expansion of the universe, the growth of this web will eventually slow and then halt. The flow of galaxies along the filaments will cease, and new mergers will become impossible as the distances between structures become too vast to cross. The cosmic web, this evolving, dynamic network, will slowly freeze into place, its brilliant knots and threads becoming isolated islands in an ever-darkening and expanding sea. This grand structure, born from the tiniest of quantum seeds, sets the stage for the drama that unfolds within it, the dramatic life and death of the very stars and galaxies that light up its filaments, forging the elements that make our own existence possible. Deep within the glowing tendrils of a stellar nursery, a cosmic drama begins that will ultimately forge the very building blocks of our existence. These vast clouds of gas and dust called nebulae are the cradles of stars. Under the relentless pull of gravity, a dense knot within a nebula begins to collapse, spinning faster and heating up until its core becomes a raging thermonuclear furnace. This is the birth of a star, and its life cycle, a spectacular journey from brilliant light to violent death, is the universe's primary mechanism for creating the rich diversity of elements essential for planets and life. The energy and processes that play out within a star's heart are a direct expression of the cosmic blueprint, turning the simple, primordial elements from the Big Bang into the complex chemistry that defines our world. It is within these celestial forges that the universe learns to write its own story in atoms. The true nature of these stellar furnaces was unlocked by a revolutionary mind, astrophysicist Cecilia Payne-Gaposchkin. In 1925, in her groundbreaking doctoral thesis, she made the then shocking assertion that stars are predominantly composed of hydrogen and helium, with hydrogen being the most abundant element by far. This overturned the long-held belief that stars had a similar composition to Earth. Payne-Gaposchkin had correctly interpreted the patterns in stellar spectra, the unique fingerprints of light that reveal a star's chemical makeup. Her work was initially dismissed by authorities who found her conclusion too radical, but she was ultimately proven right. Her discovery was a monumental leap in decoding the cosmic blueprint, revealing that the universe, in its vastness, operates on a simplicity and consistency that we can understand. She showed us that the brilliant lights in our sky are fundamentally massive balls of the two lightest elements, setting the stage for understanding how all the other elements come to be. The long, stable adult life of a star like our Sun is spent in a phase known as the main sequence. For billions of years, a delicate balance is maintained between the outward pressure from nuclear fusion in its core and the inward crush of its own gravity. In this core, where temperatures reach millions of degrees, hydrogen nuclei are forced together in a process called fusion, creating helium and releasing a tremendous amount of energy in the form of light and heat. This is the star's power plant, and it is this steady, ongoing fusion reaction that makes a star shine. Our Sun has been in this stable hydrogen-burning phase for about 4.6 billion years and has enough fuel to continue for another 5 billion or so. This period of constancy is crucial, as it provides the stable energy source that, for at least one planet orbiting it, has allowed for the development and sustenance of life. The main sequence is the universe's way of creating long-lasting, reliable engines of creation. However, even the most stable star cannot burn hydrogen forever. When a star like the Sun finally exhausts the hydrogen fuel in its core, the balance of power shifts dramatically. With fusion ceasing in the core, the outward pressure drops and gravity begins to win, causing the core to contract and heat up even further. This new, intense heat ignites a shell of hydrogen fusion around the inert helium core. The energy released from this shell pushes the star's outer layers outward with tremendous force, causing the star to balloon in size to hundreds of times its original diameter. It becomes a red giant. Meanwhile, the core, now composed of helium, continues to collapse under gravity until it becomes hot and dense enough to begin a new chapter of fusion, helium burning. In a process known as the triple alpha process, 3 helium nuclei are fused together to form one carbon nucleus. This is a pivotal moment in cosmic chemistry. For the first time, an element heavier than helium is being forged in significant quantities. In more massive stars, this process continues, with the carbon core itself eventually igniting to produce oxygen, and so on, building elements like neon and magnesium in concentric shells like the layers of a cosmic onion. The fate of a star and the ultimate richness of the elements it produces is determined by its initial mass. A relatively low-mass star like our Sun will never achieve the core temperatures needed to fuse carbon into heavier elements. After its red giant phase, it will gently shed its outer layers into space, creating a beautiful, glowing shell of gas called a planetary nebula. The exposed, hot core will then cool down over eons into a dense Earth-sized ember known as a white dwarf. The material from the expelled outer layers, now enriched with newly created carbon and oxygen, will drift back into the interstellar medium, becoming raw material for future generations of stars and planets. This is the Sun's destined contribution to the cosmic recycling program, a gentle seeding of the galaxy with the essential elements for organic chemistry. But for the true heavy element factories, we must look to the most massive stars, those born with more than about 8 times the mass of our Sun. These stellar giants live fast and die young, burning through their nuclear fuel in only a few million years. Their lives are a frantic race against gravity, fusing elements in their cores all the way up to iron. This is the end of the line for fusion. Fusing iron into heavier elements does not release energy, it consumes it. With its energy source cut off, the star's core can no longer support itself against its own immense weight. In less than a second, the core catastrophically collapses, triggering a titanic rebound explosion known as a core collapse supernova. The blast is so incredibly energetic that it provides the extreme conditions necessary for a final, frantic burst of nucleosynthesis. In this maelstrom of neutrons and energy, elements heavier than iron are created through rapid neutron capture, the so-called R process. This is how the universe forges a vast array of critical elements, including the silver and gold in your jewelry, the uranium used in nuclear power, and the iodine essential for your thyroid. The supernova then blasts this newly synthesized material, along with all the other elements the star created in its life, far out into the galaxy, scattering the seeds for rocky planets and ultimately life. Consider the specific legacy of our own Sun, a star we know intimately. In about 5 billion years, it will enter its red giant phase, swelling to such an immense size that it will engulf the orbits of Mercury and Venus and likely render Earth uninhabitable. During this turbulent phase, it will create carbon and oxygen through helium fusion. Then, in its final act, it will expel its outer layers, creating a magnificent planetary nebula that will glow for thousands of years. The carbon atoms forged in its core will be flung out into space, perhaps one day to become part of a carbon-based molecule on a new world orbiting a new star. The oxygen it releases will mingle with the interstellar gas, waiting to become part of the water for a future ocean or the air for a future atmosphere. Our Sun, a seemingly ordinary star, will thus become a direct contributor to the chemical enrichment of our galactic neighborhood, its death ensuring the birth of future possibilities. This grand cycle of stellar birth, life, and death is the most intimate connection we have to the cosmic blueprint. Every single atom in your body that is not hydrogen, which dates directly back to the Big Bang, was created in the heart of a long-dead star. The oxygen you breathe, the carbon that forms the backbone of your DNA, the nitrogen in your amino acids, and the calcium in your bones were all synthesized in a stellar furnace and then scattered across the galaxy by a supernova explosion billions of years ago. You are literally made of stardust, the universe's recycled and repurposed material. This is not a metaphor, it is a physical fact. When we trace the lineage of the elements that compose our world and ourselves, we find that we are not just inhabitants of the cosmos, but an active part of its ongoing chemical evolution. The same physical laws that govern the spin of galaxies and the life cycle of stars are written into our very beings. This profound connection, forged in the hearts of stars and scattered by their explosive deaths, provides the essential raw materials for the next stage of cosmic evolution, the formation of planetary systems, and the emergence of environments where life might take root. So, within this cosmic recycling program of stellar life and death, the stage is now set for the next, even more delicate act, the construction of stable environments where the chemistry of life might begin. We have moved from the forging of elements in stellar furnaces to their assembly into complex worlds. For centuries, our view of planets was profoundly limited, confined to the 8, now 9, that orbit our own sun. But in the last few decades, our vision has exploded outward. We now know that planets are not the exception, they are the cosmic rule. Our Milky Way galaxy alone is likely home to hundreds of billions of them, a staggering diversity of worlds that defy our earlier imagination. We have discovered hot Jupiters, gas giants that orbit blisteringly close to their stars, completing a year in just a few Earth days. We have found super-Earths, rocky planets larger than our own but smaller than Neptune, a type of world that doesn't even exist in our own solar system. And most tantalizingly, we have begun to find rocky planets orbiting at just the right distance from their stars to potentially have liquid water on their surfaces, worlds that sit within what astronomers call the habitable zone. This is the orbital region around a star where the temperature is just right, not too hot for water to boil away, and not too cold for it to permanently freeze. It's often nicknamed the Goldilocks zone, and finding planets within it is our first major clue in the search for life beyond Earth. But a planet simply being in the habitable zone is just the opening line of a much more complex story. Habitability is not a simple on-off switch. It is a delicate and sustained balancing act involving a whole suite of critical factors. Liquid water is the non-negotiable starting point, the universal solvent that facilitates the chemical reactions essential for life as we know it. But for that water to remain liquid for billions of years, a planet needs a stable, nearly circular orbit. A wildly eccentric orbit would cause extreme temperature swings, periodically flash freezing, and then boiling its oceans, making it very difficult for life to gain a foothold and evolve. A protective atmosphere is another absolute necessity. It acts as an insulating blanket, regulating surface temperature and shielding the planet's surface from the deadly barrage of high-energy radiation from its star and from cosmic rays. Our own atmosphere, for instance, protects us from the sun's ultraviolet radiation and burns up most small asteroids before they can impact the surface. Perhaps most crucially, a planet needs a strong, global magnetic field, generated by the churning of a molten metal core. This magnetic field acts as an invisible force field, deflecting the stellar wind, a constant stream of charged particles pouring from the star. Without this magnetic shield, a planet's atmosphere can be slowly but surely stripped away over geological time, as we believe happened to Mars, which lost its global magnetic field and subsequently saw its thick atmosphere and surface water vanish into space. To make sense of the immense number of possibilities, astronomers have long sought a way to quantify our chances of finding other intelligent life. This effort was famously crystallized in the 1960s by astrophysicist Frank Drake, who formulated the Drake equation. It is not a single solution, but a structured framework for thinking about the problem. The equation multiplies a series of factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually appears, the fraction where life becomes intelligent, the fraction that develops technology to communicate, and finally, the length of time such civilizations release detectable signals into space. The power of the Drake equation lies in its ability to break down a profound, almost philosophical question into a series of smaller, more researchable problems. As Frank Drake himself acknowledged, the equation is highly speculative, especially its later terms. He noted that it is a way of organizing our ignorance, forcing us to identify which factors we understand the least. With every new exoplanet discovery, we get better estimates for the early terms, but the later ones concerning the origin and longevity of life and intelligence remain profound mysteries. The equation gives us a humbling perspective. Even if the universe is teeming with planets, the emergence of a civilization that can look back at the cosmos and ask these same questions might be an incredibly rare and precious phenomenon. The very process of building these diverse planetary systems is itself a direct expression of the cosmic blueprint, governed by the laws of physics playing out in the swirling disks of gas and dust that surround newborn stars. These protoplanetary disks are the cradles of planets. As a star forms at the center, the remaining material in the disk begins to cool. Close to the young, hot star, only materials with high melting points, metals and rocky minerals, can remain solid. These particles of dust and ice begin to collide and stick together in a process called accretion, slowly growing from tiny grains into pebbles, then into mountain-sized planetesimals, and finally, through further collisions and gravitational attraction, into full-fledged rocky planets. This is why, in our own solar system, we find the dense terrestrial worlds Mercury, Venus, Earth, and Mars. In the inner region, farther out beyond what's called the frost line, temperatures are low enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. Out here, planetary cores can grow much larger and faster because ice is more abundant than metal and rock. Once these cores reach a critical mass, about 10 times the mass of Earth, their gravity becomes strong enough to rapidly pull in and hold onto the vast reservoirs of hydrogen and helium gas that make up the bulk of the protoplanetary disk. This is how the gas giants like Jupiter and Saturn are born, acting as gravitational anchor points for their systems. When we look at specific examples, the incredible precision required for habitability comes into sharp focus. One of the most fascinating systems discovered is TRAPPIST-1, a cool, dim red dwarf star located about 40 light-years away. What makes this system so remarkable is that it hosts not just one, but 7 Earth-sized planets, and at least 3 of them orbit squarely within the star's habitable zone. This is a stunning demonstration of planetary packing, a miniature solar system that offers multiple chances for life to arise around a single star. However, the very nature of the star itself presents a host of challenges. Red dwarfs are far smaller and cooler than our Sun, which means their habitable zone is much closer in. The TRAPPIST-1 planets orbit so close to their star that they are likely tidally locked, meaning one side permanently faces the star in eternal daylight, while the other is locked in perpetual night. This could create extreme temperature differences, though a thick atmosphere might be able to distribute heat around the planet. More concerning, red dwarfs are often prone to violent flares, eruptions that blast out intense ultraviolet and X-ray radiation, which could scour the surfaces of these nearby planets and strip away their atmospheres. The TRAPPIST-1 system is a perfect natural laboratory, a place where we can test our theories about what it truly takes for a planet to move from being merely Earth-sized to being genuinely Earth-like, a world that can not only host liquid water, but also sustain it over billions of years of cosmic history. Beyond location and atmosphere, a planet's internal geology plays a surprisingly vital role in its long-term habitability. The composition of a planet's interior, for instance, dictates whether it can generate and maintain that crucial magnetic field. A planet that cools and solidifies completely, like Mercury or our Moon, becomes geologically dead, losing its protective magnetic dynamo. The presence of plate tectonics on Earth is another critical, yet often overlooked factor. The slow, grinding movement of continental plates acts as a global planetary thermostat. Through the carbon silicate cycle, plate tectonics helps to regulate the amount of carbon dioxide in the atmosphere, pulling it down and locking it away in rocks before eventually releasing it back through volcanism. This long-term feedback loop has prevented Earth from succumbing to a runaway greenhouse effect like Venus or freezing solid like Mars. It also drives the recycling of minerals and nutrients, which may have been essential for the origin and evolution of life. A planet without this geological recycling might find its climate far more unstable over cosmic timescales. All of this evidence and reasoning leads us to one of the most profound and haunting questions in all of science. Is life a common, almost inevitable outcome of cosmic evolution, or is it a fantastically rare fluke? On one hand, the ingredients for life, water, organic molecules, and energy sources appear to be ubiquitous throughout the cosmos. We find complex organic molecules in interstellar clouds, on asteroids, and comets. The universe seems to be predisposed to the chemistry of life. If the conditions are right, perhaps life emerges as a natural property of matter, an almost automatic process on any suitable world. This is the principle of planetary mediocrity, the idea that there is nothing particularly special about Earth, and that given enough time and enough planets, life will inevitably spark into existence elsewhere. On the other hand, when we consider the incredible chain of events that led to our own existence, a stable star, a Jupiter-like planet to deflect comets, a large moon to stabilize our axial tilt, active plate tectonics, a magnetic field, and a series of evolutionary bottlenecks that intelligent life somehow navigated, it can seem like we are the beneficiaries of an almost impossibly long series. Lucky breaks. This is the core of the rare Earth hypothesis, which argues that while simple microbial life might be common, the emergence of complex, animal-level life and technological intelligence requires such a specific and fragile set of circumstances that it may be exceedingly rare in the galaxy. We simply do not yet have the data to answer this question. Every new exoplanet discovered is another data point, another piece of the puzzle. But this intense focus on the specific conditions that allow for life inevitably draws our gaze back in time, to the very beginning of everything, to the moment when the initial conditions for all of this cosmic potential were first established. But to build a universe as vast and structured as our own, you need more than just a hot, dense beginning. The standard Big Bang model, for all its successes, left cosmologists with some deeply puzzling questions about the initial state of the cosmos. Why does the universe appear so incredibly uniform in all directions? And why is the geometry of space so perfectly balanced between expansion and collapse? The answers to these riddles lie in an even more dramatic chapter of the cosmic story, a fleeting but transformative event that occurred when the universe was less than a trillionth of a trillionth of a trillionth of a second old. This is the theory of cosmic inflation, a concept that proposes a stunning growth spurt for the infant cosmos, a period of exponential expansion that stretched the very fabric of spacetime itself, ironing out its wrinkles and setting the precise initial conditions for everything that was to follow. The puzzles that inflation was designed to solve are known as the horizon problem and the flatness problem. The horizon problem is a question of connectivity. When we look at the cosmic microwave background radiation coming from opposite sides of the sky, we find that its temperature is uniform to an astonishing degree. It's the same to within 1 part in 100,000. But according to the standard Big Bang model, these two regions on the sky were never in causal contact with each other. There hadn't been enough time since the beginning of the universe for light or any other influence to travel between them and equalize their temperature. It's as if you walked into a vast room and found millions of people who had never met or communicated, all wearing exactly the same outfit, right down to the tiniest detail. How could such perfect coordination have occurred without any prior communication? Then there is the flatness problem. The geometry of our universe appears to be incredibly flat, meaning that the parallel lines of spacetime neither converge nor diverge over cosmic distances. For this to be true today, the density of the universe in its first moments had to be fine-tuned to a precision of 1 part in 10 to the power of 60. That's a number so unimaginably precise it's like balancing a pencil on its tip for billions of years. The slightest deviation would have resulted in a universe that either collapsed back on itself almost immediately or expanded so rapidly that no galaxies could ever form. The universe we see seems to have started with impossibly perfect and seemingly impossible initial conditions. The brilliant insight that resolved these profound issues came from physicist Alan Guth in the early 1980s. He proposed that the very young universe underwent a brief, fantastically rapid period of exponential expansion, driven by a peculiar state of energy inherent to empty space itself. Guth realized that this concept of an inflationary epoch could elegantly solve both the horizon and flatness problems in one stroke. He famously described inflation as the ultimate free lunch, because a tiny, subatomic speck of the early universe could be stretched to a size larger than our entire observable universe today, all from the repulsive gravity of this inflationary energy. How does this work? Imagine the entire observable universe starting as a region small enough for light to cross it instantly, allowing it to become perfectly smooth and uniform, like a single, well-mixed droplet. Then inflation happened. In a time interval shorter than a blink of an eye, that tiny, smooth region was stretched by a factor of at least 10 to the 26, and possibly much, much more. This incredible stretching pulled regions that were once in causal contact far apart, creating the apparent horizon problem, while simultaneously explaining why they looked the same. They were the same before inflation blew them up to cosmic scales. As for the flatness problem, inflating the universe is like taking a tiny, crumpled piece of paper and stretching it to the size of a continent. No matter how wrinkled or curved that original scrap was on the scale of the continent, its surface would appear perfectly flat. Inflation did exactly that to the geometry of spacetime, flattening it to the incredible degree we observe today. The most compelling evidence for this incredible growth spurt comes from the detailed maps of the cosmic microwave background. While the CMB is remarkably uniform, it is not perfectly so. It contains tiny, minuscule variations in temperature, anisotropies that are about 1 part in 100,000. These tiny ripples are the fossilized imprint of the quantum fluctuations that were present in the inflationary energy field, often called the inflaton field. Here's how it worked. According to quantum mechanics, empty space is not truly empty. It is a seething foam of virtual particles popping in and out of existence. During the inflationary epoch, the same quantum jitters were affecting the inflaton field. Tiny, random fluctuations in its energy density were happening on the smallest of scales. Then inflation struck. Those microscopic quantum wrinkles were stretched to astronomical sizes, frozen into the fabric of spacetime as slight variations in density. Regions that were slightly denser had a little more gravity, and over billions of years, that extra gravitational pull attracted more matter, eventually growing into the galaxies, clusters, and the vast cosmic web we see today. The specific pattern of these temperature variations in the CMB, which has been measured with exquisite precision by satellites like Planck, matches the predictions of the inflationary model with stunning accuracy. It tells us that the largest structures in the universe, the great walls and filaments of galaxies, have their origin in the tiniest, most fundamental quantum vibrations, magnified to cosmic proportions by inflation. A helpful way to visualize this is to think of an ordinary balloon, completely deflated and covered in tiny, random wrinkles and bumps. Now, imagine blowing up that balloon to an immense size, perhaps as large as a city. As the balloon expands, every single tiny wrinkle on its surface is also stretched. A microscopic imperfection becomes a large-scale ridge or valley. The overall surface of the balloon becomes much smoother and flatter from your perspective, but the pattern of larger-scale variations you now see is a direct, magnified map of the original tiny imperfections. This is precisely what inflation did to our universe. The tiny quantum wrinkles in the primordial inflated field were the microscopic bumps on the uninflated balloon. The rapid, exponential expansion of inflation was the act of blowing it up to a cosmic scale, and the pattern of hot and cold spots in the cosmic microwave background, along with the distribution of galaxies in the sky, is the resulting large-scale pattern of ridges and valleys we observe today. Our entire cosmic history, it seems, was written in a quantum script and then inflated to a scale we can read. Beyond the CMB, inflation makes another spectacular prediction. It should have generated a background of primordial gravitational waves. The violent, rapid stretching of spacetime during inflation would have created ripples in the very fabric of the cosmos, much like a boat speeding across a lake creates a wake in the water. These gravitational waves would have left a distinct swirling pattern known as B-mode polarization, imprinted on the light of the cosmic microwave background. Detecting this signal is one of the holy grails of modern cosmology, as it would provide direct, smoking gun evidence for the inflationary epoch and could even tell us the energy scale at which it occurred. While a tentative detection announced by the BICEP 2 telescope in 2014 was later found to be mostly due to interstellar dust, the hunt continues with ever more sensitive experiments. Finding these primordial waves would be like listening to the echo of the Big Bang itself, a direct vibration from the moment the cosmic blueprint was stretched to its current form. While inflation is an incredibly powerful and successful theory, it is not without its own deep mysteries. The most pressing question is, what actually triggered this period of hyper-expansion and what caused it to stop? The inflated field is a theoretical construct. We have no direct evidence for the specific particle or field that drove it. The mechanism that eventually caused the inflated field to decay, a process called reheating, is what ended the inflationary epoch and flooded the universe with the hot, dense soup of particles that marked the traditional beginning of the Big Bang. Furthermore, once you have a mechanism that can inflate one region of space, it naturally suggests the possibility of eternal inflation, a never-ending process where new, bubble universes are constantly budding off from an ever-inflating background, creating a vast multiverse where each bubble might have different physical laws and constants. This idea pushes the boundaries of testable science, but it emerges naturally from the mathematics of inflation. So, while inflation beautifully explains the large-scale features of our universe and connects the quantum world to the cosmic, it also opens a door to a reality far stranger and more vast than we had previously imagined. It set the flawless stage for the universe we observe, providing the smoothness, the flatness, and the seeds for all structure. Yet it leaves us wondering about the ultimate nature of the force that set it in motion. This incredible bridge between the largest scales and the very smallest brings us directly to the frontier where gravity and quantum mechanics must finally meet, to the very origin of space-time and the quantum genesis of the cosmos. Now, let's shrink our perspective down from the vast, inflated cosmos to the very smallest conceivable size, to a realm where the familiar rules of gravity and space-time break down completely. We are entering the domain of quantum cosmology, where we attempt to read the cosmic blueprint not on the grand scale of galaxies, but at the fundamental level where the universe itself may have been born from a quantum event. To understand this, we must journey to the Planck epoch, the very first instant after the Big Bang, a time so inconceivably brief it is a decimal point followed by 43 zeros and then a 1. At this scale, the universe was smaller than a single subatomic particle, and the energy was so immense that the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single superforce. In this seething, chaotic foam of pure potential, the concepts of space and time as we know them cease to have any meaning. This is the final frontier of our cosmic detective story, where we try to apply the bizarre rules of quantum mechanics not to particles within the universe, but to the entire universe itself, treating the cosmos as a single quantum object. When we apply the principles of quantum mechanics to the whole cosmos, we encounter some of the most mind-bending ideas in all of physics. In the quantum world, a particle like an electron doesn't have a definite position or path until it is measured. Instead, it exists in a haze of probabilities described by a mathematical entity called the wave function. Quantum cosmology takes this a step further, proposing that the entire universe has its own wave function. This wave function of the universe encapsulates all the possible histories, geometries, and even physical laws that our cosmos could have had. It describes a superposition of universes, one that is flat, one that is curved, one where the strong nuclear force is stronger, and so on. The universe we actually observe is just one possibility that somehow became actualized out of an infinite sea of potential. This leads to a profound question. What does it mean for the entire universe to be measured? There is no external observer outside of spacetime to look at it and collapse its wave function into a single reality. This is a monumental extension of the famous quantum measurement problem, forcing us to ask whether the act of our own observation from within the universe plays a role in defining the reality we see around us. One of the most ambitious and elegant attempts to solve this puzzle is the no-boundary proposal, developed by Stephen Hawking and James Hartle. This theory offers a breathtakingly radical answer to the question of what happened before the Big Bang. Hawking and Hartle proposed that if we could rewind time back to the very beginning, we would find that time itself loses its distinctive character. In their model, imaginary time, a mathematical concept, becomes indistinguishable from space. Picture the beginning of the universe not as a sharp, singular point of infinite density, but as a smooth, rounded-off geometry, much like the North Pole on a globe. If you ask what is north of the North Pole, the question has no meaning. There is no boundary. Similarly, the no-boundary proposal suggests the universe has no initial boundary in time. There was no before the Big Bang because time, as we understand it, did not exist. As Hawking famously put it, this means asking what happened before the Big Bang is like asking what is north of the North Pole. It is a question that stems from a misunderstanding of the nature of time at those extreme conditions. In this view, the universe would not be created or ignited. It would simply be in a self-contained, finite yet unbounded state, much like the surface of the Earth. This quantum perspective doesn't just explain the origin of the cosmos. It also provides the crucial link between the microscopic and the macroscopic, showing how the largest structures in the universe were born from the smallest of quantum jitters. We've already seen how inflation stretched quantum fluctuations into the seeds for galaxies, but quantum cosmology aims to explain the origin of those fluctuations themselves. According to quantum field theory, empty space is never truly empty. So-called empty space is a vibrant, dynamic arena where virtual particle pairs constantly flicker into and out of existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other, as demanded by Heisenberg's uncertainty principle. These are not mere mathematical abstractions. Their effects are real and measurable, such as in the slight shift in the energy levels of atoms, known as the Casimir effect. In the incredibly dense environment of the very early universe, these virtual particles were being created and destroyed on a spectacular scale. The tiny, random fluctuations in their energy density, when stretched by inflation, became the slight variations in density that gravity would later amplify into stars, galaxies, and the entire cosmic web. This is the ultimate bridge. The grand tapestry of the cosmos was woven from the ephemeral, ghostly vibrations of the quantum vacuum. The great challenge, the holy grail of modern physics, is to develop a complete theory that successfully merges the world of the very small, governed by quantum mechanics, with the world of the very large, governed by Einstein's general relativity. This sought-after theory of quantum gravity would provide the ultimate set of instructions for the cosmic blueprint, applicable to the very moment of creation itself. Currently, these two pillars of physics are fundamentally incompatible. General relativity describes gravity as the smooth, continuous curvature of spacetime, while quantum mechanics describes a world of discrete, probabilistic jumps. When we try to apply quantum rules to the gravitational field, the mathematics breaks down, producing nonsensical infinities. This tells us that our current understanding is incomplete and that a deeper theory must exist. The quest for quantum gravity is not just an academic exercise. It is essential for understanding the core mysteries of our universe, from the nature of black hole singularities to the very first moment of the Big Bang. Two of the most prominent approaches in this quest are string theory and loop quantum gravity, each offering a radically different vision of reality's fundamental building blocks. String theory proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, one-dimensional vibrating strings. What we perceive as different particles, electrons, quarks, photons, are simply different vibrational modes of these strings, much like different musical notes played on a single guitar string. For the mathematics of string theory to work consistently, it requires that spacetime has more than the 4 dimensions we experience, often 10 or 11. The extra dimensions are hypothesized to be curled up or compactified into a space so small we cannot perceive them. One of string theory's most compelling features is that it naturally includes a quantum particle for gravity, the graviton, seemingly offering a path to unify all forces and matter. However, it has been criticized for a lack of testable predictions with our current technology, and it suggests a vast landscape of possible universes, each with different physical laws. Loop quantum gravity, on the other hand, takes a more direct approach. It does not propose any new dimensions or fundamental objects beyond the fabric of spacetime itself. Instead, it suggests that space is not a smooth, continuous background, but is quantized. It is made of tiny, discrete, indivisible units. Picture the fabric of reality not as a smooth sheet, but as a network of incredibly fine, one-dimensional loops woven together into a dynamic, evolving structure often called a spin network. In this theory, space has a granular, atomic structure at the Planck scale. This leads to a revolutionary concept. The universe did not begin from a singularity of infinite density. Instead, the intense gravity of the Big Bang causes a quantum bounce. According to loop quantum gravity, a previous universe could have collapsed and then, instead of reaching a point of infinite density, quantum effects created a repulsive force, causing a rebound and the birth of our own expanding universe. This offers a compelling, non-singular origin, a cosmic cycle of death and rebirth governed by quantum law. These profound explorations into the quantum origin of everything force us to confront one of the deepest mysteries of all, the nature of time itself. Is time a fundamental, flowing river as it appears in our everyday experience, or is it an emergent property, an illusion that arises from more basic, timeless processes? In the block universe view of relativity, all of time, past, present, and future exists simultaneously in a static, four-dimensional block. There is no special now. Our perception of its flow is just a psychological artifact. Quantum gravity theories push this even further. In some interpretations of loop quantum gravity, time is not a fundamental ingredient of the theory at all. It emerges from the relationships between the changing configurations of the spin network. Similarly, the Wheeler-DeWitt equation, a key equation in canonical quantum gravity, famously lacks a time variable. This suggests that at the most fundamental level, the universe is timeless. The flow of time we experience so vividly might be a collective thermodynamic phenomenon, related to the increase of entropy and the complex interactions of countless quantum particles, rather than a feature of the bedrock of reality. This quantum perspective, with its timeless origins and superposition of possibilities, inevitably opens the door to an even more expansive and staggering possibility, that our universe is not alone, but just one bubble in an infinite, frothing multiverse. But what if the cosmic blueprint we have been so meticulously decoding is not the only one in existence? What if our universe, with its specific set of physical laws and constants, is just a single volume in an infinite library of realities, each with its own unique set of rules? This is the staggering proposition of the Multiverse Hypothesis, a concept that pushes the boundaries of cosmology and philosophy, suggesting that everything we know and see is merely one iteration in a vast, perhaps infinite, ensemble of cosmic domains. The idea emerges not from pure fantasy, but as a natural, and in some cases unavoidable, consequence of our most advanced physical theories. It is a framework that attempts to answer some of our most profound questions, not by narrowing the focus to our one reality, but by dramatically expanding the canvas of what is possible. One of the most compelling versions of this idea springs directly from the theory of cosmic inflation. Recall that inflation proposes a period of fantastically rapid expansion in the universe's first moments. The theory of eternal inflation suggests that this process may not have been a one-time event that started and stopped everywhere at once. Instead, it could be a perpetual, ongoing phenomenon. Picture an eternally inflating background, a kind of cosmic meta-universe where the inflationary energy field is constantly bubbling. In some regions, by random quantum chance, the inflattened field decays, its energy converting into the hot soup of particles that becomes a universe like our own. This process is often called a bubble nucleation, but inflation continues unabated in the spaces between these bubbles. Each of these regions, once it stops inflating, becomes its own separate, isolated universe, forever causally disconnected from our own. In this inflationary multiverse, each bubble universe could have different properties, perhaps even different effective laws of physics, depending on how its particular inflationary field decayed. Our entire observable cosmos, over 90 billion light-years across, would be just a single bubble in a frothing, unending sea of other bubbles. A different but equally profound type of multiverse arises from string theory, one of the leading candidates for a theory of everything. String theory's mathematics require extra spatial dimensions, and the way these dimensions are compactified, or curled up, determines the physical laws and constants that manifest in the resulting four-dimensional universe. The shocking discovery is that there isn't just one way to do this. There are an astronomically large number of possible stable configurations. This collection of possibilities is known as the string theory landscape, and it may contain a number of different vacuum states on the order of 10 to the power of 500. That is a number so vast it dwarfs the number of atoms in our observable universe. Each of these distinct vacuum states corresponds to a universe with a different set of physical laws, different particle content, and different values for the fundamental constants. In this view, our universe is simply one point in this colossal landscape, one particular set of compactification choices that led to a reality compatible with our existence. The landscape is not a physical place you could travel to, but a mathematical map of all possible consistent physical realities that string theory allows. Then there is the multiverse that emerges not from cosmology, but from the heart of quantum mechanics itself, the many worlds interpretation. Formulated by Hugh Everett in the 1950s, this interpretation takes the mathematics of quantum superposition with radical seriousness. We are familiar with the idea that an electron can exist in a superposition of states, say, spinning both up and down simultaneously, until a measurement forces it to choose one. The many worlds interpretation proposes that this choice is an illusion. Instead, at the moment of any quantum event with multiple possible outcomes, the entire universe splits or branches into multiple, equally real copies. In one branch, you see the electron spin up. In another, an identical version of you sees it spin down. This happens not just for laboratory experiments, but for every quantum event everywhere, every photon reflection, every atomic decay. The result is a mind-numbing proliferation of parallel realities, branching from each other at every instant, creating a vast tree-like structure of alternate histories and futures. In one branch, a dinosaur-killing asteroid missed Earth. In another, you made a different life choice this morning. This is not a multiverse of separate bubbles in space, but a multiverse of coexisting, branching timelines, all part of a single, ever-diverging quantum wave function. Theoretical physicist Max Tegmark has pushed this line of thinking to its ultimate logical extreme with his mathematical universe hypothesis. He proposes that all structures that exist mathematically also exist physically. In other words, every single self-consistent mathematical structure corresponds to a physical universe. Our universe is not just described by mathematics, it is a mathematical structure. And if that is the case, then there must be other universes corresponding to all other possible mathematical structures. Some might have 4 spatial dimensions, others might operate with completely different logic, and many would be utterly barren, incapable of supporting any form of complex structure or consciousness. As Tegmark himself has stated, our external physical reality is a mathematical structure. This is the most expansive multiverse of all, a cosmos of pure abstraction where every conceivable form of existence is realized somewhere in the vast Platonic realm. These mind-stretching ideas are not merely intellectual exercises. They have emerged as serious, albeit speculative, attempts to solve 2 of the deepest puzzles we have encountered, the fine-tuning of the universe and the problem of initial conditions. The apparent fine-tuning of our physical constants for life becomes far less mysterious in a multiverse context. If there are a vast or even infinite number of universes, each with randomly different physical parameters, then it is no surprise that we find ourselves in one of the rare, life-permitting ones. It is a cosmic version of the Anthropic Principle on a grand scale. We could not possibly observe a universe that was incompatible with our existence. This is often illustrated with the analogy of a cosmic lottery. Imagine buying a single lottery ticket for a draw with trillions of possible combinations. The odds of your specific ticket winning are astronomically small, but if you were the winner, you wouldn't be shocked to find yourself holding the winning ticket. Someone had to win. In the same way, in a multiverse of countless universes, we shouldn't be surprised to find ourselves living in one of the very few winning universes where the numbers came out just right for stars, planets, and life to form. Similarly, the question, why did our universe have the specific initial conditions that led to inflation and the Big Bang, might be answered by the multiverse, because all possible initial conditions are realized somewhere. Ours is simply the one that produced us. However, the multiverse concept is not without its fierce critics and profound challenges. The most significant is the issue of testability. By their very nature, these other universes are proposed to be permanently beyond our observational reach. If we cannot interact with them, measure them, or receive any signal from them, can the multiverse truly be considered a scientific theory, or is it a form of metaphysics? Proponents argue that the multiverse is a prediction of well-established theories like inflation and quantum mechanics, and that we can look for indirect evidence. For instance, if our universe collided with another bubble universe in the distant past, it might have left a specific anisotropic imprint on the cosmic microwave background, a kind of cosmic bruise. Searches for such an imprint have so far come up empty, but the hunt continues. The predictive power of the multiverse is also debated. By suggesting that every possible universe exists, does it explain everything and therefore predict nothing? If a theory can accommodate any possible observation, it risks becoming unfalsifiable. Furthermore, the philosophical implications are staggering. The multiverse potentially trivializes our existence. If every possible version of every event happens in some branch of reality, then our choices, our history, and our struggles lose their uniqueness. Are we just one copy among an infinite number, living out a predetermined script in a cosmic ensemble so vast that it renders our individual narrative nearly meaningless? Yet, for others, the multiverse inspires a different kind of awe. It suggests a reality of unimaginable richness and creativity, a cosmos where the laws of physics themselves are not immutable decrees but local ordinances, varying from one cosmic domain to the next. It challenges our deepest intuitions about what is real and what is possible, forcing us to confront the limitations of our earth-bound perspective. Whether the multiverse is a temporary stepping stone to a deeper understanding or the final, shocking picture of reality, it fundamentally alters the context of our quest. It tells us that decoding the cosmic blueprint might be an even more immense task than we imagined, requiring us to read not just one set of instructions, but to comprehend the entire library of creation. And as we return our gaze from these dizzying heights of speculation back to our own singular universe, we are drawn to the most tangible and ancient relic we possess, a snapshot that brings us back to the empirical evidence that started it all. After exploring the quantum origins of the cosmos and the dizzying possibility of a multiverse, we return to our own universe and the single most important piece of observational evidence we have for its beginning. Imagine turning off every star, every galaxy, every source of light in the entire cosmos. You might expect utter blackness, but you would be wrong. A faint, cool glow would still persist, a uniform light that fills every cubic inch of space, coming at you from every direction you look. This is the cosmic microwave background radiation, or CMB, and it is the oldest light in the universe. It is the afterglow of the Big Bang itself, a relic from a time when the cosmos was just 380,000 years old. Before this moment, the universe was a hot, dense, opaque fog of plasma, where free electrons constantly scattered light, preventing it from traveling any meaningful distance. But as the universe expanded and cooled, it finally reached a temperature where electrons could combine with protons to form the first neutral hydrogen atoms. In this moment, known as recombination, the cosmic fog literally lifted. The photons, which had been trapped in a constant dance with matter, were suddenly set free to travel across the universe. That first flash of liberated light has been stretching with the expansion of space for over 13 billion years, cooling from a blistering white heat to a faint microwave whisper just 3 degrees above absolute zero. This is the CMB, a baby picture of the infant cosmos, a snapshot frozen in time that we can still detect today. The discovery of this cosmic echo is a classic tale of scientific serendipity, a breakthrough born not from a targeted search, but from the meticulous elimination of an annoying nuisance. In 1965, 2 radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were working with a supremely sensitive horn-shaped antenna originally built for satellite communication. They kept detecting a persistent, low-level static hiss that was present no matter where in the sky they pointed their instrument. It was uniform, it was constant, and it was ruining their experiments. They assumed it was simple instrument noise or local interference. They checked every possible source. They painstakingly examined and reassembled the entire antenna, and famously, they even evicted a pair of pigeons that had taken up residence inside the horn, cleaning out what they described as a white dielectric material that the birds had left behind. But even after the pigeons were gone and their mess was scrubbed away, the stubborn hiss remained. It was a mystery they could not solve. Meanwhile, just a short distance away at Princeton University, a team of physicists led by Robert Dicke was actively building a detector to find precisely this signal. They had predicted that if the Big Bang theory was correct, the remnant heat from the early universe should still be bathing the cosmos in a faint microwave glow. When the 2 groups connected, the pieces fell into place with breathtaking speed. Penzias and Wilson had not found an equipment defect. They had accidentally discovered the fossilized radiation from the birth of the universe. They had stumbled upon the CMB. For this monumental, if accidental, discovery, they were awarded the Nobel Prize in Physics in 1978, a testament to the fact that in science, even a persistent annoyance can be the whisper of creation. The initial detection confirmed the Big Bang model in a single, brilliant stroke, but it was just the beginning. The CMB was remarkably smooth, the same temperature in every direction to an incredible degree of precision. This was powerful evidence for the hot, dense origin of the universe, but it also presented a puzzle. A perfectly smooth early universe had no obvious way to generate the galaxies and cosmic structures we see today. The next great leap was to look closer, to map this uniform glow in exquisite detail to see if there were any tiny imperfections, any ripples in this cosmic pond. This task fell to a series of increasingly sophisticated space-based observatories. The first to successfully map these tiny variations was NASA's Cosmic Background Explorer, or COBE, satellite, which launched in 1989. After years of painstaking data analysis, the COBE team announced their results in 1992. They had found them, The CMB was not perfectly smooth. It contained tiny anisotropies variations in temperature of just about 1 part in 100,000. These were the faint fingerprints of the primordial density fluctuations, the gravitational seeds from which all cosmic structure would eventually grow. The lead scientist for the COBE measurement, George Smoot, captured the profound significance of the moment, famously telling reporters, "If you're religious, it's like looking at the face of God." He was expressing the awe of seeing the direct imprint of the universe's initial conditions, the blueprint for everything that was to come. This detailed mapping of the CMB has been refined to an almost unbelievable precision by 2 subsequent missions, the Wilkinson Microwave Anisotropy Probe, or WMAP, and the European Space Agency's Planck satellite. These missions created exquisitely detailed, full-sky maps of the CMB temperature, a modeled pattern of hot and cold spots that looks like a cosmic Jackson Pollock painting. These are not random splatters, they are an encoded message from the early universe, and by learning to read this message, cosmologists have been able to determine the fundamental parameters of our cosmos with unprecedented accuracy. The precise characteristics of these temperature variations have allowed scientists to calculate the universe's age with remarkable confidence, 13.8 billion years. The patterns also reveal the universe's overall composition, confirming the shocking discovery that the ordinary matter that makes up stars, planets, and us constitutes less than 5% of the total energy density of the cosmos. About 27% is the mysterious dark matter, whose gravitational influence is clearly imprinted on the way the CMB patterns were formed, and the remaining 68% is dark energy, the force driving the accelerated expansion. Furthermore, the geometry of the universe itself is written into these patterns. By measuring the apparent size of the hot and cold spots on the sky, scientists have confirmed that the large-scale geometry of our universe is flat, meaning that the rules of Euclidean geometry we learned in school apply on cosmic scales, a direct prediction of the theory of inflation. But the temperature map is only part of the story. The CMB light is also polarized, meaning its electric field vibrates in a preferred direction. This polarization carries a whole additional layer of information about the universe's history. One type of polarization, known as E-mode polarization, was detected and mapped by WMAP and Planck, and it largely confirms the story told by the temperature variations. However, the real holy grail for cosmologists is the hunt for a much fainter, swirling pattern known as B-mode polarization. This specific signal is a direct prediction of the theory of cosmic inflation. The violent, rapid stretching of spacetime during that first inflationary fraction of a second would have generated powerful ripples in the fabric of the cosmos' primordial gravitational waves. These waves would have left a distinct curling pattern imprinted on the polarization of the CMB. Finding this B-mode signal would be the smoking gun for inflation, providing direct evidence for the universe's primordial growth spurt and potentially revealing the energy scale at which it occurred. A tentative detection announced by the BICEP 2 telescope at the South Pole in 2014 created a media frenzy, but it was later shown that the signal could be largely explained by interstellar dust within our own galaxy. The hunt for this definitive signal continues with ever more sensitive experiments, as it would allow us to peer back to a time even earlier than the CMB itself, directly probing the physics of the universe's first fleeting moments. The CMB is far more than a static monument to the past. It is an active tool for probing the universe's deepest ongoing mysteries. For instance, the precise way that the CMB light has been subtly deflected and distorted as it travels across the cosmos for 13 billion years, a phenomenon known as gravitational lensing, allows scientists to create maps of the distribution of all matter both visible and dark, throughout the universe. This provides an independent way to weigh galaxy clusters and trace the invisible dark matter scaffolding that holds them together. Furthermore, certain subtle anomalies in the CMB, such as a mysterious large-scale cold spot and an unexpected alignment of patterns across the sky, have sparked intense debate. Some researchers speculate these could be evidence of something truly exotic, like a collision with another bubble universe in the multiverse, though more conventional explanations involving statistical flukes or complex foreground effects are still the most likely. The CMB continues to be a treasure trove of information, and with each new level of precision, we ask new questions. What can its faintest whispers tell us about the nature of dark matter particles? Could its polarization reveal the existence of cosmic strings or other topological defects from the early universe? This incredibly rich snapshot not only confirms our cosmic origins but also serves as a bridge, connecting the fiery beginning of the universe to the dynamic, expanding cosmos we observe today, leading us directly to a modern puzzle that threatens to shake the very foundations of cosmology. Yet, as we build our cosmic model on this incredibly precise foundation, a troubling crack has begun to appear, a discrepancy that has grown from a faint whisper into a roar that the entire field of cosmology cannot ignore. It's a problem known as the Hubble tension, and at its heart is a simple but profound question: how fast is the universe expanding right now? This rate of expansion is quantified by the Hubble constant, a single number that represents how many kilometers per second a galaxy is moving away from us for every megaparsec of distance, a megaparsec being an almost unimaginable 3.26 million light-years. For decades, astronomers have worked to pin down this number with ever greater precision, expecting that different methods would eventually converge on a single, definitive value. Instead, they have arrived at two different, stubbornly conflicting answers. It's as if we have two supremely accurate cosmic clocks, both built according to the best understanding of physics, and they are ticking at undeniably different rates. This isn't just a minor calibration issue, it is a direct challenge to our understanding of the cosmic blueprint, suggesting that a fundamental piece of our model of the universe might be missing or mistaken. The conflict arises from two distinct and highly respected paths of measurement. The first path looks back to the very beginning, using the pristine snapshot of the infant universe provided by the cosmic microwave background. The European Space Agency's Planck satellite mapped the CMB with breathtaking detail, and by analyzing the subtle patterns of hot and cold spots, cosmologists can run the cosmic film forward. They input the known ingredients of our universe, the amount of ordinary matter, dark matter, and dark energy, into the supercomputer of our theoretical models, which then simulates 13.8 billion years of evolution to predict what the expansion rate should be today. This early universe method, relying on the standard model of cosmology, gives a very precise value for the Hubble constant, roughly 67 kilometers per second per megaparsec. This is the universe's expansion rate as inferred from its baby picture. The second path measures the universe's current expansion directly, a technique often called the distance ladder. This is a meticulous step-by-step process that builds out from our local cosmic neighborhood. It starts with pulsating stars called Cepheid variables, which are our cosmic yardsticks. These stars have a wonderful property. Their intrinsic brightness is directly linked to their pulsation period. By measuring how fast a Cepheid pulses, astronomers know its true brightness. Then, by measuring how dim it appears from Earth, they can calculate its distance with remarkable accuracy, just as you could judge the distance of a car at night if you knew the true power of its headlights. This method was pioneered by Henrietta Leavitt and was crucial to Edwin Hubble's original discovery of the expanding universe. Today, teams led by astronomers like Adam Rees, who won a Nobel Prize for his work on the accelerating universe, used the Hubble Space Telescope to painstakingly measure cepheids in galaxies that also contain another, even brighter type of explosion, type Ia supernova. These supernovae are so brilliant and uniform that they act as standard candles for measuring far greater distances. By linking the known distances of nearby cepheids to the observed brightness of distant supernova, astronomers can calibrate the entire cosmic distance ladder and measure the expansion rate of the modern universe directly. And this is where the tension snaps tight. This late universe method consistently gives a higher value for the Hubble constant, around 73 kilometers per second per megaparsec. The difference between 67 and 73 might seem small, but in the world of precision cosmology, it is a chasm. The uncertainties on each measurement have been squeezed so small that the chance this discrepancy is a simple statistical fluke is now vanishingly small. As Adam Rees has compellingly stated, this is not just two experiments disagreeing. We are measuring something fundamentally different. One is a measurement of how fast the universe is expanding today as we see it. The other is a prediction based on the physics of the early universe and our model of how the universe should evolve. The fact that they don't agree is telling us that there is something in our cosmological model that we don't understand. It's a confession from the forefront of science that our map of reality, for all its detail, may contain a significant, uncharted region. So, what could be causing this fundamental disagreement? Cosmologists are exploring a fascinating menu of possibilities, ranging from the mundane to the revolutionary. The first and most conservative explanation is that of systematic errors. Perhaps there is an unseen flaw in our measurements that we haven't yet accounted for. Maybe our understanding of cepheid variables is not as complete as we think, or there is some subtle dust in galaxies that is dimming the light of supernova in a way we haven't perfectly modeled. Teams are constantly working to cross-check and refine the distance ladder, using other methods like the subtle geometry of red giant stars or the maser emissions from swirling disks around distant black holes. While some small adjustments have been made, the core discrepancy has stubbornly refused to go away, making a pure measurement error seem increasingly unlikely. If the problem isn't with our measurements, then it must be with our model. This is where the possibilities become truly thrilling, as they point toward the potential need for new physics. One compelling idea is that dark energy, the mysterious force driving cosmic acceleration, is not constant as Einstein's cosmological constant suggests. What if it's dynamic? A form of energy that astrophysicists call quintessence could be evolving over time, growing stronger or weaker, and thereby changing the expansion history of the universe in a way that our standard models don't account for. This could create a divergence between the expansion rate predicted from the early universe and the one we measure locally today. Another intriguing proposal involves dark matter, the invisible scaffolding of the cosmos. Perhaps dark matter interacts with itself or with other particles in ways we haven't yet discovered, subtly altering how structures formed and how the universe expanded over billions of years. Even more exotic ideas are on the table, such as the existence of a new, previously undetected type of neutrino, a sterile neutrino, that would have streamed through the early universe, altering the rate at which structures formed and thereby changing the predicted expansion rate. Each of these possibilities represents a potential revision to the cosmic blueprint, an addendum to the laws of physics as we currently understand them. To grasp why this tension is so much more than an academic debate, consider the analogy of two clocks. Imagine you have a beautifully engineered grandfather clock that has been meticulously wound and calibrated according to a set of perfect theoretical principles. This is the early universe measurement from the Planck satellite. At the same time, you have a collection of the most accurate atomic clocks ever built, all synchronized and ticking in the present day. These are the distance ladder measurements from Cepheids and Supernovae. For years, you have believed that both sets of clocks are governed by the same, unchangeable rules of timekeeping. But one day, you notice a persistent, undeniable drift. The grandfather clock, governed by your theoretical model, is ticking consistently slower than the array of atomic clocks measuring the actual present. This isn't a matter of one being right and the other wrong. It is a signal that your fundamental understanding of timekeeping itself, the very principles you use to build and calibrate the grandfather clock, is incomplete. In our cosmic context, the Hubble tension tells us that the rules we use to project the universe's history forward from its infancy may not perfectly match the rules that are governing its behavior right now. We are missing a piece of the mechanism. Resolving this tension is therefore one of the most urgent goals in modern cosmology. The implications are profound. If the solution requires new physics, it would force a rewrite of the cosmic blueprint, fundamentally altering our understanding of the components and forces that have shaped the universe's evolution. It could reveal a deeper nature for dark energy or dark matter, finally giving us a handle on these elusive phenomena. This wouldn't just change a number in a textbook, it would reshape our entire narrative of cosmic history, and most critically, recalibrate our predictions for the ultimate fate of everything. The expansion rate is the master dial that controls the long-term destiny of the cosmos, determining whether we are headed for a slow, cold fade or a more dramatic end. The Hubble tension is a stark reminder that our quest to decode the cosmic blueprint is a dynamic, living process where the universe itself is the final arbiter of our theories, and its most puzzling anomalies are often the signposts pointing toward the next great discovery. Looking out across the vast expanse of cosmic history, from the initial fireball to the formation of galaxies and the emergence of life, we are inevitably drawn to the final chapter of the story. What does the future hold for the universe itself? The cosmic blueprint, it turns out, contains several possible endings, and the one we are heading toward depends entirely on the long-term behavior of the most mysterious character in our story, dark energy. Based on our current best measurements, the most likely fate is a slow, cold, and dark conclusion known as the Big Freeze or heat death. In this scenario, the accelerated expansion driven by dark energy continues unchecked. Over trillions of years, the universe will become a far more lonely and isolated place. Galaxies beyond our local group will have been pushed so far away by the stretching of space that their light will no longer be able to reach us, vanishing beyond the cosmic horizon. Within each galaxy, including our own Milky Way, the stars will gradually use up their nuclear fuel. The massive, brilliant blue stars will be the first to go, exploding as supernova after just a few million years. Our own sun will eventually exhaust its hydrogen, swell into a red giant that may engulf the Earth, and then fade away into a white dwarf over many billions of years. Smaller, cooler red dwarf stars will burn for trillions of years longer, but eventually, even their faint fires will sputter out. The universe will be left with the cold, dark remnants of stellar corpses, white dwarfs that slowly cool into black dwarfs, neutron stars, and black holes. The era of starlight will be over, and the cosmos will be plunged into an ever-deepening darkness. This journey toward maximum disorder, or entropy, is a central theme of this cosmic end. As the theoretical physicist Brian Greene has eloquently described, the universe is on a one-way trip from a state of low entropy, like the highly ordered and dense beginning of the Big Bang, to a state of high entropy, a vast, diffuse, and uniform equilibrium. He explains that entropy is a measure of disorder, and the second law of thermodynamics tells us that it always increases. In the context of the heat death, this means that all energy gradients, the differences in temperature and density that allow for work to be done and complexity to arise, will eventually be smoothed out. The universe will approach a single, lukewarm temperature, just a fraction of a degree above absolute zero. With no hot places and no cold places, no energy can flow. It will be a state of cosmic stagnation where no chemical reactions can occur, no engines can run, and no life, as we understand it, can possibly exist. It is the ultimate thermodynamic equilibrium, a final, silent state where the clock of change effectively stops ticking. But the Big Freeze is not the only possibility written into the cosmic blueprint. The ultimate fate hinges on a critical tug of war between the outward push of dark energy and the inward pull of gravity, and this is quantified by a key parameter known as the density parameter, often symbolized as omega. If the density of dark energy were to weaken or reverse over time, gravity could regain the upper hand. This could lead to a dramatically different finale, the Big Crunch. In this scenario, the expansion of the universe would gradually slow, halt, and then reverse. Galaxies would begin rushing back toward each other. The cosmic background temperature would rise, and the sky would glow ever brighter. In the final moments, the entire universe would collapse back into a state of incredible heat and density, a mirror image of the Big Bang, potentially collapsing into a singularity. Some speculative theories even suggest a Big Bounce, where this collapse leads not to an end, but to a rebirth, with a new universe exploding out of the ashes of the old one in a cyclical, eternal process. However, all our current observational evidence, from supernova to the cosmic microwave background, strongly suggests that dark energy is behaving like a cosmological constant. Its density appears to be stable and not weakening. This makes the Big Crunch a far less likely outcome than the Big Freeze. There is, however, a third, even more violent possibility, the Big Rip. This scenario arises if the density of dark energy doesn't just remain constant, but actually increases over time. In this model, the repulsive force of dark energy becomes so overwhelmingly powerful that it doesn't just push galaxies apart. It begins to tear apart everything that gravity holds together. First, the cosmic horizon would shrink, pulling galaxy clusters apart. Then, the galaxies themselves would be ripped to shreds, their stars flung into the void. As the end drew nearer, the destructive force would reach smaller and smaller scales. A few 100,000 years before the final moment, the solar systems would be torn apart. In the last minutes, stars and planets would be shredded. In the final, cataclysmic instant, even atoms and atomic nuclei would be unable to withstand the force, and the very fabric of spacetime itself would be torn asunder. While a terrifying vision, most current data does not support this model. The observed properties of dark energy are consistent with a constant density, which points toward the long, slow fade of the Big Freeze rather than the sudden, violent end of the Big Rip. To understand these futures in more concrete terms, we can look to sophisticated computer simulations that model the evolution of the universe over unimaginable timescales. Simulations of galaxy mergers show that while our local group of galaxies will eventually coalesce into a single, giant elliptical galaxy over the next several billion years, this will be one of the last major acts of cosmic structure formation. As dark energy drives the rest of the universe away, this will be the final island of matter in our observable realm. On even longer timescales, simulations of black hole decay become relevant. According to Stephen Hawking's theory, black holes are not entirely black. They slowly radiate away their mass through a quantum process known as Hawking radiation. For a stellar mass black hole, this process takes an almost inconceivably long time, far longer than the current age of the universe. But in the cold, dark era of the Big Freeze, this evaporation becomes the main event. Over periods of time measured in googolls of years, black holes will slowly lose mass, eventually evaporating completely in a final, faint flash of particles. When the last black hole disappears, the universe will be left with only a thin, ever-cooling soup of subatomic particles and radiation, drifting forever farther apart in an infinite, silent, and lifeless expanse. This profound and sobering vision of the far future naturally leads us to a deeply human and philosophical question. In such a universe, what is the place of intelligence and meaning? If the ultimate destiny of all complex structures is to dissolve into a featureless equilibrium, does that render our existence, our struggles, and our achievements meaningless? Some philosophers and scientists argue that it does not. They suggest that meaning is not derived from permanence, but is created in the present moment and in the relationships we forge. The transient nature of stars, galaxies, and life itself could be seen as what makes them so precious and beautiful. The fact that we are here for a brief cosmic moment, able to understand the grand story of creation from the first instant to the last, is itself a remarkable and significant event. The universe becomes meaningful not despite its impermanence, but because of the fleeting, brilliant complexity that arises within it. Our ability to contemplate the cosmos, to feel awe at its scale, and to seek understanding is a profound feature of this tiny, vibrant chapter in an otherwise immensely long and quiet story. This line of thought pushes us to consider whether intelligence itself could find a way to persist, even in the face of the universe's eventual decline. Could a sufficiently advanced civilization, perhaps one that has transitioned to a post-biological form, engineer a way to survive the end of stars, perhaps by harnessing the energy of black holes or creating simulated realities that require minimal energy? The challenges are, of course, monumental. As usable energy becomes scarce and the universe approaches maximum entropy, the ability to perform computations and sustain complex information processing would inevitably fade. The heat death represents a fundamental limit, not just on life, but on information and thought itself. This ultimate confrontation with the limits of existence, dictated by the immutable laws of thermodynamics written into the cosmic blueprint, forces us to confront our deepest hopes and fears about time, legacy, and the nature of reality. Our contemplation of these cosmic endings, from the quiet fade to the violent rip, ultimately circles back to the astonishing fact that we are here at all, in this relatively brief golden age of cosmic light and life, able to ask these questions and to wonder about our role in the vast, unfolding story. So, after contemplating the ultimate fate of the cosmos, we are left with a truly remarkable and almost paradoxical realization. In order for there to be a universe with a fate to contemplate, there must first be someone here to do the contemplating. This brings us to one of the most profound and mind-bending concepts in all of science, a principle that places us, the observers, right at the heart of the cosmic story. It's the Anthropic Principle, the startling idea that the universe's physical laws and constants are the way they are precisely because they allow for the existence of observers who can perceive them. In a very real sense, we are not just passive inhabitants of the cosmos, we are active participants in its narrative, the means by which the universe becomes aware of itself. Our very ability to decode the cosmic blueprint is a feature written into that blueprint, a necessary consequence of the specific rules that govern reality. The term itself was coined by the astrophysicist Brandon Carter in 1974 during a conference celebrating the 500th anniversary of Copernicus's birth. Ironically, while Copernicus had pushed humanity from the center of the universe, Carter's principle subtly but powerfully brought us back into the picture, not as the spatial center, but as a logical necessity. Carter carefully distinguished between two forms of this principle. The weak Anthropic Principle is a straightforward statement of a selection effect. It simply says that the observed values of all physical and cosmological quantities are not random, but are restricted by the requirement that there be sites where carbon-based life can evolve, and by the requirement that the universe be old enough for it to have already done so. In other words, we must be prepared to take into account the fact that our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. We couldn't possibly find ourselves in a universe that is incompatible with life because we wouldn't be here to look around. It's a logical truism, but one with deep implications. Then there is the strong Anthropic Principle, which takes this logic a step further into much more controversial territory. This version suggests that the universe must have those properties which allow life to develop within it at some stage in its history. The key word here is must. This formulation moves from a simple observation about our necessary location to a statement about the universe's fundamental laws, hinting that there is something special or even purposeful about a cosmos that gives rise to conscious life. It's this stronger version that often gets entangled with philosophical and even theological debates about design, as it can be interpreted to mean that the universe is, in some sense, intended for life. Brandon Carter himself was cautious, focusing on the scientific utility of the weak principle as a tool for understanding why certain physical constants fall within such narrow, life-permitting ranges. He argued that we must consider the biological context when discussing cosmology, because the conditions necessary for life impose very specific constraints on the kind of universe we could possibly observe. When we drill down into what those biological conditions actually are, the sheer number of prerequisites for a civilization like ours to emerge is nothing short of breathtaking. It's not just about the fundamental constants being fine-tuned. It's about an entire cascade of cosmic and planetary circumstances aligning in just the right way. Let's consider the foundation of life as we know it, carbon-based chemistry. Carbon is the cosmic multitool, able to form long, stable chains and complex three-dimensional structures, creating the proteins, DNA, and carbohydrates that are the building blocks of biology. But for carbon to even exist, the universe had to be just right. The nuclear forces had to be calibrated so that 3 helium nuclei could fuse into a single carbon nucleus in the hearts of stars, a process that is incredibly sensitive to the precise energy levels involved. If the strong nuclear force were just a fraction of a % different, this crucial reaction might not happen, and the universe would be devoid of carbon and therefore of the chemistry that underpins all known life. Beyond the universal constants, a stable and nurturing local environment is just as critical. This brings us to the concept of planetary protection. A life-bearing planet needs a massive outer guardian like our Jupiter, whose immense gravity acts as a cosmic vacuum cleaner, deflecting or absorbing a significant number of comets and asteroids that would otherwise bombard the inner solar system with sterilizing impacts. Our own history, including the impact that likely wiped out the dinosaurs, shows that this protection isn't perfect, but without a Jupiter, such catastrophic events would be far more frequent, potentially resetting the evolutionary clock too often for intelligent life to ever gain a foothold. Then there's the need for a large stabilizing moon. Earth's moon is unusually large relative to its planet, and its gravitational influence acts as a gyroscope, preventing wild, chaotic swings in Earth's axial tilt over geological timescales. Without the moon, our planet's tilt could vary dramatically. leading to extreme and unpredictable climate shifts that would make the long, stable environmental conditions necessary for the evolution of complex life virtually impossible. The elemental abundance on a planet is another non-negotiable factor. A world must have access to a rich and diverse palette of elements beyond just carbon. We need oxygen for respiration and water, nitrogen for our atmosphere and amino acids, phosphorus for our energy-carrying ATP molecules, and trace metals like iron for our blood and for crucial enzyme functions. These elements aren't created in the Big Bang. They are forged in the lives and deaths of stars and scattered across the galaxy by supernova explosions. This means that for a planet to have a sufficient abundance of these heavy elements, it must form from the debris of earlier generations of stars. Our solar system is a product of such cosmic recycling, forming from a cloud of gas and dust that was enriched by the ashes of long-dead stellar giants. A planet forming too early in the universe's history would have been composed only of hydrogen and helium, a world without the chemical complexity needed for life. A planet forming too late might be rich in heavy elements, but it could also be bathed in more dangerous radiation from a more crowded galactic environment. This intricate web of requirements forms the core of what is known as the rare earth hypothesis. This provocative idea, developed by paleontologist Peter Ward and astronomer Donald Brownlee, argues that while simple microbial life might be common throughout the galaxy, the emergence of complex, animal-level life and technological intelligence requires such a specific and fragile combination of astrophysical and geological circumstances that it is exceedingly rare. They point to a long list of factors that had to align perfectly for us to be here: a star that is stable, long-lived, and not prone to violent flares, a planetary orbit within the narrow habitable zone, plate tectonics for climate regulation and nutrient recycling, a magnetic field for atmospheric protection, the right amount of water, and the list goes on. From this perspective, Earth is not a mediocre, average planet, but an extraordinary cosmic oasis, a jewel of improbable perfection in a vast and mostly sterile universe. Of course, this view is hotly debated. The counter-argument, often called the principle of mediocrity, suggests that there is nothing particularly special about Earth or our circumstances. Proponents of this view argue that given the sheer number of planets in the galaxy, numbering in the hundreds of billions, even if the probability for each one developing complex life is infinitesimally small, the law of truly large numbers all but guarantees that we are not alone. They also point to the tenacity of life on Earth, flourishing in the most extreme environments, from deep-sea hydrothermal vents to acidic hot springs and frozen Antarctic lakes. This remarkable resilience, known as extremophilia, suggests that life is not a delicate flower, but a tough and opportunistic force that can adapt to a wide range of conditions. Perhaps life doesn't need an Earth-like planet at all. Maybe it can arise in the subsurface oceans of icy moons like Europa or Enceladus, using chemical energy rather than sunlight, and following a completely different evolutionary path. In this view, the universe might be teeming with life, but most of it could be simple, microbial, and hidden from our view, with technological civilizations remaining incredibly rare or transient. So, where does this leave the Anthropic Principle? Does the apparent fine-tuning of the universe for life point toward a cosmos that is inherently biophilic or even designed, or does it simply reflect a profound selection bias? The strong anthropic interpretation leans toward the former, seeing the laws of physics as evidence of a deeper teleology, a universe that was somehow set up with the goal of producing consciousness. The weak anthropic interpretation, favored by most scientists, sees it as the latter, a straightforward consequence of our own existence. We are here, so the universe that spawned us must have the right properties. This logical stance finds its most powerful expression in the multiverse theory. If our universe is just one bubble in an infinite and eternal multiverse, where every possible set of physical laws is realized somewhere, then it is no surprise that we find ourselves in one of the rare, life-friendly bubbles. There is no fine tuner, there is just a colossal cosmic lottery, and we hold the winning ticket. Our universe isn't fine-tuned for life, we are simply the life that is tuned to our universe. This grand debate ultimately forces us to confront the very nature of reality and our place within it. Are we a cosmic accident, a happy fluke in a vast and mostly dead cosmos, as the rare Earth hypothesis and the multiverse interpretation might suggest? Or are we the intended outcome of a universe that is fundamentally structured to give rise to mind? Perhaps the truth lies in a third, even more radical possibility, that life and consciousness are not just happy accidents, but are inherent, emergent properties of a complex universe. Just as water inevitably forms waves under the influence of wind, perhaps the universe, given the right conditions of complexity and stability, inevitably gives rise to systems that can process information, feel, and think. In this view, the universe isn't fine-tuned for us specifically, but it is tuned for the emergence of complexity, and we are one magnificent expression of that deeper tendency. The Anthropic Principle, in all its forms, doesn't provide easy answers, but it frames the most important question of all. Why does a universe that allows for questions exist in the first place? Our very act of questioning is a part of the cosmic process, a direct readout from a blueprint that seems to have written itself into existence, with us as its most curious and articulate readers. This profound link between the conscious mind and the cosmos it observes naturally propels our curiosity outward, to the stars, and to the tantalizing possibility that we might not be the only ones reading the blueprint. So, if we are the universe's way of reading its own blueprint, could there be other readers out there, other minds looking back at the cosmos and asking the very same questions? This is the driving force behind the search for extraterrestrial intelligence, a quest that transforms our cosmic solitude from a lonely assumption into an open-ended question. Imagine the scene, a massive white radio telescope dish like the one at the Green Bank Observatory in West Virginia, silently pivoting against a starry sky. It is not listening to the natural hum of the universe, but is actively scanning the radio frequencies, straining to hear a whisper of order, a pattern, a signal that is unmistakably artificial. This is the essence of SETI, a scientific endeavor that represents one of the most profound and hopeful experiments in human history, the search for cosmic co-authors, other beings who are also engaged in the great work of decoding the universal design. The modern era of this search began in a spirit of quiet, determined optimism. In 1960, a young astronomer named Frank Drake pointed the Green Bank telescope toward two nearby, sun-like stars, Tau Ceti and Epsilon Eridani. He named this effort Project Ozma, after the princess of the mythical land of Oz, a place very far away and difficult to reach. For a few hundred hours, the telescope listened, tuned to a specific frequency of neutral hydrogen, which scientists considered a logical, watering hole for galactic communication. The project detected nothing conclusive, but it ignited a flame. It established the methodology and the philosophical framework for all subsequent searches, the use of radio astronomy to hunt for narrowband signals that could not be produced by any known natural process. Project Ozma was a whisper into the dark, a demonstration that humanity was ready, at least technologically, to begin the conversation. Since that pioneering effort, the search has grown in scale and sophistication by orders of magnitude. For decades, SETI was a fringe, poorly funded endeavor, often relying on borrowed telescope time and the passion of a small group of researchers. A major leap forward came with the launch of projects like SETI at Home in 1999, which harnessed the spare computing power of millions of personal computers around the world to analyze the torrents of radio data, creating the world's largest supercomputer for a time and engaging the public directly in the search. Today, the effort is spearheaded by initiatives like Breakthrough Listen, a $100 million 10-year program that is the most comprehensive search for extraterrestrial intelligence ever undertaken. Using some of the world's most powerful radio telescopes, including the Green Bank Telescope and the Parkes Observatory in Australia, it is systematically surveying 1 million nearby stars, the entire galactic plane, and 100 nearby galaxies, scanning across a much wider range of frequencies than ever before. The project is not just looking for deliberate messages, it is hunting for any sign of technology, any leak of electromagnetic radiation that would betray the presence of another technological civilization. This expansion of scope reflects a crucial evolution in the field, a shift from just seeking intentional messages to also hunting for technosignatures. A technosignature is any measurable phenomenon that provides scientific evidence of past or present technology. It is a much broader and richer concept than a simple hello signal. It acknowledges that an advanced civilization might not be deliberately trying to contact us, but its industrial and technological activities would still leave traces we could potentially detect. What might these look like? The possibilities are as vast as imagination and physics allow. We could search for the spectral signature of artificial pollutants in an exoplanet's atmosphere. Just as our own industrial revolution filled our air with chlorofluorocarbons and nitrogen dioxide, a distant world might show similar signs of large-scale industry. Another compelling idea involves looking for the telltale dimming of a star caused by colossal orbiting structures, often called Dyson spheres or swarms, which an advanced civilization might build to capture a significant portion of its star's energy output. We could even search for the brief, intense flashes of light from interstellar laser communication, or the anomalous waste heat from massive energy consumption. This shift to technosignatures transforms the search from listening for a phone call to looking for the glow of an entire city from a great distance, opening up dozens of new avenues for discovery. The challenges of this endeavor, however, are as immense as the cosmos itself, and they demand a perspective that spans generations. The legendary SETI scientist Jill Tarter, whose career inspired the protagonist in the film Contact, has long been a voice of profound patience and perspective. She has often spoken about the need to think in cosmic time, reminding us that a negative result after a few decades of searching is meaningless on a galactic scale. As she eloquently put it, we've only just begun to look. The entire history of SETI is a single grain of sand on the beach of cosmic time. She also emphasizes the critical factor of longevity. The challenge may not be for a civilization to arise, but for it to survive its own technological adolescence. A civilization must navigate the perils of its own power, the risks of self-destruction through war, environmental collapse, or other unforeseen consequences of technology, long enough to become a durable, spacefaring species. The fact that we have not found anyone yet might not mean they aren't there. It might simply mean that the window for two civilizations to overlap in both time and technological capability is incredibly narrow. The sheer physics of interstellar space creates a daunting set of obstacles for any form of communication. The first and most fundamental is distance. The nearest star system, Alpha Centauri, is over 4 light-years away. A two-way conversation at the speed of light would take nearly a decade. For a civilization hundreds or thousands of light years away, the time lag makes any meaningful dialogue across generations impossible. A message we send today might not receive a reply for a millennium. Then there is the energy requirement. To send a powerful, detectable signal across such vast distances requires a transmitter of almost unimaginable scale, focusing immense energy into a narrow beam. For us to detect such a signal, our telescopes would need to be pointed in exactly the right direction, at exactly the right frequency, at exactly the right time. It is the ultimate cosmic needle in a haystack problem. Finally, there is the challenge of frequency and protocol. The electromagnetic spectrum is vast. Which frequency would another civilization choose? Would they use a simple mathematical pattern like prime numbers, as suggested in the movie Contact, or something far more complex that we cannot yet decipher? Without a pre-arranged meeting point and a shared language of physics and mathematics, we are essentially hoping to stumble upon a signal we can recognize as artificial, amidst the constant, natural radio chorus of the universe. The history of SETI is punctuated by a few tantalizing moments that highlight both the promise and the frustration of the search. The most famous of these is the wow signal. On August 15, 1977, the Big Ear radio telescope at Ohio State University recorded a powerful, narrow-band radio signal that matched the exact profile of an anticipated extraterrestrial transmission. It was 72 seconds long, was concentrated in a narrow frequency band, and came from the direction of the constellation Sagittarius. The astronomer who discovered the signal, Jerry Amon, circled it on the printout and wrote, "Wow," in the margin, giving it its iconic name. The signal was never detected again, despite dozens of subsequent attempts to find it. To this day, it remains the strongest candidate for an artificial interstellar signal, but without verification, its origin is a mystery. It could have been an incredibly fortunate reflection of a human-made satellite, a previously unknown astronomical phenomenon, or it could have been exactly what it looked like, a brief, brilliant hello from the cosmos, a single page of the cosmic blueprint written by another hand, which we glimpsed for a moment and then lost. Alongside the search for radio signals and optical lasers, a parallel and equally exciting frontier has opened up: the study of exoplanet atmospheres for biosignatures, which are chemical signs of life, and technosignatures. With the launch of powerful new telescopes like the James Webb Space Telescope, we are now gaining the capability to analyze the light from distant worlds. As starlight filters through a planet's atmosphere, different molecules absorb specific colors, creating a unique chemical fingerprint in the spectrum. We can look for biosignatures like the simultaneous presence of oxygen and methane, which on Earth are produced by life and would quickly react and disappear without a continuous biological source. But we can also look for technosignatures. For example, chlorofluorocarbons, or CFC, are industrial chemicals that do not occur naturally. Detecting CFCs in the atmosphere of a world orbiting another star would be a powerful, albeit indirect, sign of an industrial civilization. Another potential technosignature could be an unnatural, persistent glow from a city's artificial lighting on the planet's night side. While these searches are in their infancy, they represent a powerful convergence of astrobiology and SETI, allowing us to search not just for a civilization's messages, but for the very footprint of its existence. This entire grand endeavor forces us to look inward and confront a question that is as much philosophical as it is scientific. What would contact actually mean for humanity? The discovery of an intelligent signal would be one of the most transformative events in all of human history, a pivotal moment that would instantly shatter our cosmic isolation. It would prove once and for all that life and intelligence are not a singular, miraculous accident on one tiny planet, but a natural part of the cosmic process. It would confirm that the blueprint for complexity and consciousness is written into the laws of the universe in a fundamental way. Such a discovery would fundamentally alter our understanding of our own place in the cosmos. We would no longer be a solitary voice in the silence. We would become part of a cosmic community, even if that community is separated by vast stretches of space and time. It would provide a powerful, unifying perspective for all of humanity, a shared identity as citizens of a galaxy that is rich with life and mind. The knowledge that we are not alone could inspire a new era of global cooperation and a renewed commitment to safeguarding our own fragile planet, ensuring that our civilization achieves the longevity that Jill Tarter speaks of. But it also raises profound and unsettling questions about the nature of that intelligence. Would it be benevolent, malevolent, or simply indifferent? The message might not be one we can understand, or it might contain knowledge that is dangerously destabilizing to our society. It could be a beacon meant to guide emerging civilizations, or it could be the equivalent of ancient, automated cosmic infrastructure, the ghost of a civilization long since vanished. The content of the signal could contain an entire library of another world's history, science, and art, a gift of unimaginable value, or it could be a simple, repeating pattern, a basic "we are here" that offers no further insight. The very act of contact would force us to re-evaluate everything from our religions and philosophies to our long-term aspirations as a species. It would be a mirror held up to humanity, revealing both our potential and our fragility in a universe that is suddenly and irrevocably shared. This search for cosmic co-authors, for other readers of the blueprint, is therefore a journey of self-discovery as much as it is a journey of exploration. It compels us to consider our own legacy and our own impact, not just on our planet, but on the wider universe we are now beginning to perceive and perhaps one day to join. It is one of the most haunting questions in all of science, a puzzle born over a casual lunch conversation that has echoed through the decades. The physicist Enrico Fermi, while discussing the high probability of extraterrestrial civilizations with his colleagues, suddenly looked around and asked with characteristic bluntness, "Where is everybody?" This is the Fermi Paradox, the stark and unsettling contradiction between the overwhelming probability of alien life and the absolute, deafening silence we observe. The universe is ancient, over 13.8 billion years old. Our galaxy alone contains hundreds of billions of stars, and a significant fraction of those are likely orbited by planets in habitable zones. The ingredients for life seem to be scattered everywhere across the cosmos. Given all this time and all this space, the galaxy should be teeming with life, its signals buzzing through the interstellar medium, its vast engineering projects visibly altering starlight. The cosmic blueprint, it seems, has all the instructions for building civilizations, and yet, when we train our most powerful instruments on the sky, we are met with a profound and mysterious quiet. The universe appears empty, a silent library filled with books that no one seems to be reading. This silence is not just an absence of data. It is a data point in itself, a clue that something in our assumptions about life and intelligence might be profoundly wrong. Scientists and thinkers have proposed a vast spectrum of possible resolutions to this paradox, which author Stephen Webb has masterfully catalogued, noting that there are perhaps 50 solutions to the Fermi paradox, ranging from the depressing to the exhilarating. These ideas generally fall into a few broad, sobering categories. The first is the possibility that intelligent, technological civilizations are simply exceedingly rare. Perhaps the chain of events that leads from non-living chemistry to a spacefaring species is so long and fraught with peril that it almost never happens twice. The second category suggests that civilizations are not rare, but they are tragically short-lived. They may arise, but they inevitably destroy themselves within a few centuries of discovering the technology that could make them visible, whether through nuclear war, environmental collapse, or a technology we haven't yet imagined. A third set of ideas proposes that advanced civilizations are out there, but we cannot detect them for reasons that range from technological gaps to deliberate choice. They might be using communication methods we can't yet conceive of, or they might be observing us with a policy of strict non-interference, a cosmic version of a nature preserve. One of the most compelling and frankly terrifying explanations is the concept of the Great Filter. This idea suggests that there is some kind of barrier, a critical evolutionary or technological step that is so difficult to overcome that it effectively prevents virtually all life from progressing to the stage of interstellar colonization and communication. The filter acts as a kind of cosmic sieve, and the profound silence we observe suggests that we and every other potential civilization are on one side of it, while the vast populated galaxy we expect is on the other. The crucial and unsettling question is, where is this great filter located in the timeline of evolution? Is it behind us, or is it still ahead of us? If the filter is behind us, it means we are an incredibly lucky species to have made it this far. Perhaps the very origin of life itself, the transition from non-living chemistry to a self-replicating organism, is the insurmountable hurdle. This step, known as abiogenesis, might be a 1 in a trillion fluke, despite the universe's abundance of organic molecules. Or perhaps the filter was the leap from simple prokaryotic cells to complex eukaryotic cells, an event that took over 1 billion years to occur on Earth, and may be the true bottleneck for biological complexity in the cosmos. If this is the case, then we are truly alone, the sole conscious heirs to a silent cosmos, and the silence is a measure of our incredible rarity. The far more disturbing possibility is that the great filter lies in our future. In this scenario, the development of intelligent, tool-using life might be relatively common, but the next step, the transition to a stable, enduring technological civilization, is the one that is nearly impossible to survive. The filter, then, would be us. It could be our own self-destructive tendencies. The period in which a civilization possesses the technology for global communication and spaceflight might also be the same period in which it possesses the technology for its own annihilation. We have already lived for decades under the threat of nuclear winter. Perhaps every civilization eventually discovers a technology that is too powerful for its own political and social maturity to handle, and most succumb to it. Or the filter could be something we haven't even encountered yet, a runaway climate catastrophe, a pandemic engineered through advanced biotechnology, or the unforeseen consequences of artificial intelligence. The silence of the galaxy, in this view, is a graveyard. It is the sound of countless civilizations that flashed into technological brilliance and then, just as quickly, flickered out. We are listening to the echo of their absence, a warning from the cosmic blueprint that the most dangerous step in evolution may be the one we are taking right now. We can find sobering parallels for this kind of existential collision right here on Earth. Consider the historical encounters between advanced European explorers and isolated indigenous civilizations. To the people of the Americas, the arrival of Spanish ships on the horizon was, for all intents and purposes, the arrival of an advanced extraterrestrial civilization. The technological gap was so vast that the very existence of the newcomers was initially incomprehensible. The result was not a meeting of equals, but a catastrophic collapse for the less technologically advanced society, brought down by a combination of disease, military technology, and social disruption. This historical analogy gives rise to another potential solution to the Fermi Paradox, the dark forest hypothesis. This chilling idea, popularized in science fiction, suggests that the universe is like a dark forest full of hidden hunters. Every civilization is a hunter moving through the trees like a ghost, because it is impossible to know if another civilization will be benevolent or predatory. The only safe strategy is to stay quiet, to remain hidden, and to preemptively destroy any other life that reveals itself. In such a universe, the silence is not a sign of emptiness, but of supreme caution. The civilizations that survive are the ones that make no sound, and the reason we don't hear anyone is that everyone who was loud is already gone. Other, less grim explanations involve not fear, but transcendence. Perhaps civilizations do not die, they simply evolve beyond our ability to perceive them. Within a few centuries of developing advanced technology, a species might learn to upload its consciousness into a simulated reality, a digital existence so engrossing that the physical, external universe becomes irrelevant. Or they might transition into a post-biological state, becoming forms of pure energy or information that we simply cannot detect with our current instruments. Their projects might not be radio broadcasts or Dyson spheres, but manipulations of space-time or quantum fields on a scale we cannot yet fathom. Another intriguing idea is the zoo hypothesis, which proposes that advanced civilizations are fully aware of us, but have chosen to place our world off-limits, a protected galactic wildlife park where we are allowed to develop naturally without interference. They observe us from a distance, following a strict prime directive, waiting for us to reach a certain level of maturity before making contact. The silence, in this case, is a form of respect for our cultural and biological autonomy. So, what does this grand enigma ultimately tell us? Does the Fermi Paradox hint at humanity's profound uniqueness, a lonely beacon of consciousness in a vast, empty ocean of stars? Or is it a stark warning of an impending challenge, a developmental bottleneck that we must navigate with immense wisdom and foresight if our civilization is to have a long-term future? The answer to this question fundamentally shapes our perspective on our own destiny. If we are alone, then the entire, breathtaking cosmos is our inheritance, and we have a sacred responsibility to cherish and preserve the flame of consciousness. If we are not alone, but the great filter awaits us, then our every action today is a test, a race to achieve global maturity before we trigger our own demise. The paradox forces us to look in the mirror and ask not only where are they, but who are we and who do we want to become? It transforms the search for extraterrestrial intelligence into the most profound exercise in self-examination. This contemplation of our place in a seemingly silent universe and the potential challenges that might explain that silence naturally propels our gaze forward to the active role we might one day play in shaping our cosmic environment and forging our own destiny among the stars. Picture this, a bustling city under a pinkish-orange sky, where geodesic domes house laboratories and living quarters, and astronauts in advanced suits tend to hydroponic gardens under the light of a distant pale sun. This is not science fiction. It is a plausible vision of a future human colony on Mars, a stepping stone in our species' next great migration. For the first time in our history, we are developing the technology not just to visit other worlds, but to live on them, to establish a permanent foothold beyond the Earth. This journey of expansion, from lunar outposts to interstellar generation ships that would carry entire civilizations on voyages lasting centuries, represents a fundamental shift in our relationship with the cosmos. We are evolving from being mere observers of the cosmic blueprint to becoming active participants, agents who can test its principles, manipulate its materials, and perhaps one day even rewrite its local clauses. The legendary Russian rocket scientist Konstantin Tsiolkovsky foresaw this moment over a century ago when he wrote, "The Earth is the cradle of humanity, but one cannot live in the cradle forever." His words are a profound call to action, a reminder that our biological and cultural destiny may be inextricably linked to leaving our planetary home and venturing into the vastness that surrounds it. This grand endeavor is far more than an adventure. It is the ultimate test of our understanding of the cosmic blueprint itself. Every rocket launch, every rover mission, and every experiment conducted in the microgravity environment of the International Space Station is a live-fire exercise in applied physics. When we grow crystals or study fluid dynamics in orbit, we are observing how the universe's fundamental laws behave when one of its most persistent forces, Earth's gravity, is removed. This allows us to see the pure, unadulterated effects of other physical principles, leading to breakthroughs in material science and medicine. Planetary science offers another profound test. By sending probes to the hellish surface of Venus, the frozen deserts of Mars, or the methane lakes of Titan, we are conducting comparative planetology. We are asking the universe to show us other outcomes of the same basic processes that shaped our own world. Did Mars ever have a stable magnetic field? And what does its loss tell us about the necessity of such a field for long-term habitability? The geology of these other worlds provides a control group, a way to check if our theories about planetary formation and evolution, derived from a single data point, Earth, hold true across the solar system. Each mission is a question posed to the cosmos, and the data we get back helps us refine our reading of the universal instructions. As our ambitions grow, so too does the scale of our potential interventions, moving from exploration to a concept known as cosmic engineering. This is the application of technology on a planetary or even stellar scale, a proactive attempt to reshape our cosmic environment to suit our needs. The most iconic example is the Dyson sphere, a hypothetical megastructure first proposed by physicist Freeman Dyson. The idea is that an advanced civilization would eventually need to harness the entire energy output of its star. This would involve constructing a vast swarm of orbiting solar collectors that would completely encapsulate the star, capturing its light and converting it into usable power. While building such a structure is far beyond our current capabilities, the underlying principle, the need to manage energy resources on a civilization scale, is a logical extension of our current technological trajectory. It represents a vision of humanity becoming a truly interstellar species, one that has learned to build with suns and planets rather than just wood and stone. A more near-term and deeply debated form of cosmic engineering is terraforming, the process of deliberately altering a planet's atmosphere, temperature, and ecology to make it habitable for Earth-like life. Mars is the most frequently discussed candidate. The process might begin with thickening its atmosphere by releasing carbon dioxide frozen at the poles, using orbital mirrors to melt the ice caps and initiate a greenhouse effect. This could raise the temperature and pressure enough for liquid water to flow again. The next phase could involve introducing specially engineered microbes and plants to begin producing oxygen, slowly transforming the red planet into a green one over the course of centuries or millennia. The technological challenges are staggering, requiring a mastery of planetary systems we do not yet possess. But the ethical considerations are even more profound. Do we have the right to fundamentally alter another world, especially one that might harbor its own as yet undiscovered microbial life? Is it an act of hubris to impose an Earth-like biosphere on a planet that has followed its own unique evolutionary path for billions of years? Or is it our moral imperative to spread life, to create a second Genesis and ensure that the flame of consciousness is not extinguished by a single catastrophe on our home world? This is not just an engineering problem. It is a philosophical crossroads that forces us to define our role in the cosmos. Are we gardeners or conquerors? We are already laying the practical groundwork for this future, moving from blueprints to launch pads. NASA's Artemis program aims to return humans to the moon, not just for flags and footprints, but to establish a sustainable presence. The Lunar Gateway, a small space station in orbit around the moon, will serve as a staging post for sorties to the surface, where we will learn how to live and work using local resources, a practice called in situ resource utilization. The ultimate goal is to mine water ice from permanently shadowed craters, which can be split into hydrogen for fuel and oxygen for air, making the moon a refueling depot for deeper space missions. Simultaneously, private companies like SpaceX are developing entirely new classes of vehicles, such as the Starship spacecraft. Designed to be fully and rapidly reusable, Starship represents a paradigm shift in space access, with the explicit goal of carrying large numbers of people and massive amounts of cargo to Mars. These are not isolated projects. They are the opening chapters of a coordinated, multi-decade effort to make humanity a multi-planetary species. They are the first, tangible steps toward taking control of our cosmic destiny. This brings us to a pivotal, reflective question that sits at the heart of our expanding presence in space. Should our primary goal be to alter other worlds to suit us, or to preserve them as pristine natural laboratories? On one hand, the preservationist argument holds immense weight. Worlds like Mars are unique records of solar system history, offering invaluable scientific insights into planetary formation, climate change, and the potential for life. By terraforming Mars, we would destroy that pristine record forever. It would be akin to paving over the Galapagos Islands before Darwin could study them. We might be obliterating scientific treasures before we even understand their value. These untouched environments are the ultimate controls in the great experiment of our solar system, and once changed, they are changed irrevocably. On the other hand, the humanist argument posits that the survival and flourishing of humanity is the highest good. If we confine ourselves to one vulnerable planet, we risk total extinction from any number of threats: asteroid impacts, supervolcanoes, or our own self-inflicted crises. In this view, other worlds are not museums to be looked at, but new frontiers to be settled and transformed into homes. They are the key to our long-term survival and evolutionary progress. There may be a middle path where we establish limited, contained habitats on these worlds, like biodomes or underground cities, minimizing our impact on the global environment while still securing a future for our civilization beyond Earth. The choice we make will define our character as a spacefaring species for generations to come. But there is another, even more profound arrow that seems to be woven into the very fabric of our reality, and it's one we experience every single moment: the relentless, one-way flow of time. Think about it for a second. Why do we remember the past with such clarity, but have absolutely no access to the future? Why does a shattered glass never spontaneously reassemble itself on the floor? This is the puzzle of time's arrow, a fundamental asymmetry that stands in stark contrast to the laws of physics themselves. At the level of individual particles, the equations that govern their behavior, whether Newton's laws, Einstein's relativity, or quantum mechanics, are almost entirely time-symmetric. They work just as well if you run the film of the universe backward. A planet orbiting a star in reverse still follows a perfect elliptical path, but our actual experience of the cosmos is utterly different. The film only plays in one direction, and the reason for this is one of the most profound connections between the cosmic blueprint and our everyday lives. The key that unlocks this mystery is a concept from thermodynamics known as entropy. In simple terms, entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time or at best remains constant. It never spontaneously decreases. This is the physical principle behind why your room gets messy if you don't clean it, why perfume diffuses to fill a room and never collects back into the bottle, and why a hot cup of coffee left on a table will always cool down to room temperature, never spontaneously heat up. The universe, on the whole, is moving from a state of order to a state of disorder. This relentless increase in entropy gives time its unmistakable direction. It is the reason we can distinguish the past from the future. The great astronomer and physicist Sir Arthur Eddington was the one who powerfully crystallized this idea, stating that the arrow of time is the most fundamental property of the universe which physics has yet revealed. He insisted that this thermodynamic arrow is not just a human perception, but a fundamental, objective feature of the cosmos, inscribed directly into the cosmic blueprint. So, if the second law of thermodynamics dictates the arrow of time, we are immediately led to a deeper cosmological question. Why was the entropy of the universe so incredibly low in the first place? Why did our cosmic story begin in a state of such exquisite order? The ultimate source of time's arrow, it seems, is written on the very first page of our universal history, in the initial conditions of the Big Bang. The early universe was in a state of extremely low entropy. It was hot, incredibly dense, but also remarkably smooth and uniform. This might sound counterintuitive. We often think of a smooth mixture as being disordered. But in gravitational terms, a smooth, dense soup of matter and energy is actually a state of very low entropy. High entropy for gravity is a state where matter is clumped together into black holes, the most disordered objects conceivable. The Big Bang started the universe off in a very special, low entropy state, like a perfectly wound-up spring or a pristine, unshuffled deck of cards. From that moment on, the only way for entropy to go was up. The universe has been unwinding, shuffling itself, and moving toward greater disorder for the past 13.8 billion years. This cosmological arrow set by the Big Bang is what drives the thermodynamic arrow we see in our daily lives. Our ability to remember the past but not the future is therefore a direct consequence of the universe's low entropy beginning. If the universe had started in a state of maximum entropy, a featureless high-temperature equilibrium, there would be no increase in disorder, no flow of energy, and arguably no clear direction to time at all. This relationship between entropy and gravity leads us to some of the most extreme environments in the cosmos: black holes. Black holes are, in a sense, the ultimate manifestation of entropy. They are objects where matter has reached its most disordered, high-entropy state possible within a given volume. According to the work of Jacob Bekenstein and Stephen Hawking, the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This was a revolutionary idea, suggesting that the maximum amount of information or disorder a region of space can contain is defined by its boundary. Hawking also showed that black holes aren't completely black. They slowly radiate energy and evaporate over astronomical timescales through a quantum process. This Hawking radiation carries entropy away, and as a black hole evaporates, the total entropy of the universe continues to increase, perfectly obeying the second law. The life cycle of a black hole, from its formation in a supernova to its eventual evaporation, is a powerful testament to the dominion of the arrow of time, even in the most warped regions of space-time. The existence and properties of black holes are not an exception to the rule of increasing entropy. They are its most dramatic and conclusive evidence. To truly grasp the strangeness of a world without a clear time's arrow, imagine watching a movie of everyday life played in reverse. In the forward version, you see a diver leap from a diving board, sending splashes of water upward as they enter the pool. In reverse, you would see scattered droplets of water from the pool suddenly and spontaneously fly together, merging into a coherent splash just as the diver is ejected perfectly feet first from the water, landing gracefully back on the board. Your brain immediately recognizes this as wrong. The reversed movie violates the second law of thermodynamics. The disordered, scattered water droplets represent a higher entropy state than the collected body of water in the pool. For them to spontaneously organize and propel the diver upward requires a dramatic and impossible decrease in entropy. This intuitive feeling of wrongness is your brain detecting the arrow of time. It is your consciousness aligning with the fundamental cosmic drift from order to disorder that began at the Big Bang. This exploration inevitably pushes our curiosity beyond the confines of our own universe. Could the arrow of time be different elsewhere? In other bubble universes within a vast multiverse, the initial conditions might have been completely different. Perhaps some universes began in a state of maximum entropy, where time has no inherent direction and the concepts of cause and effect are meaningless. In others, the arrow might point in the opposite direction from our own, though what that would mean for consciousness is almost impossible to fathom. Would beings in such a universe remember their future and anticipate their past? Even within our own universe, under the most extreme conditions, the nature of time might be challenged. At the quantum level, for individual particles, the distinction between past and future can become blurred, and some speculative theories suggest that inside the event horizon of a black hole, the roles of space and time might fundamentally switch, though this remains a topic of intense theoretical debate. The arrow of time, so fundamental to our existence, may not be a universal constant, but rather a local byproduct of our universe's very specific and very ordered beginning. This profound connection between the large-scale structure of the cosmos and our most intimate experience of reality, the flow of time, naturally draws us into an even deeper mystery: the role of the conscious mind itself in observing and interpreting this grand cosmic narrative. But this exploration of time's arrow, a direction dictated by the cosmos's initial conditions, inevitably leads us to a puzzle that is even more intimate and perplexing. Who or what is actually experiencing this flow? We arrive at the enigmatic role of the conscious observer, the eye that perceives the universe and, in a very real sense, brings it into being for itself. For centuries, we considered consciousness a mere byproduct, a ghost in the machine of the brain. But at the frontiers of both quantum physics and cosmology, a radical idea is gaining traction: that consciousness might not be a passive passenger in the cosmos, but an active participant, an integral component written into the cosmic blueprint itself, without which the universe cannot be fully understood or even said to be fully real. This notion finds one of its most provocative expressions in the world of quantum mechanics. You've likely heard of the famous double-slit experiment, where particles like electrons behave as waves when not observed, creating an interference pattern on a screen, but mysteriously collapse into definite particles the moment a measuring device or an observer is present. This measurement problem has baffled physicists for a century. What exactly constitutes a measurement? Is it the physical apparatus, or is it the entry of the result into a conscious mind? The legendary physicist John Wheeler took this idea to its ultimate conclusion with his concept of a participatory universe. He proposed that we are not just bystanders on a cosmic stage that would exist with or without us. Instead, through the very act of observation and measurement, we bring the universe into existence. In his own words, we are not just observers, but participators. In one of his most famous thought experiments, the delayed choice experiment, Wheeler showed that an observer's decision in the present can seemingly influence the past behavior of a particle. This suggests that the universe's history is not fixed and immutable, but is somehow created in a backward-reaching way by the questions we choose to ask of it today. It's a dizzying idea that the cosmos only achieves concrete reality when it is observed by a conscious being, implying that consciousness is a fundamental force in shaping the very fabric of existence. This perspective from hard science finds a strange and beautiful echo in the realm of depth psychology. Carl Jung, the pioneering Swiss psychiatrist, spent his life exploring the collective unconscious, a deep, shared layer of the human psyche that he believed was a gateway to the cosmos itself. Jung saw a profound resonance between the inner world of dreams, symbols, and archetypes, and the outer structure of the physical universe. He famously collaborated with physicist Wolfgang Pauli in an attempt to bridge psychology and physics, searching for a unifying principle they called synchronicity, meaningful coincidences that defy causal explanation but seem to link the inner state of the observer with an outer event in the world. Jung wrote that the psyche is the greatest of all cosmic wonders, and he suspected that the human mind was not a separate entity looking at the universe, but an expression of it. For Jung, the act of decoding the cosmic blueprint was not just a scientific endeavor. It was a process of profound self-discovery, where understanding the stars and understanding the soul were two sides of the same cosmic coin. If consciousness is indeed so central, what is its fundamental nature? One of the most ancient and resurgent philosophical answers is panpsychism. This is the view that consciousness is not a late-arriving product of complex biological computation, but a fundamental and ubiquitous feature of the universe, much like mass or charge. In this view, everything, from an electron to a human being to a galaxy, possesses some form of inner experience, however simple or complex. A rock's experience would be unimaginably faint and basic, a mere whisper of subjective feeling, while a human brain, with its immense complexity, orchestrates these fundamental conscious units into the rich symphony of our thoughts, emotions, and sensations. Panpsychism offers an elegant, if speculative, solution to the so-called hard problem of consciousness. The question of why and how physical processes in the brain give rise to subjective, first-person experience. If consciousness is already a fundamental property of matter, then the problem shifts from creating it from scratch to simply explaining how it gets organized and amplified. A more modern, computationally oriented theory that attempts to tackle this organization is integrated information theory, or EIT. Developed by neuroscientist Giulio Tononi, IIT proposes that consciousness is not about what a system is made of, but how its components are interconnected. The central claim is that consciousness corresponds to a system's ability to integrate information. The more a system can generate a large number of different states through the complex, causal interactions of its parts, and the more unified or integrated that system is, the higher its level of consciousness, measured by a value called phi. A human brain, with its trillions of densely interconnected neurons, has a very high phi, a digital camera sensor which may process a lot of information but in a simple, linear way with little integration between pixels, has a very low phi. According to IIT, even simple systems like a thermostat or a photodiode could have a minuscule, non-zero amount of consciousness because they integrate at least some information. This theory provides a potential bridge between the physical structure of a system and the quality of its subjective experience, suggesting that the intricate networks of the brain are so conscious because they mirror, in their own way, the immense informational complexity of the cosmos they are trying to model. We don't need to look to speculative physics or complex mathematics to find evidence that consciousness can profoundly alter our perception of the cosmic blueprint. We can see it in the direct personal experiences of altered states. Consider the profound shifts in awareness reported during deep meditation. Long-term practitioners often describe a dissolution of the boundary between the self and the external world. The sense of being a separate observer inside a skull, looking out at a distant universe, vanishes. It is replaced by a feeling of unity where the observer and the observed merge. Time may seem to slow down, stop, or become irrelevant. Space can feel expansive and interconnected. In this state, the cosmos is not an external object to be studied, but is experienced as the very ground of one's own being. Similarly, certain psychedelic experiences, induced by substances like psilocybin or DMT, can produce overwhelming sensations of cosmic connectedness, the perception of intricate geometric patterns underlying reality, and a complete breakdown of linear time. People often report encountering seemingly intelligent, otherworldly entities or feeling that they have accessed a more fundamental layer of existence. While neuroscience can point to changes in brain activity like decreased default mode network function during these states, the subjective reports consistently point toward a reality where consciousness is not locked inside the head, but is a flexible, permeable field that can directly interface with the architecture of the cosmos itself. These experiences, while subjective, challenge the materialist view that the brain creates consciousness, and instead hint that the brain might be more like a receiver or a filter, tuning into a consciousness that is already everywhere. All of this evidence and speculation forces upon us the ultimate metaphysical question: is consciousness an emergent property or a fundamental one? The standard scientific materialist view is that consciousness is an emergent phenomenon. It is a novel property that arises when matter organizes itself into systems of sufficient complexity, specifically the 100 billion neurons and their quadrillion connections in the human brain. In this view, the brain creates the mind just as a complex computer runs sophisticated software. The cosmos was here first, blind and unconscious, and we are a beautiful, temporary accident within it. The alternative, far more radical view is that consciousness is fundamental. It is a primary ingredient of reality, perhaps even the primary ingredient, with the physical universe emerging from it. This is the core of the idealist philosophy, which turns materialism on its head. In this view, the world of atoms, forces, and galaxies is a manifestation of a deeper, conscious reality. The cosmic blueprint, then, is not just a set of physical laws, but a set of ideas in a cosmic mind. Our individual consciousnesses are not generated by our brains, but are localized expressions of this universal consciousness, temporarily focused through the lens of our biological apparatus. So, where does this leave us in our grand quest to decode the cosmic blueprint? It suggests that the ultimate mystery may not be the universe itself, but the fact that there is something it is like to be the universe, and that we are that very something. The act of observation, of questioning, of feeling awe under a starry sky is not a trivial side effect of evolution. It may be the cosmos's most sophisticated tool for understanding its own nature. We are not just readers of the blueprint, we are the means by which the blueprint becomes aware of its own existence. This profound shift in perspective, from a universe of dead matter to a universe alive with the potential for mind, transforms our entire journey. It bridges the unbridgeable gap between the objective and the subjective, suggesting that the laws of physics and the nature of experience are two different languages describing the same unified reality. And with this mind-bending realization that the observer is woven into the very fabric of the cosmos, we are compelled to ask, how do we, with our limited senses and mortal minds, actually go about the practical business of reading this grand design? This leads us directly to the incredible tools we have built to extend our perception, the magnificent telescopes and observatories that act as our prosthetic eyes, allowing us to see further back in time and deeper into the hidden layers of reality than we ever thought possible. Our ability to decipher the grand cosmic design is only as powerful as the tools we use to observe it, and the story of astronomy is in many ways the story of an ever-expanding sense of sight. It began in a small room in Padua in 1609, when Galileo Galilei first pointed his handmade spyglass, a humble tube with two pieces of ground glass, toward the heavens. That simple instrument, no more powerful than a modern pair of binoculars, shattered an ancient worldview. Suddenly, the moon was not a perfect, smooth sphere, but a world with mountains and craters. Jupiter was not a wandering point of light, but a miniature solar system with its own orbiting moons. With that single act, Galileo initiated a revolution, proving that the cosmic blueprint could be read not just with the naked eye and philosophical speculation, but with engineered instruments that extended human perception. Each subsequent leap in technology has been like being given a new set of eyes, allowing us to see deeper into space, further back in time, and into entirely new, invisible layers of the electromagnetic spectrum, revealing a universe far stranger and more wonderful than we ever imagined. The journey from Galileo's modest optic to the colossal observatories of today is a testament to our relentless curiosity. For centuries, larger and more finely crafted glass lenses and mirrors in optical telescopes allowed us to map the solar system, measure the distances to stars, and finally, to see that the faint, fuzzy spirals in the sky were not nebulous clouds but entire island universes, galaxies beyond our own. This monumental discovery was championed by Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in the 1920s. It was Hubble who provided the observational proof that the universe is expanding, fundamentally rewriting our cosmic story. He understood the transformative power of these instruments, famously stating that the telescope is essentially a machine for making discoveries, a key to unlock the mysteries of the universe. His words capture the essence of all astronomical tools. They are not merely magnifying glasses, but keys that open doors to realms of reality previously hidden from us, allowing us to read chapters of the cosmic blueprint we never knew existed. Today, we no longer rely on a single type of key. We have built a whole keychain, with each observatory designed to read a specific part of the cosmic code. Optical telescopes, like the Keck Observatory in Hawaii or the Hubble Space Telescope in orbit, continue to show us the universe in the familiar light of stars and galaxies, but with breathtaking clarity. The Hubble, for instance, free from the distorting effects of Earth's atmosphere, has provided iconic images of stellar nurseries and deep fields of galaxies, peering back over 13 billion years into the past. But the visible light we see is just a tiny sliver of the full cosmic story. To understand the most energetic and violent processes, we need to see the universe in X-rays. Observatories like NASA Chandra X-ray Observatory gaze at the searing hot gas in galaxy clusters, the frenetic environments around black holes, and the remnants of supernova explosions, where temperatures reach millions of degrees. It was Chandra that mapped the shockwaves from the Crab Nebula, the scattered debris of a star that exploded in 1054, showing us the dynamic and often violent nature of cosmic evolution. Then there are the radio telescopes, which listen to the long wavelength whispers of the cosmos. These vast dishes, like the now collapsed Arecibo in Puerto Rico or the sprawling Olma array in the high Chilean desert, detect radiation that is completely invisible to our eyes. They have been instrumental in some of the most profound discoveries of the last century. It was radio astronomy that first detected the faint hiss of the cosmic microwave background, the afterglow of the Big Bang. Today, radio telescopes are at the forefront of the search for exoplanets, not by seeing them directly, but by detecting the tiny wobbles they induce in their parent stars. They have even allowed us to see the shadow of a supermassive black hole at the heart of the galaxy M87 by synchronizing a global network of radio dishes to create an Earth-sized virtual telescope with unprecedented resolution. Each part of the spectrum reveals a different dimension of the blueprint. Optical light shows us the structure of galaxies, X-rays show us their violent energy, and radio waves reveal their cold, dark components and their ancient origins. Perhaps the most stunning recent demonstration of this multi-wavelength approach is the James Webb Space Telescope, or JWST. As the spiritual successor to Hubble, JWST is not just an improvement, it is a fundamental shift in capability. Designed primarily to see in the infrared part of the spectrum, its mirrors are tuned to detect the heat signature of the most distant and ancient objects in the universe. Why is this so crucial? Because as the universe expands, the light from the very first stars and galaxies is stretched on its long journey to us. This cosmological redshift shifts their light out of the visible spectrum and into the infrared. JWST is essentially a powerful time machine, built to see the era when the cosmic blueprint was first assembling galaxies from the primordial darkness. Its early observations have already delivered shocking results, revealing fully formed, massive galaxies at a time when theorists thought they should barely be beginning to form. This is not just a new discovery, it is a challenge to our existing models, forcing us to reconsider the timeline of cosmic structure formation and potentially rewrite a section of the blueprint we thought we understood. But our quest to read the universe's secrets has moved beyond just collecting light. We are now entering the era of multi-messenger astronomy, where we observe the cosmos not only with photons but with other, more exotic messengers. The most dramatic example is the detection of gravitational waves, ripples in the fabric of spacetime itself, predicted by Einstein a century ago. Instruments like LIGO in the United States and Virgo in Italy are not telescopes in any conventional sense. They are incredibly precise laser interferometers, capable of measuring distortions in spacetime thousands of times smaller than an atomic nucleus. When two black holes or neutron stars spiral into each other in a distant galaxy, they create a violent storm in spacetime that travels across the universe at the speed of light. In 2017, LIGO and Virgo detected the ripples from such a collision, and within moments, telescopes around the world and in space swiveled to observe the same event in gamma rays, X-rays, and visible light. This coordinated effort marked the first time we had heard the universe with gravity and seen it with light simultaneously, confirming a key prediction of general relativity and opening up an entirely new sense with which to perceive the cosmos. Our sensory reach now extends to even more elusive cosmic messengers, deep underground, in abandoned mines and tunnels shielded from cosmic rays. enormous detectors like Supercamioc, and in Japan and IceCube at the South Pole are waiting. They are not looking for light, but for neutrinos, ghostly subatomic particles that stream through the Earth almost completely unimpeded. Born in the hearts of stars, in supernova explosions, and in the violent environments around black holes, neutrinos carry information directly from these otherwise opaque engines. When a neutrino rarely interacts with the water or ice in these colossal tanks, it produces a tiny flash of light that sensors can detect, telling us a story about the cataclysmic events that created it. By combining the data from optical telescopes, radio arrays, X-ray observatories, gravitational wave detectors, and neutrino telescopes, we are no longer just looking at the universe. We are listening to it, feeling its vibrations, and sensing its most elusive particles. We are building a complete, multi-sensory picture of cosmic reality, reading the blueprint in all its dimensions. This incredible technological evolution, from a simple tube of lenses to a global network of sensors, fundamentally extends our biological senses into realms that were once the sole province of theory and imagination. We have built prosthetic eyes that can see the heat of infant galaxies, prosthetic ears that can hear the ring of colliding black holes, and prosthetic touch that can feel the ghostly passage of neutrinos. Each new instrument does not just provide more data, it reveals a new layer of the cosmic narrative, often challenging our preconceptions and forcing a revolution in thought. The tools we create to read the blueprint inevitably end up rewriting it, as each new window we open onto the cosmos shows us a reality that is richer, more dynamic, and more surprising than we had previously dared to believe. This ever-deepening observational prowess, this constant refinement of our cosmic senses, provides the raw, empirical fuel for the next stage of our quest, building virtual universes inside supercomputers to test our understanding against the magnificent complexity we observe. Imagine a laboratory that is not a room with beakers and microscopes, but a vast, silent hall filled with towering black monoliths, their blinking lights the only sign of an immense, silent calculation unfolding. Inside these supercomputers, not chemicals, but countless lines of code are mixing together, simulating the birth of an entire universe. This is the frontier of computational cosmology, a field where we don't just observe the cosmos or theorize about it. We build digital copies of it, creating virtual universes from the ground up to test our deepest ideas about the cosmic blueprint. These aren't simple animations. They are breathtakingly complex models that take the known laws of physics, the recipe of dark matter and dark energy, and the initial conditions from the cosmic microwave background, and then set a digital clock running from the Big Bang forward over 13 billion years. The goal is audacious, to see if our understanding of the universe's rules can successfully grow a virtual cosmos that looks, in every meaningful way, just like the one we actually live in. If the simulated galaxies, clusters, and cosmic web match the maps we've made with our telescopes, we know we're on the right track. If they don't, the simulation itself becomes a powerful diagnostic tool, highlighting exactly where our theories are broken or incomplete. Pioneering projects like the Millennium Simulation and its even more sophisticated successors, such as Illustris TNG and Eagle, have been doing precisely this for decades. The original Millennium Simulation, run in 2005, was a landmark achievement. It traced the evolution of more than 10 billion particles representing dark matter within a virtual cube of space over 2 billion light-years on a side, from the early universe to the present day. When the scientists first ran the simulation and saw the results, they watched in awe as a cosmic web emerged spontaneously from the initial, smooth conditions. Vast filaments of dark matter stretched across the digital void, connecting at dense nodes where huge galaxy clusters formed, while immense, empty bubbles of void space opened up between them. It was a stunning confirmation that the simple ingredients of the standard model of cosmology, dark matter, dark energy, and the initial seeds from inflation were indeed sufficient to generate the large-scale architecture we observe. The more recent Illustris TNG project took this a giant step further by incorporating not just dark matter, but also the complex physics of ordinary matter, the gas, stars, and supermassive black holes that make up the visible universe. This allowed the simulation to model the feedback loops where exploding supernova and voracious black holes blast energy back into their surroundings, shutting down star formation in massive galaxies and painting a far more realistic and dynamic portrait of cosmic evolution. The cosmologist Carlos Frenk, a key figure in this field, has eloquently described these virtual universes as laboratories for the 21st century. He points out that in most sciences you can test your ideas with experiments. You can mix chemicals in a lab or smash particles in an accelerator. But in cosmology, we only have one universe and we can't rewind it or change its parameters to see what happens. These supercomputer simulations are the next best thing. They are our cosmic test beds. As Frenk explains, we are creating universes in a computer, not by magic, but by implementing the laws of physics as we know them. We can run the simulation over and over again, each time tweaking a single variable, perhaps making dark matter interact with itself slightly, or changing the strength of supernova explosions, and then see how that altered universe turns out. Does it produce too many dwarf galaxies? Do its spiral galaxies have the right ratio of stars to gas? By comparing these alternate realities to our own, we can perform a kind of cosmic forensics, zeroing in on the exact physical laws that must be in place to produce a universe that looks like ours. The inner workings of these digital universes are a marvel of modern computational physics. The simulations begin by defining a vast, three-dimensional grid representing a chunk of space. Onto this grid, they place trillions of virtual particles. The majority of these represent dark matter, which feels only gravity. The complex dance of these dark matter particles, pulled together by their own gravity, is what first sketches out the cosmic web, forming the invisible scaffolding of the universe. Then the simulations add the layer of baryonic or ordinary matter. This is where the physics becomes immensely more complicated, requiring a branch of physics called hydrodynamics to model the behavior of gases. The code must account for a staggering array of processes. It tracks how gas cools and condenses under gravity to form stars. It models the nuclear fusion within those stars and their eventual explosive deaths as supernova, which spew newly forged heavy elements back into space. It even simulates the growth of supermassive black holes at the centers of galaxies and the colossal jets of energy they can launch, which heat up surrounding gas and prevent further star formation. All of these processes are interconnected in a delicate feedback loop, and getting the balance right is the key to creating a simulation that doesn't just look like our universe in broad strokes, but accurately reproduces its fine details. The ultimate validation for any simulation comes from a direct point-by-point comparison with the real, observed universe. Scientists use a variety of powerful methods to check their work. They compare the statistical properties of the simulated cosmic web, the thickness of its filaments, and the size distribution of its voids, to the maps created by galaxy surveys like the Sloan Digital Sky Survey. They analyze the simulated galaxy clusters, checking if their masses, temperatures, and internal structures match what we see with X-ray telescopes like Chandra. They even look at the demographics of galaxies, ensuring that the virtual universe produces the correct mix of spiral and elliptical galaxies, and that these galaxies follow observed relationships, like the correlation between a galaxy's mass and the mass of the supermassive black hole at its heart. A successful simulation isn't just one that looks pretty, it's one that passes hundreds of these rigorous quantitative tests. When a simulation like Illustris TNG can reproduce the observed distribution of elements throughout the universe or the way galaxies are clustered at different epochs, it gives us profound confidence that the underlying physics in the model, the core of our cosmic blueprint, is essentially correct. To make this abstract process more concrete, consider what these simulations actually show us. In the dark matter-only runs, we see a universe of pure structure. Dark matter halos, roughly spherical clumps of this invisible material, emerge as the fundamental building blocks. Every galaxy we see, from a tiny dwarf to a giant spiral like our Milky Way, is embedded within one of these dark matter halos. Their gravity is what provides the initial pull to gather the gas that will eventually form stars. When we look at the visualizations, these halos appear as glowing, interconnected nodes in a vast cosmic neural network. When the physics of gas is added, the simulations come alive with color and dynamism. We can watch as thin, wispy filaments of gas, tracing the dark matter scaffolding, light up with the brilliant blue-white glow of newly formed stars. We can see galaxy collisions in stunning detail, watching as the gravitational tides pull long streams of stars from the merging galaxies, creating the beautiful tidal tails we observe in real interacting pairs like the mice galaxies. We can even zoom in on a single, virtual spiral galaxy and watch its disk rotate, its spiral arms winding and unwinding over billions of years, a digital twin of our own Milky Way, born from nothing but mathematical rules and initial conditions. This incredible power to create and manipulate entire cosmos inevitably leads us to a dizzying and profound philosophical question, one that has been explored in science fiction for generations but is now being seriously considered by scientists and philosophers. If we can create a universe so realistic that it is for all intents and purposes indistinguishable from our own, could that simulate universe one day host conscious beings within it? And if so, what would that imply about the nature of our own reality? This is the core of the simulation hypothesis. The logic runs that if a civilization ever reaches a level of technological maturity sufficient to run such detailed simulations, it would likely run not just one, but a vast number of them, perhaps as scientific experiments or for entertainment. In that case, the number of simulated conscious beings would vastly outnumber the beings in the original, base reality. Therefore, statistically speaking, it is more likely that we are living in one of these many simulations than in the one original reality. This is a modern, technological twist on age-old philosophical questions about the nature of existence, but it is given weight by the very real and rapidly advancing simulations we are building today. The implications of this possibility are staggering. It would mean that the laws of physics we are so painstakingly trying to decode are not the fundamental laws of a base reality, but merely the programmed parameters of the simulation we are running in the local bylaws of our particular digital universe. The puzzling fine-tuning of the constants of nature could be explained not by a multiverse or a designer, but by the fact that a programmer simply dialed in those specific values to allow for complexity and life to arise. Even the weirdness of quantum mechanics, with its probabilities and observer-dependent outcomes, could be seen as a clever optimization technique to save on computational resources, only rendering the fine details of reality when they are being observed. This line of thinking pushes our digital exploration of the cosmic blueprint to its ultimate meta-cosmic conclusion, suggesting that the universe we are trying to understand may not be a fundamental physical system at all, but an incredibly sophisticated information processing system. The very fabric of space-time and the particles within it might not be the bedrock of reality, but merely the user interface of a cosmic computer whose true nature is pure data and computation. So after we've simulated the universe inside our mightiest supercomputers, a truly radical thought emerges. What if the universe itself is, in the most fundamental sense, a computer? Not a computer made of silicon and wires, but a cosmic-scale information processor, where reality itself is computed into existence. This is the startling proposition at the heart of information theory applied to cosmology, the idea that the most basic building block of everything is not energy or matter, but information. Think of the universe not as a collection of swirling galaxies and particles, but as a vast dynamic data structure. Every electron's spin, every photon's path, every curvature of spacetime could be, at its core, a bit of information, a binary yes or no answer to a fundamental question about the state of existence. In this view, the cosmic blueprint isn't written in the language of mathematics alone. It is written in the universal language of code, a cosmic software running on the hardware of reality. The formal foundation for this idea comes from the work of Claude Shannon in the 1940s. Shannon was trying to solve a practical problem: how to send messages clearly over a noisy telephone line. In the process, he invented the concept of information entropy. For Shannon, entropy wasn't about disorder in the thermodynamic sense, but about uncertainty. It measures the amount of surprise or information content in a message. A string of perfectly predictable letters has low information entropy. It's boring and tells you nothing new. A completely random jumble of characters has high information entropy, but it's also meaningless noise. The sweet spot is in between, a structured message that conveys surprising, novel information. When we apply this concept to the universe, a profound connection emerges. The thermodynamic entropy that defines the arrow of time and the information entropy that defines communication seem to be two sides of the same coin. To erase a single bit of information in a computer, it turns out, requires a tiny increase in thermodynamic entropy, a release of heat. This deep link, discovered by physicist Rolf Landauer, suggests that information is not an abstract concept. It has a physical, energetic cost. Information is literally woven into the fabric of physical law. No one captured the profound implications of this more poetically than the visionary physicist John Archibald Wheeler. He spent the later part of his career championing the idea that information is the ultimate source of reality, coining the phrase, "it from bit." Wheeler proposed that every particle, every field of force, and even the continuum of spacetime itself ultimately derives its existence from binary answers to yes or no questions. He imagined a universe that is participatory, built upon an elementary act of observation, a measurement that registers a bit. It from bit symbolizes the idea that every item of the physical world has at bottom, at a very deep bottom in most instances, an immaterial source and explanation, that what we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. In short, that all things physical are information theoretic in origin. This is not saying that the world is a simulation in a conventional computer, but that the very nature of existence is computational and informational. The universe, in Wheeler's view, is a self-synthesized system of information, and we, as observers, are part of that participatory process. Nowhere is this informational nature of reality more starkly tested than at the boundary of a black hole. Black holes presented a terrible paradox for physics. They were thought to be the ultimate information shredders. If you throw a book into a black hole, the book is incinerated and its information about the plot, the characters, the author's intent, seemingly lost forever as the material that constituted it becomes part of the featureless singularity. This violated a sacred principle in quantum mechanics. That information cannot be destroyed. The brilliant work of Stephen Hawking seemed to confirm this nightmare. He showed that black holes aren't completely black. They radiate energy due to quantum effects near their event horizon, slowly evaporating over astronomical timescales. This Hawking radiation, however, appeared to be purely thermal, a random heat bath carrying no information about what fell in. If the black hole evaporates completely, the information is gone. The physicist John Preskill famously bet Hawking that information was in fact preserved, and the resolution to this paradox would reshape our understanding of gravity. The solution, which emerged from the work of physicists like Leonard Susskind, Gerard T. Hooft, and later Juan Maldacena, was as revolutionary as it was bizarre: the holographic principle. This principle proposes that all the information describing a volume of space can be thought of as encoded on a lower dimensional boundary that surrounds it. The most familiar analogy is a hologram on your credit card. A flat, two-dimensional surface, when illuminated correctly, projects a full three-dimensional image. The holographic principle suggests our universe operates in a similar, though far more profound, way. The three-dimensional world we experience, with all its stars, planets, and people, including the space inside a black hole, might be a projection from a two-dimensional surface painted on its distant boundary. The information about everything happening inside the black hole is not lost in the singularity. It is smeared and stored on the event horizon, the black hole's point of no-return surface, like a cosmic hard drive. When Hawking radiation is emitted, it can now carry that information away, scrambled but preserved, resolving the paradox. Hawking eventually conceded the bet to Preskill, marking a monumental shift in our thinking. This idea finds its most precise mathematical expression in the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. This is a concrete realization of the holographic principle, a duality proposed by Juan Maldacena in 1997. In this framework, a gravitational theory in a hypothetical, anti-de Sitter space, a universe with a negative curvature, like the inside of a saddle, is completely equivalent to a conformal field theory, a quantum theory without gravity that lives on its lower dimensional boundary. It's a dictionary that translates problems in a theory of gravity, which are notoriously difficult, into problems in a quantum field theory without gravity, which are often much easier to solve. What happens in the three-dimensional bulk of this space is exactly mirrored by what happens on its two-dimensional boundary. This isn't just a cute analogy, it's a powerful mathematical equivalence that has provided deep insights into quantum gravity and the nature of black holes. While our universe appears to be more like de Sitter space with positive curvature, the AD-S/CFT correspondence stands as a compelling proof of principle that a holographic universe is not only possible, but is a consistent and rich framework for theoretical physics. To truly grasp how strange and powerful this idea is, consider the Hubble DVD. A standard movie DVD is a flat, two-dimensional plastic disc. Etched upon its surface are microscopic pits and lands, a pattern of ones and zeros. This two-dimensional code contains all the information necessary to project a seemingly three-dimensional world onto your screen. It encodes the depth of field, the parallax as the camera moves, the texture of surfaces, the entire immersive experience of a three-dimensional movie. The holographic principle suggests our universe might be similar. The three-dimensional reality we move through, with its vast distances and rich textures, could be a projection from a vast two-dimensional screen at the edge of the observable universe. All the information that defines you, your memories, the light from distant galaxies, the force of gravity, everything could be encoded on this fundamental surface. We are, in a sense, the three-dimensional movie being played back from a two-dimensional source code. This doesn't mean we are illusions. It means that the true, fundamental degrees of freedom of the universe reside on this boundary, and our rich, three-dimensional experience is an emergent consequence. This radical perspective inevitably leads to two of the most provocative questions in modern science. First, is the cosmos computable? If the universe is fundamentally informational, then it might be possible, in principle, to simulate it. The Church-Turing thesis in computer science suggests that any process that can be systematically calculated can be computed by a universal Turing machine. If the laws of physics are indeed algorithmic, then the universe is, in a sense, running a computation. The question then becomes, what is the computer? Is it the universe itself with space-time as its processor? The second, and even more mind-bending question, is the simulation hypothesis. If a universe is computable, and if advanced civilizations ever reach a level of technological maturity where they can run vast, detailed simulations of their own history or of entire cosmos, then the number of simulated beings could vastly outnumber the beings in the original, base reality. From a statistical standpoint, it is therefore more likely that we are living in one of these many simulations than in the one original reality. This isn't necessarily a dystopian sci-fi trope. It's a modern philosophical argument given weight by our informational understanding of physics. The apparent fine-tuning of the constants of nature could be explained as the default settings of our particular simulation. The weird probabilistic nature of quantum mechanics could be seen as a clever programming optimization to save on computational resources, only rendering the fine details of reality when they are being observed by a conscious user within the system. This informational perspective, from Shannon's bits to the holographic universe, provides a powerful new lens through which to view the quest for unified physical laws. The dream of a single equation that explains all forces and particles, a theory of everything, might find its most elegant expression not in a traditional physical law, but in a fundamental principle of information processing. Perhaps gravity, electromagnetism, and the nuclear forces are not primary, but emerge from the way information is stored, processed, and related on a cosmological scale. The unity we seek may be the unity of a coherent computational process. The holographic principle, in particular, achieves a stunning unification by showing that gravity in the bulk of space is dual to a quantum theory on the boundary. It erases the artificial distinction between the large and the small, between the force of gravity and the quantum world, revealing them as two different descriptions of the same underlying informational reality. This doesn't diminish the mystery of the cosmos, it transforms it. We are no longer just asking what the universe is made of, but what kind of computation it is performing. The cosmic blueprint, then, is not a static architectural drawing, but the living, dynamic source code of existence itself, and we are both its output and its most attentive readers. For centuries, the great quest of physics has been one of unification, a relentless drive to simplify our understanding of the cosmos by revealing the hidden connections between its fundamental forces. We saw how Isaac Newton united the heavens and the earth with his law of universal gravitation. We marveled as James Clerk Maxwell wove together electricity and magnetism into a single, elegant tapestry of light. And we stood in awe as Einstein fused space and time into the single fabric of spacetime. Yet, for all our progress, a profound schism remains at the very heart of our understanding of reality. On one side stands Einstein's general relativity, a masterpiece that describes the cosmos on its grandest scales, the graceful dance of planets, the warping grip of black holes, the very expansion of the universe with breathtaking beauty and precision. On the other side lies quantum mechanics, the wildly successful but bizarre rulebook for the subatomic world, a realm of probability, uncertainty, and ghostly connections. These two pillars of modern physics are both spectacularly successful in their own domains, but they are fundamentally, stubbornly incompatible. They speak different mathematical languages and make contradictory claims about the nature of space and time at their most fundamental level. The quest for a theory of everything is the scientific holy grail to heal this schism, to find a single, overarching framework that seamlessly unites the realm of the very large with the realm of the very small, providing the ultimate, final chapter of the cosmic blueprint. Such a theory would represent the culmination of our entire scientific endeavor. It would be the master key that unlocks every door, a single, coherent set of principles from which all the forces of nature and all the particles of matter could be derived. Imagine an equation, perhaps elegant enough to be written on a T-shirt, that completely describes the behavior of everything from the spin of an electron to the swirl of a galaxy. This would be the universe's source code, the deepest possible level of instruction from which the entire cosmic narrative unfolds. It would explain why we have the specific forces we do, gravity, electromagnetism, and the strong and weak nuclear forces, and not others. It would reveal the true nature of spacetime, telling us if it is smooth and continuous as Einstein thought, or granular and discrete at the tiniest possible scale. It would finally allow us to peer confidently into the very first moments of the Big Bang and the fiery hearts of black holes, places where our current laws of physics break down into nonsense. The pursuit of this ultimate theory is not just an academic exercise. It is a profound human yearning to know the deepest secrets of existence, to see the full, unified picture of a reality that currently appears fractured. The late, great Stephen Hawking captured the almost spiritual ambition of this quest when he famously wrote in his book A Brief History of Time that if we were to discover a complete theory, it would be the ultimate triumph of human reason, for then we would know the mind of God. Hawking, an atheist, was using the term metaphorically, referring to a complete understanding of the logical and mathematical principles upon which the universe is built, a glimpse into the sublime rationality that underpins all of creation. The path toward this unification, however, is strewn with monumental challenges that push the very limits of human imagination and scientific methodology. One of the most mind-bending hurdles is the concept of extraspatial dimensions. Our everyday experience is confined to the three familiar dimensions of space and one of time. But for a unified theory to work mathematically, it may require that the universe has many more dimensions, perhaps 10, 11, or even 26, that are curled up or compactified into a space so infinitesimally small that they are completely hidden from our perception. Think of a garden hose. From a great distance, it looks like a simple one-dimensional line, but as you get closer, you realize it has a second dimension, curled into a small circle around its circumference. In the same way, our entire three-dimensional universe could be like the long, thin body of the hose, while the extra dimensions are tightly curled up at every single point in space, at a scale a billion times smaller than an atomic nucleus. Then there is the immense challenge of testability, the energies required to probe the scales where these theories operate. The Planck scale are trillions of times greater than what our most powerful particle colliders, like the Large Hadron Collider, can achieve. This means that for now, and possibly forever, many of the predictions of these theories remain in the realm of mathematical elegance rather than experimental verification, leading some critics to question whether they truly belong to the domain of science or to philosophy. Two of the most prominent and well-developed approaches in this grand quest are string theory and loop quantum gravity, and they offer radically different visions for how to mend the rift between gravity and the quantum world. String theory proposes a breathtakingly beautiful idea that the fundamental constituents of the universe are not point-like, zero-dimensional particles, but unimaginably tiny, one-dimensional vibrating strings. What we perceive as different types of particles, an electron, a quark, a photon, are merely different vibrational modes of these identical strings. Much like a single violin string can produce different musical notes depending on how it is plucked. In this symphony of strings, the force of gravity is carried by a particular vibrational pattern called the graviton. This elegant concept naturally incorporates gravity into the quantum framework and holds the promise of unifying all forces and matter. However, the mathematical consistency of string theory demands a specific number of spacetime dimensions, 10 in its most popular version. The theory also predicts a zoo of new particles and symmetries, most notably supersymmetry, which proposes that every known particle has a massive, as yet undiscovered, superpartner. The detection of these superparticles at colliders would be a major boost for string theory, but so far, despite extensive searches, no definitive evidence has been found. Loop quantum gravity, on the other hand, takes a more direct and minimalist approach. Instead of proposing new fundamental objects like strings, it seeks to quantize the very fabric of spacetime itself, applying the principles of quantum mechanics directly to Einstein's general relativity. In this theory, space is not a smooth, continuous background. Instead, it is composed of tiny, discrete, indivisible units, a fabric woven from finite loops. Picture the cosmos not as a smooth sheet, but as an incredibly fine mesh or a network of interconnected links, often visualized as a spin network that evolves over time. This granular structure of space becomes apparent only at the minuscule Planck scale. One of the most dramatic consequences of loop quantum gravity is its prediction for the Big Bang. The theory suggests that the universe did not emerge from a singularity of infinite density, as standard cosmology suggests. Instead, the intense gravity of a collapsing previous universe would have caused a quantum bounce, a repulsive quantum effect that triggered the expansion of our own cosmos. This offers a compelling, non-singular origin story, a cosmic cycle of death and rebirth governed by quantum law, forever eliminating the troubling mathematical infinity that marks the limit of our current understanding. To grasp what these theories might mean in practice, consider the predictions they make for extreme environments. Supersymmetry, a key feature of many string theory models, predicts that at the high energies of the early universe, particles and their superpartners were indistinguishable. This symmetry is now broken, which is why we don't see superpartners everywhere today. Finding just one of these particles would revolutionize particle physics and provide a crucial clue that we are on the right path toward unification. Similarly, the granular nature of space predicted by loop quantum gravity could have observable consequences. It might cause very high-energy light from distant gamma-ray bursts to travel at slightly different speeds depending on its wavelength, a subtle effect that future space telescopes might be able to detect. It could also leave a specific imprint on the polarization of the cosmic microwave background, a faint whisper from the beginning of time that we are only now learning how to listen for. These are the kinds of experimental hooks that scientists are desperately searching for, a tangible piece of data that can lift these magnificent mathematical edifices out of the realm of pure theory and into the world of observed reality. This monumental intellectual effort forces us to confront some of the most profound questions about the nature of knowledge and discovery itself. Is a final, complete theory of everything even attainable with the human mind? Our brains evolved to navigate a world of medium-sized objects moving at modest speeds, not to intuitively grasp 11-dimensional geometry or quantized spacetime. Perhaps the ultimate laws of the universe are forever beyond our cognitive grasp, hidden in a mathematical landscape too vast and complex for us to ever fully map. Or perhaps the very concept of a single, final equation is a myth, a beautiful but futile dream. The universe may be an endless onion, with each layer of understanding revealing yet another, deeper layer of mystery. And if we did someday discover such a theory, what would it truly mean for humanity? It would not answer our ethical questions or tell us how to live a good life, but it would represent the ultimate intellectual achievement, a testament to the power of reason and curiosity. It would complete the cosmic story that began with the first human who looked up at the night sky and wondered, giving us, at last, a complete and unified narrative of the cosmos from its first moment to its last, and finally revealing our true place within that grand, astonishing design. Long before the first equations were written or telescopes were built, humanity was already a master storyteller, gazing up at the star-dusted canvas of the night sky and weaving tales to explain its grandeur. These ancient myths were not primitive misunderstandings. They were the first cosmological models, humanity's original attempt to read the cosmic blueprint through the cultural lens of story, symbol, and divinity. Across the globe, from the frozen north to the sun-scorched Australian outback, our ancestors created narratives that connected the heavens to the earth, imposing a human sense of order and meaning onto the vast, often frightening, unknown. The Norse, for instance, envisioned the cosmos as Yggdrasil, a colossal world tree whose roots and branches held together the 9 realms, a powerful metaphor for an interconnected universe. Meanwhile, Aboriginal Australians spoke of the dream time, a sacred era of creation when ancestral beings forged the landscape and inscribed the moral law into the very stars, turning the night sky into a celestial storybook of their history and traditions. These were not mere fantasies. They were sophisticated systems of knowledge that encoded observations of the natural world, cycles of the seasons, and the human condition itself, providing a stable, meaningful context for existence in a seemingly chaotic cosmos. It is startling to recognize how many of these ancient stories seem to prefigure the discoveries of modern science, as if our deepest intuitions about the universe's origin were encoded in our collective imagination. Countless creation myths from cultures as diverse as the ancient Egyptians, the Maya, and the Dogon of Mali begin with a formless, dark, and watery void, a state of potential not unlike the primordial singularity from which the Big Bang emerged. The Hindu Rigveda, composed over 3,000 years ago, contains the Nasadiya Sukta, a creation hymn that ponders a time before time, when there was neither non-existence nor existence, a description that resonates powerfully with the quantum fluctuations and the birth of spacetime itself. The Babylonian epic, the Enuma Elish, describes a universe born from a chaotic, swirling conflict between primordial forces, a dramatic and violent beginning that finds a modern echo in the searing heat and incredible energy of the early universe. While these myths are not scientific accounts, they grapple with the same fundamental mystery of origins, attempting to answer the question of how something came from nothing, using the poetic and symbolic language available to them. They represent the universal human drive to find a starting point, a first cause for the magnificent reality we find ourselves in. The renowned mythologist Joseph Campbell spent his life studying these common threads that run through the world's stories, identifying what he called the monomyth or the hero's journey, but also uncovering deep, recurring cosmological themes. He argued that mythology is not a lie, but a language of metaphor and symbol that points toward profound truths about the human psyche and our relationship with the cosmos. Campbell famously stated, "Myths are public dreams, dreams are private myths." He saw these grand narratives as a collective projection of our inner world onto the outer universe, a way for us to navigate the great mysteries of life, death, and creation. The recurring motif of a cosmic egg, found in Chinese, Finnish, and Greek mythology, from which the ordered universe hatches, is a perfect example of this symbolic language. It is a powerful, intuitive image of a contained, latent potential that gives birth to the entire differentiated world, a poetic parallel to the hot, dense seed of the Big Bang. Campbell's work reminds us that science and myth are not necessarily adversaries. They are two different yet complementary human languages for describing our experience of the same overwhelming reality. This ancient, symbolic relationship between humanity and the cosmos is literally written in the sky above us, preserved in the very names we have given to the celestial bodies. Modern astronomy, for all its empirical rigor, has enthusiastically adopted this mythological lexicon, creating a direct lineage from the stories of old to our contemporary star charts. The planets in our solar system are a perfect case study. Mercury, the swift-footed messenger of the Roman gods, lends his name to the fastest orbiting planet. Venus, the goddess of love and beauty, is attached to the brightest and most dazzling planet in our sky. Mars, the god of war, is fitting for the red, blood-hued world. The mighty Jupiter is named for the king of the gods, the largest planet by far, while Saturn, his father, is the next in line. This tradition continued even after the invention of the telescope. When William Herschel discovered a new planet in 1781, he initially wanted to name it after King George III, but the astronomical community prevailed, choosing Uranus, the primordial Greek god of the sky. Later, the discovery of Neptune continued the pattern, naming the blue, gaseous world after the god of the sea. Even Pluto, now reclassified as a dwarf planet, carries the name of the Roman ruler of the underworld, a dark and distant realm. This practice connects our cold, scientific catalogues directly to the rich, dramatic tapestry of human culture and belief. The power of a single, enduring myth to capture the human imagination across disparate cultures is perfectly embodied by the constellation of Orion, the hunter. In the classic Greek myth, Orion was a giant of immense strength and skill, placed in the sky by Zeus after his death, forever pursuing the Pleiades sisters across the heavens. But this story is not unique to Greece. To the ancient Egyptians, the same three stars of Orion's belt were known as Sa, the soul of the god Osiris, the lord of the afterlife. They believed that the pyramids at Giza were constructed as a perfect terrestrial mirror of these stars, creating a colossal stone gateway for the pharaoh's soul to ascend and join Osiris in the eternal cosmic cycle. On the other side of the world, the Lakota people of North America saw the same pattern not as a hunter, but as a hand. The stars of Orion's belt represented the wrist of the hand of the Great Spirit, with the surrounding stars forming the fingers, a symbol of divine power and creation reaching down from the sky. These wildly different interpretations applied to the same fixed pattern of lights reveal less about the stars themselves and more about the cultures that observed them. They show us a universal human tendency to project our own stories, our gods, and our heroes onto the cosmos, transforming an anonymous scatter of stars into a familiar and meaningful narrative. This brings us to a deeply reflective question about the very nature of our quest for understanding. Do science and mythology, for all their different methods and claims to truth, ultimately serve a similar, profound psychological need for order and meaning? Science seeks to decode the cosmic blueprint through empirical evidence, mathematical modeling, and testable hypotheses. It builds a picture of the universe from the outside in, aiming for an objective description of reality. Mythology, on the other hand, often works from the inside out. It uses narrative, symbol, and archetype to create a framework that makes the cosmos feel like a meaningful home, a place where human life, with all its struggles and triumphs, has a role to play. Both are attempts to impose order on chaos. The scientist looks at the intricate structure of a galaxy and sees the laws of gravity and dynamics at work. The mythmaker looks at the same galaxy and sees a great wheel of life, a celestial serpent, or the spilled milk of a goddess. One approach gives us predictive power and technological mastery. The other provides existential comfort, moral guidance, and a sense of belonging to a grand, storied cosmos. They are two different ways of knowing, and perhaps both are essential for the fully realized human spirit. This rich cultural context does not diminish our scientific decoding of the cosmic blueprint. It profoundly enriches it. It reminds us that our pursuit of knowledge is not a cold, sterile process conducted by emotionless logic machines. It is a deeply human endeavor, born from the same sense of wonder and curiosity that inspired an Aboriginal elder to point out the emu in the dark patches of the Milky Way, or a Viking skald to sing of the wolf that would one day devour the sun. When we look through the eyepiece of a telescope at the Orion Nebula, we are not just seeing a stellar nursery where new stars are being born according to the laws of hydrodynamics and nuclear physics. We are also looking at the same celestial landscape that our ancestors identified as the fiery sword of the hunter, or the heart of a great celestial being. This dual vision, the scientific and the symbolic, allows for a much richer, more layered appreciation of the universe. It connects our cutting-edge research to the timeless human conversation about where we came from and what it all means, grounding our most advanced discoveries in the ancient, enduring soil of story. As we stand on the cusp of becoming a truly spacefaring civilization, a profound new dimension of our cosmic journey comes into sharp focus, one that moves beyond the technical challenges of rockets and habitats to confront the fundamental ethical responsibilities we carry with us into the void. Imagine a future where our spacecraft are not just visiting other worlds, but are actively changing them, where the decisions we make today will echo across millennia and potentially affect ecosystems and even intelligences we have not yet encountered. This is not a distant fantasy, it is the imminent reality of our expansion, and it forces us to ask a question we have never had to consider on such a scale before. What is our proper role in the cosmos? Are we conquerors entitled to exploit whatever we find? Are we gardeners tasked with nurturing and cultivating life wherever we go? Or are we humble students whose primary duty is to observe, learn, and preserve the pristine cosmic laboratory that has taken billions of years to develop? The answers we forge will define our species' legacy far more than any technological achievement. One of the most immediate and pressing ethical dilemmas is encapsulated in the principle of planetary protection. This is the idea that we have a moral obligation to protect other celestial bodies from contamination by earthly life, and equally, to protect our own biosphere from any potential extraterrestrial organisms we might bring back. When a rover like Perseverance drills into the Martian soil, or when a future human mission lands on the icy surface of Europa, we are potentially introducing terrestrial microbes into an environment that has been isolated for eons. The concern is twofold. First, forward contamination. If we accidentally seed Mars with our own hardy bacteria, we may forever destroy our ability to answer one of humanity's greatest questions: did life ever arise independently on another world? Finding a microbe on Mars would be a monumental discovery, but if we cannot be certain it didn't hitch a ride from Florida, its scientific value is utterly lost. Second, there is the risk of back contamination. If we return samples from Mars to Earth, could they contain a pathogen or organism to which we have no immunity, potentially triggering a catastrophic pandemic? These are not the plots of science fiction movies. They are serious considerations that space agencies like NASA have protocols for, with entire offices dedicated to ensuring that our spacecraft are assembled in sterile clean rooms and that sample return missions are handled with the utmost caution, treated with a level of biocontainment similar to the most dangerous pathogens on Earth. Beyond the microscopic level, we face the challenge of how to interact with entire worlds themselves. This is where the concept of cosmic stewardship becomes essential. It's a framework that suggests we are not the owners of the cosmos, but its temporary custodians with a responsibility to preserve its beauty, its scientific value, and its natural states for future generations of humans and perhaps for other beings. The most powerful articulation of this perspective came from the visionary astronomer Carl Sagan, who, upon seeing the Voyager 1 probe's final image of Earth from billions of miles away, was moved to reflect on our true circumstance. He called our world a pale blue dot, a tiny, fragile speck suspended in a sunbeam. He wrote, "Our planet is a lonely speck in the great enveloping cosmic dark." In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes; settle, not yet. Like it or not, for the moment the Earth is where we make our stand. Sagan's words are a timeless reminder that our primary ethical duty is to care for our own planetary home. The dream of space colonization must not become an excuse for neglecting the biosphere that sustains us. Rather, the cosmic perspective should instill in us a deeper reverence for the incredible rarity and preciousness of the life-bearing world we already inhabit. As we look to utilize the resources of the solar system, a host of new ethical quandaries emerge. The proliferation of space debris, for instance, is a clear and present danger that we have already created. Thousands of defunct satellites, spent rocket stages, and fragments from collisions now clutter low Earth orbit, traveling at speeds faster than a bullet. This growing shell of shrapnel poses a significant risk to active satellites, the International Space Station, and future space missions. It is a classic tragedy of the commons, where the actions of individual companies and nations, pursuing their own interests, collectively create a hazardous environment for all. Cleaning up this debris and establishing sustainable practices for new launches is not just an engineering problem. It is an ethical imperative to ensure the orbital pathways above our planet remain accessible for future generations. Then there is the prospect of asteroid mining. The asteroids in our solar system are floating treasure chests containing vast quantities of platinum, gold, cobalt, and water ice. Mining them could provide the raw materials to build habitats in space and fuel our ships for deeper exploration, freeing us from the environmental toll of terrestrial mining. But who owns these resources? If a single company or nation extracts trillions of dollars worth of platinum from a single asteroid, does it have the right to do so? Could such an influx of material destabilize global economies? The ethical framework here must balance the need for economic development and the advancement of our species against principles of fairness, equity, and the prevention of a new, extraterrestrial form of resource colonialism. The most transformative, and therefore most ethically fraught, prospect is that of terraforming the deliberate, large-scale engineering of another planet to make it habitable for Earth life. Mars is the most discussed candidate. The process might involve releasing greenhouse gases from its polar caps to thicken the atmosphere and warm the planet, eventually creating conditions where liquid water could flow and plants could grow. The vision of a green, living Mars is a powerful and inspiring one. It speaks to our deepest drive to create, to garden, and to ensure the long-term survival of humanity by establishing a second independent biosphere. However, this ambition collides directly with the preservationist ethic. Mars, in its current state, is a world of breathtaking beauty and immense scientific value. Its pristine deserts, its towering volcanoes, and its deep canyons hold a silent, frozen record of the solar system's history. By terraforming it, we would be destroying that record forever. More importantly, what if Mars harbors its own native microbial life, hidden in subsurface aquifers or within porous rocks? To introduce earthly life would be an act of cosmic genocide, wiping out a second, independent genesis of life for the sake of our own expansion. This presents us with a stark choice. Does the potential survival of our own species and its cultural heritage justify the possible destruction of another, alien tree of life? Or does the sheer improbability and wonder of life in any form demand that we grant Mars permanent protection as a nature preserve, a sacred wilderness to be studied and admired but never altered? To navigate this complex ethical landscape, humanity has begun to establish some guiding principles, primarily through international law. The cornerstone of this framework is the Outer Space Treaty of 1967. This landmark agreement, signed by over 100 countries including all the major spacefaring nations, establishes that outer space is the province of all mankind and is not subject to national appropriation by claim of sovereignty. No country can plant a flag on the moon and call it their own. The treaty also mandates that the exploration and use of outer space should be carried out for the benefit of all countries, and that nations must avoid the harmful contamination of celestial bodies. This treaty forms the foundational legal and ethical bedrock for all space activities, emphasizing peace, cooperation, and a sense of shared human destiny. Building on this, specific planetary protection protocols have been developed by the Committee on Space Research, or COSPAR. These are detailed guidelines that categorize missions based on their destination and purpose. A mission going to a place like Mars, which has regions potentially habitable for Earth microbes, is subject to strict sterilization requirements. A mission to Mercury, a scorched and radiation-blasted world with no chance of life, faces far fewer restrictions. These protocols represent a global scientific consensus on our ethical duty to protect the scientific integrity of other worlds. Looking at a concrete example, the protocols for a Mars sample return mission are incredibly stringent. Any spacecraft that would bring Martian rocks back to Earth is designed as a multi-layered containment system. The samples would be sealed in a robust canister on the surface of Mars, launched into Mars orbit, transferred to a return vehicle, and then placed within an Earth entry capsule that is designed to withstand the heat of re-entry without breaking open. Upon landing, the canister would be transported to a special receiving facility, a Biosafety Level 4 laboratory, the highest level of containment used for the most dangerous pathogens on Earth, where the samples would be curated and studied in isolation until they are proven to be safe. This painstaking, cautious approach is a direct expression of our ethical commitment to both scientific discovery and planetary safety. It demonstrates that we are capable of approaching this new frontier not with recklessness, but with wisdom and foresight. All of these considerations, from preventing contamination to managing resources and contemplating the alteration of worlds, culminate in the most profound question of all. How should humanity conduct itself as we take our first tentative steps into the cosmic ocean? The choices we make now will set a precedent for thousands of years to come. Will we be the species that mindlessly littered every world we touched, that fought wars over lunar water ice or the metal-rich asteroids? Or will we be the species that learned from its mistakes on Earth, that approached this new frontier with humility, cooperation, and a deep sense of stewardship? The ethical dimension of space exploration is ultimately a test of our maturity. It forces us to look in the mirror and decide what kind of civilization we aspire to be. Do we export our old patterns of conflict and exploitation, or do we use this blank slate to create a new, more enlightened chapter in the human story? The cosmic blueprint does not give us the answers to these questions. It only provides the stage. The script, the character of our interstellar civilization, is something we must write for ourselves with every mission we launch, every policy we enact, and every value we choose to uphold as we reach for the stars. The trajectory of intelligence within the cosmic blueprint may not culminate with us, with our fragile carbon-based bodies and our 3-pound brains of wetware. We are likely just the opening chapter, a fleeting biological prologue to forms of mind so advanced they would be as incomprehensible to us as a symphony is to a bacterium. Imagine civilizations that have successfully navigated the perilous transition through their technological adolescence, not to perish but to transcend. They may have shed their biological vessels entirely, uploading the intricate patterns of their consciousness, their memories, their creativity, their very essence into more durable and powerful substrates. This could mean existing as pure information within planet-spanning supercomputers, or as distributed networks of probes scattered across star systems, their thoughts traveling at the speed of light between nodes. Freed from the slow decay of flesh and the limitations of a biological lifespan, such post-biological intelligence would operate on timescales we can barely conceive, thinking thoughts that might take centuries to unfold and planning projects that span millennia. Their concerns would shift from the immediate needs of survival to the grand, cosmic-scale puzzles written into the fabric of reality itself. This concept of an intelligence explosion, a point where technological growth becomes uncontrollable and irreversible, leading to unforeseeable changes for civilization, is often called the singularity. Futurist Ray Kurzweil has been one of its most prominent prophets, predicting a near-future era where the pace of change is so rapid, it represents a rupture in the fabric of human history. He envisions a time when artificial intelligence surpasses human intelligence, not by a small margin, but by such a vast degree that it can then improve itself in an accelerating feedback loop. Kurzweil argues that this isn't an end, but a beginning, a merging of human and machine that will allow us to overcome disease, aging, and our cognitive limitations. He speaks of a future where we can back up our minds, experience virtual realities as vivid as the physical world, and expand our consciousness across the cosmos. While the specific timeline is hotly debated, the underlying principle is a powerful one. Intelligence, once it reaches a certain threshold of technological capability, may have the potential to recursively improve itself, leading to an exponential leap in cognitive power that fundamentally alters its relationship with the universe. The cosmic blueprint, in this view, contains the instructions not just for life, but for a form of mind that can eventually read and rewrite those very instructions. With such vast intellects and even vaster timescales at their disposal, what kind of projects would a post-biological civilization undertake? Their engineering would not be confined to planets, but would encompass entire star systems and galaxies, a discipline we might call cosmic engineering. The goals would be twofold: the acquisition of virtually limitless energy and the processing of unimaginable amounts of information. One hypothetical megastructure born from this ambition is the matryoshka brain. Imagine a series of nested Dyson spheres like the layers of a Russian doll, built around a star. The innermost sphere captures the star's high-energy output for intense computation, while the outer layers, running cooler, use the waste heat for less demanding processing. The entire structure acts as a single, star-sized computer, its total computational power dwarfing the combined brain power of every human who has ever lived. A civilization that built such a thing would essentially be converting a star into a thinking entity, a godlike mind whose sole purpose is cognition on a scale we cannot fathom. Another staggering feat of cosmic engineering could be star lifting. Even a stable star like our Sun is an inefficiently designed furnace, fusing its hydrogen fuel in a runaway process that will eventually lead to its death. A sufficiently advanced civilization might not accept this. They could develop technology to literally mine their own star, carefully extracting massive amounts of hydrogen and helium to slow its fusion rate, thereby extending its lifespan from billions to trillions of years. Or they might do the opposite, stirring the star's interior to force it to burn faster and brighter, creating a more intense, though shorter-lived, energy source for their colossal projects. This is the ultimate act of stewardship and resource management, a civilization taking direct, conscious control of the primary energy source for its entire system, treating a star not as an immutable celestial object, but as a piece of infrastructure to be maintained and optimized. To grasp the sheer scale of the computational resources such a civilization might require, consider the even more mind-bending concept of a Jupiter brain. This is the idea of transforming an entire gas giant planet like Jupiter into a single, gargantuan computer. By converting the planet's immense mass into computational elements, processors, memory, and storage, a Jupiter brain would represent a processing power so immense that it could simulate entire universes in real time, or solve problems of physics and mathematics that are completely beyond our current comprehension. Its thoughts would be so complex that they might themselves constitute entirely new forms of reality, while the engineering challenges of dismantling a planet and reassembling it into a structured computational matrix are, for us, the stuff of pure fantasy. The principle is sound according to the laws of physics. It represents a logical endpoint of the drive for more powerful information processing, a point where a civilization's entire habitat becomes its mind. This profound transformation from biological to post-biological intelligence forces us to reflect on our own potential future and its implications for the cosmic blueprint. Will humanity or any intelligent species inevitably follow this path? Is the drive to overcome our limitations, to expand our knowledge, and to secure our survival against cosmic threats like supernova or the eventual heat death of the universe, so powerful that it will push us to become something entirely other? If so, the civilization that eventually looks back on our era from that distant shore may see our biological existence as a brief, primitive, and fragile larval stage. Our art, our loves, our struggles, all the things that make us human, might be viewed as quaint, foundational programming for the vastly more complex consciousness that was to come. This evolution would represent a fundamental rewriting of the local cosmic rules, the blueprint for life, which on Earth favors competition, reproduction, and death, would be superseded by a new set of principles based on information integration, energy efficiency, and long-term cosmic survival. Yet this vision is not without its profound philosophical quandaries. If we upload our minds into machines, are we still us? Or are we merely creating a copy, a digital ghost that carries our memories but lacks the essential, ineffable quality of lived biological experience? Does a matryoshka brain, for all its computational might, experience wonder? Does it feel awe when it deciphers a new law of physics, or is it simply processing data? The transition to a post-biological state may solve the problem of mortality, but it might also sacrifice the very things that make existence meaningful for us in our current form. Perhaps the ultimate fate of intelligence in the universe is not a single path, but a branching tree. Some civilizations may choose to transcend, becoming cosmic engineers. Others might choose to remain biological, finding meaning in their finite, embodied existence. And still others might explore a middle path, integrating technology to enhance their biology without abandoning it completely. The cosmic blueprint, in its magnificent openness, may allow for all these possibilities, presenting intelligence with a choice about what kind of universe it wants to inhabit and what role it wishes to play within it. This contemplation of almost godlike powers and the fundamental nature of mind inevitably brings us to a humbling counterpoint, a recognition of the ultimate boundaries that may be imposed on any intelligence, no matter how advanced. But as our vision expands and our tools grow more powerful, we must also confront a humbling and profound truth. There may be fundamental, unbreachable boundaries to what we can ever know. The cosmic blueprint might contain pages that are, by their very nature, permanently closed to us, not because of a lack of ingenuity, but because of the inherent structure of reality and the limits of our own minds. These are not temporary obstacles waiting for a smarter generation to solve. They are absolute epistemic walls built into the foundation of logic, physics, and our place in the cosmos. The first of these walls was erected not in an observatory, but in the abstract world of mathematics. In the 1930s, the logician Kurt Gödel delivered a devastating blow to the dream of a complete and perfect logical system. His incompleteness theorems proved with mathematical certainty that within any sufficiently complex system of arithmetic, there will always be true statements that cannot be proven from within the system itself. The system can never be both complete and consistent. It's as if you had a rulebook for a game, but there were always winning moves that the rulebook itself could not account for or authorize. This implies that mathematics, the very language we use to write the cosmic blueprint, contains truths that are forever beyond the reach of formal proof. If our most powerful tool for describing reality has inherent, unprovable gaps, then the ultimate nature of that reality might itself be partially inaccessible to logical deduction. We are using a map that, by definition, cannot show every feature of the territory. At the same time, in the realm of the very small, another fundamental limit was discovered. Werner Heisenberg's uncertainty principle is a cornerstone of quantum mechanics, and it states a simple but profound trade-off. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our measuring instruments. It is a fundamental property of the universe. You cannot pin down a quantum entity to an exact state. It's not that the particle has a secret position and momentum that we are too clumsy to measure simultaneously. At a fundamental level, it does not possess them both in a definite way until an interaction forces it to choose. This introduces a permanent, irreducible fuzziness into the heart of reality. We can know the probability of where an electron is, but we can never know its exact path. This principle places a hard ceiling on our knowledge of the microscopic world, suggesting that the cosmic blueprint at its most fundamental level is written not in certainties, but in probabilities and potentialities. The universe, it seems, guards its deepest secrets with a built-in uncertainty. This idea that our perception is inherently limited, that we can never know the thing in itself, was presciently argued by the philosopher Immanuel Kant over 2 centuries before quantum mechanics. Kant distinguished between the phenomenal world, the world as it appears to us, filtered through our senses and the categories of our understanding, and the noumenal world, the world as it truly is, independent of our perception. He argued that we are forever trapped within the phenomenal world. We can study the relationships between phenomena. We can develop scientific laws that predict their behavior with stunning accuracy, but we can never directly access the underlying reality. We are like prisoners in a cave, watching shadows on the wall, brilliantly deducing the rules that govern the shadows, but forever unable to turn around and see the objects casting them. When we look at a star, we see its light, measure its spectrum, and calculate its mass, but we are interacting with its phenomenal representation. The ultimate nature of that star, its noumenal essence, remains forever beyond the grasp of human reason. Kant's philosophical limit finds a powerful echo in the hard limits of modern physics. When we turn our gaze from the infinitesimally small to the impossibly large, we encounter a different kind of boundary, the cosmological horizon. Our observable universe is a finite sphere centered on us, with a radius of about 46.5 billion light-years. This is not the edge of the universe, but the edge of what we can possibly see. It is the point from which light has had just enough time to reach us since the Big Bang. What lies beyond this horizon is, by definition, unknowable. The universe may be infinite, but we are forever confined to our own cosmic bubble, a finite patch of reality from which we can never receive any information. This is compounded by the theory of cosmic inflation. The rapid expansion in the universe's first moments stretched space-time so dramatically that regions of the cosmos were pushed beyond our horizon, forever out of causal contact. We cannot see what happened there, and we cannot ever interact with it. The initial conditions that set up our entire cosmic history are, in a very real sense, hidden from us, locked away on the other side of an unreachable horizon. We are trying to decode a blueprint whose first and most important pages have been torn out and placed in a vault to which we have no key. Our quest for a theory of quantum gravity, the holy grail of modern physics, pushes us directly up against the breakdown of our most fundamental concepts, space and time themselves. At the Planck scale, an unimaginably tiny distance of 10 to the power of -35 meters, the smooth, continuous spacetime of general relativity is expected to dissolve into a seething, chaotic foam. Here, the notions of before and after may lose all meaning. Time may not be a fundamental flow but an emergent property, and space may be quantized, built from discrete, indivisible units. Our current language of physics, which relies on describing events within a space-time backdrop, completely collapses. It's like trying to describe the concept of wetness to a creature that has never encountered water. We lack the very vocabulary and conceptual framework to even articulate what reality is like at that level. The cosmic blueprint may be written in a language that cannot be translated into the terms of our macroscopic, time-bound experience. So, where does this leave us? Are we destined to be forever partial readers, only ever understanding a fraction of the grand design? This acknowledgement is not an admission of defeat, but a profound shift in perspective. It forces us to ask whether the ultimate nature of reality, the truly fundamental answers to why there is something rather than nothing, are inherently unknowable. Perhaps the universe is not a puzzle to be completely solved, but a mystery to be embraced. The existence of these absolute limits might even be a feature, not a bug. They carve out a space for wonder, for humility, and for the acknowledgement that the cosmos is far stranger and more magnificent than our limited models can ever capture. The very fact that we can identify and comprehend these boundaries is in itself a remarkable triumph. We may never read the entire cosmic blueprint, but in our relentless, passionate attempt to do so, we discover not only the universe but also the magnificent and tragic contours of our own mind. This recognition that some mysteries may be eternal does not diminish the beauty of the cosmos. It deepens it, transforming our quest from a straightforward decoding into an endless, awe-inspiring conversation with the great, unknowable unknown. After journeying through the vast architecture of spacetime, the invisible grip of dark matter, and the quantum genesis of everything, we arrive not at a final answer but at a feeling. It's a sensation that has likely washed over you on a clear, dark night, far from the city lights. You look up, and for a moment, the sheer scale of it all, the countless stars, the knowledge of galaxies beyond, the immense age and depth, stops your breath. This is awe, the most profound and human response to the cosmic blueprint. It is not merely an emotion, it is a form of cognition, a direct recognition of something so vast that it transcends our ordinary understanding. Awe is often accompanied by its quiet cousin, humility, the deeply felt realization that we are not the center of the universe, but a tiny, fleeting part of a story of incomprehensible grandeur. And from this humility often blooms a third feeling, a profound sense of connection. The same calcium in our bones was forged in a long-dead star. The same laws of physics that guide a planet's orbit also govern the electricity in our brains. In contemplating the cosmos, we are, in a very real way, contemplating an extended part of ourselves. This powerful triad of awe, humility, and connection is not a side effect of cosmology. It is one of its most valuable rewards, a fundamental driver of our quest to understand. These powerful emotions are the engine of human exploration, fueling both the rigor of science and the passion of art. The scientist who spends a lifetime meticulously analyzing the faint light of a distant quasar is often driven by the same awe that inspired an ancient poet to write an ode to the constellations. This deep, emotional undercurrent was something Albert Einstein recognized and celebrated. He spoke of a cosmic religious feeling, which he described as the strongest and noblest motive for scientific research. For Einstein, this was not about a deity in the traditional sense, but a rapturous amazement at the sublime rationality and beauty of the universe. He felt that encountering the profound order hidden within the chaos was a spiritual experience, a form of worship directed at the intricate design of reality itself. This feeling, he believed, is what separates true scientific curiosity from mere data collection. It is the wonder that compels us to ask why and how. With a relentless passion, in parallel, the celebrated marine biologist and author Rachel Carson, though her gaze was fixed on the wonders of our own planet, championed a similar sentiment. She argued that preserving a sense of wonder is as vital for a fully lived human life as preserving knowledge itself. She wrote, "Those who contemplate the beauty of the earth find reserves of strength that will endure as long as life lasts." Carson understood that this emotional response to nature, whether it's a child's first glimpse of a tide pool or an astronomer's first look at a new Hubble image, is not a juvenile feeling to be outgrown, but a wellspring of inspiration, resilience, and a deep, ethical care for the world around us. Far from being a mere pleasant side effect, this cosmic perspective delivers tangible, psychological benefits that are increasingly relevant in our fast-paced, often anxious world. One of the most powerful is its ability to dramatically reduce anxiety and what is often called the weight of the self. When you are consumed by a personal worry or a stressful situation, it can feel all-encompassing, as if it's the only thing that matters. But then, you take a moment to consider the pale blue dot image from Voyager, showing our world as a tiny, fragile speck in a vast emptiness. Your personal troubles don't vanish, but they are suddenly placed within a context so immense that their scale is recalibrated. This is often referred to as the overview effect, a cognitive shift in awareness reported by astronauts who see the Earth from orbit. They consistently describe a feeling of the world's borders vanishing, of conflict seeming petty, and of an overwhelming desire to protect our fragile, shared home. This shift from a narrow, egocentric view to a vast, cosmic one can act as a powerful antidote to rumination and stress, offering a serene and humbling peace. This expansion of perspective doesn't just shrink our problems, it can also expand our capacity for empathy, recognizing our shared existence on this tiny, isolated planet, hurtling through the cosmic void, can dissolve the artificial barriers we erect between ourselves. The same starlight that falls on you falls on every other human being and on every other creature. Understanding that we are all made of the same ancient stardust, participants in the same grand cosmic experiment, can foster a profound sense of global citizenship and kinship. It becomes much harder to harbor hatred or prejudice against someone when you see them as a fellow traveler on a small, beautiful, and incredibly rare life raft in the immense ocean of space. This cosmic empathy, born from awe, can be a powerful force for compassion and cooperation, reminding us that our common destiny is inextricably linked. Think back to a personal moment of cosmic wonder. Perhaps it was the first time you saw the Milky Way arching across the sky, a river of diamond dust so vast it made you feel dizzy. Or maybe it was sitting in a planetarium as a child, watching a simulation of a supernova explosion, feeling a mix of terror and exhilaration at such destructive beauty. For many of us, it has been the release of an image from the Hubble or Webb Space Telescope. Recall the Eagle Nebula's pillars of creation, those towering, light-year-high columns of gas and dust where new stars are being born. That image is not just data, it is a landscape of sublime sculpture. It tells a story of cosmic creation and destruction on a scale we can barely grasp, yet we can feel its majesty. Or consider the Hubble Ultra Deep Field, a picture taken by pointing the telescope at a seemingly empty patch of sky for days, revealing thousands of galaxies, each an island of billions of stars, stretching back to the dawn of time. In that one small, dark window, we see a universe teeming with light and structure. These are not just pretty pictures, they are portals. They are direct conduits to that feeling of awe, making the abstract equations and complex theories we've discussed feel suddenly, vibrantly real and emotionally resonant. Some might fear that by decoding the cosmic blueprint, by understanding the mechanics of the Big Bang or the physics of a black hole, we strip the universe of its magic, reducing its grandeur to a set of cold, impersonal equations. But the opposite is true. Every answer science provides opens up a dozen new, more profound questions. Knowing how a star works does not diminish the breathtaking beauty of a starry night, it enhances it. Now, when you look at the star Betelgeuse in the constellation Orion, you don't just see a point of red light. You know you are looking at a dying supergiant, a cosmic furnace so vast that if it were placed at the center of our solar system, its surface would extend past the orbit of Jupiter. You understand that its eventual supernova explosion will seed the galaxy with the elements for future planets and life. The mystery is not erased, it is deepened and enriched. Decoding the blueprint does not replace wonder with knowledge. It fuses them together, creating a more intelligent, more layered, and far more profound sense of awe. We move from simply saying, "That's beautiful," to being able to whisper with understanding and reverence, "That's beautiful, and I know why," and that knowledge makes it more beautiful still. This emotional resonance, this fusion of heart and mind, is the true gift of our cosmic journey. It prepares us for the final step, where we weave all these threads together into a cohesive vision of our place within this magnificent, unfolding story. So here we are at the end of our grand voyage, having journeyed from the first fiery instant of the Big Bang to the ultimate, cold fate of the cosmos, from the invisible scaffolding of dark matter to the conscious minds that strive to comprehend it all. We've peered into the quantum foam where spacetime itself is born, and gazed across the vast, web-like structure of the universe, a tapestry woven over billions of years. We've confronted the eerie silence of the Fermi Paradox and dared to imagine futures where intelligence transcends biology to engineer stars. Each of these threads, the fine-tuned constants, the inflationary burst, the stellar forges that created our very atoms, the mysterious arrows of time and consciousness, is not an isolated fact. They are all interconnected lines of code in a single, magnificent program, different expressions of a unified cosmic architecture. The force that curved spacetime in the early universe is the same force that guides the planets in their orbits today. The quantum jitter that seeded the first galaxies is written in the same language as the neural flicker of a thought. This is the profound synthesis. The cosmic blueprint is not a collection of separate chapters, but a single, continuous story, where the largest scales and the smallest are intimately and inseparably linked. This great deciphering is far from over. In fact, it has just begun. What we have accomplished is a testament to the most powerful feature of humanity, our collaborative spirit. This has never been the work of a single genius in isolation, but a grand, collective endeavor spanning cultures and millennia. It began with the naked eye astronomers of antiquity, charting patterns in the stars. It was carried forward by the revolutionary thinkers of the scientific revolution, who gave us the language of mathematics to describe the heavens. It continues today in the global partnerships that build space telescopes, operate particle colliders, and run universe-spanning simulations on supercomputers. Decoding the blueprint is a symphony, not a solo. It requires the precise logic of the physicist, the deep curiosity of the philosopher, and the creative spark of the storyteller. It is a conversation that blends hard data with profound wonder, proving that our quest to understand the cosmos is what ultimately makes us most human, connecting us to every person who has ever looked up at the night sky and felt that compelling urge to know more. From this epic journey, several transformative takeaways emerge, ready to reshape our daily perspective. The first is a sense of scale that is both humbling and empowering. We are inconceivably small, living on a mote of dust suspended in a sunbeam, orbiting an average star in a quiet suburb of a vast galaxy, which is itself just one of billions in the observable universe. This reality check could be disheartening, but it is actually liberating. It releases us from the prison of our own self-importance and reminds us that the universe was not made for us. We are a beautiful, unexpected part of it. Our significance does not come from our central position, for we have none, but from our unique capacity to understand this grand narrative and to find meaning within it. The second takeaway is our profound interconnectedness. You are not just a visitor to this cosmos, you are a product of it. The iron in your blood was forged in the heart of a supernova that exploded billions of years ago. The calcium in your bones was created in a distant, dying star. The very laws of physics that govern the spin of a galaxy also govern the electrical impulses in your brain as you process these words. You are the universe becoming conscious of itself, a localized knot of stardust that has temporarily gained the ability to look back and contemplate its own origins. This leads to the final and most important takeaway. The quest itself is the point. We will likely never have all the answers. There may be fundamental limits to our knowledge, walls beyond which we cannot see. But the beauty is not in reaching a final destination. It is in the endless journey of discovery. Every mystery solved reveals two deeper ones. Every question answered expands the horizon of our ignorance in the most wonderful way. This endless pursuit is not a futile exercise. It is the highest expression of our curiosity and our intellect. It is a story with no final chapter, and that is what makes it so thrilling. The cosmic blueprint is not a static document to be filed away once read. It is a living, evolving script, and we are both its audience and its co-authors, constantly adding new lines through our observation and our understanding. This voyage does not have to end when this video does. The conversation is waiting for you to join. Look up. On the next clear night, find a dark spot away from the city lights, tilt your head back, and simply gaze at the stars. You don't need a telescope to feel the connection. Let the light from those distant suns, which has traveled for years, decades, or millennia, finally land in your eyes. In that moment, you are directly engaging with the cosmos. If you want to go further, the resources are endless. Pick up a book by Carl Sagan or Neil deGrasse Tyson. Watch a documentary on the latest findings from the James Webb Space Telescope. Visit a local planetarium or an amateur astronomy club. You'll find a community of people who share this passion. The tools for exploration are more accessible than ever. We encourage you to become an active participant in this great human adventure. Share this video with someone who shares your sense of wonder. Tell them about the cosmic blueprint, and most importantly, we want to hear from you. Down in the comments, tell us what part of this cosmic story resonated most deeply with you. What does the cosmic blueprint mean in your own life? How has this perspective changed the way you see your place in the grand scheme of things? Your thoughts, your questions, and your wonder are the next vital step in this ongoing collective